authorities, with regional authorities, and other stakeholders. Our university is a coordinator of the Volga region medical cluster, which includes 6 universities. We also coordinate innovative cluster of pharmaceutical technologies here in the Samara region with about 70 participants. For about 6 years now, we've been forming the new industry for our area, IT in medicine. And of course, another strategic goal is to make our region known not just as one of the centers of space exploration, petrochemistry, or other industries, but also as one of the IT medicine capitals of Russia. We are in close interaction with our regional authorities and with the governor of the region, Mr. Zdarov, who supports all initiatives of our university as we develop breakthrough technologies. But most importantly, these technologies and developments reach our patients here. I'd like to once again thank the governor and the government of our region. Again, we are a center of innovative and technological development. Our university has extensive interaction with real industry companies. They can be major state corporations and IT companies, dozens and dozens of companies that really work in the economy. Of course, we cooperate with a number of development institutions, with the Foundation of Innovative Support, with Skolkovo and many others, and we pay special attention to interaction with foreign or international companies and universities. We cannot develop science or research in the Russian Federation separately or in separation from the rest of the world. Again, it's of global nature, and we are trying to reach synergy and get to the new levels. Our university today is a scientific and innovative center developing a number of areas that are connected with the topic of our conference today. We have a medical social rehabilitation center. We develop expert systems and systems of supporting making decisions by doctors, preventive medicine, educational technologies that help us develop new products. We have an extensive knowledge in the industry. We have clinics and trials. We interact with actual hospitals in the region and the entire country, and we always have access to depersonalized medical data. As we accumulated experience in the last 8 years, we have some serious technology competencies having to do with VR. We run 7 VR projects and 6 projects in augmented reality, neural networks, 2 projects in big data, 6 projects in BCI, and also lab on chip. There are 5 projects there, simulation technologies, and many other innovations. And for most of the projects, we have already reached the stage of making it part of the everyday life. We're also one of the centers of the digital technologies federal project here in the Russian Federation. We want to create conditions to increase the number of companies that are involved in forming the markets of digital economy. We also try to develop new products and services for virtual and augmented reality, and we need to overcome technological barriers as we reach targets of the roadmap for the comprehensive digital technologies program. Again, we're running a number of projects currently, and for each one of them we have a business partner, and at the end we will have a special project for commercialization. These are the projects that we are implementing. We have to develop special devices to restore and rehabilitate micro and general motor functions of humans using virtual reality and different audiovisual scenarios. We create a set for social rehabilitation of patients with multiple sclerosis and autism. And we also work on other areas as we create a simulator for surgery using virtual reality. We develop a system of tracking of marker objects and feedback in mobile devices of augmented reality. We have software, hardware, modular integration with a surgery microscope for surgery navigation system. We have 2 simulators to deal with emergency situations at gas distribution networks and checking knowledge and skills of the people working with railroad systems. And also have some projects related to HR, or digital HR. This is what we're going to implement as we are done with our main program. Also, we have a well-equipped technical park. We have more than 20 units of high-tech equipment, more than 120 highly qualified specialists who work for our university. They are IT specialists, engineers, and designers. Again, they are university employees, let me say it again. And we have all these broad competencies as we develop our projects from ideas all the way to trial and mock-up stage. Let me also briefly introduce to you some of the products that will be presented later in the course of our Neuro Week. There's one project, this is Reviver, to rehabilitate people with the defects of lower extremities. It helps imitate walking as the patient is involved in the virtual environment, as there's tactile impact on the feet of the patient. There's feedback. We get excellent motivation for the patient. We activate their walking reflex, improve their motor functions, increase their efficiency of the rehabilitation process. And there are around 20 such units already deployed in the centers of CRS. Another project is, again, to rehabilitate patients with defects of lower and upper extremities. We started working with kids, working with palsy patients, and then we moved on to the adult patients. And the product is actually works quite well. There's this optic tracking of the movements of those patients. There's the feedback with some visual and audio effects. And again, it has been installed in more than 20 Russian centers. Another one is Reviver gloves for micro motor movements. As we track the movements of patients' fingers and wrist in the VR environment, there's this feedback, tactile feedback. We also can collect analytical information. We see how we can restore the micro motor functions, and eventually we speed up rehabilitation doing that. Our next product is Reviver Audio. This is hardware, software set of equipment to rehabilitate spatial capabilities and hearing. And that helps our patients to find themselves in the environment and to orient in the environment. We diagnose spatial and speech-based hearing. We activate cognitive functions. And another project deals with patients of problems with lower and upper limbs or extremities. We use VR helmets, optical tracking systems, biological feedback with audio and visual effects, and the ability to solve cognitive tasks. There is gaming, first-person content that motivates the patient, and the analytical information system allows the doctor to monitor the progress of the patient. As I said today, together with our partners, Smart Lab, running neuromarketing study of objective assessment of emotions and feelings of human beings as they interact with advertising and the product.
So what are the advantages? First of all, we can measure the information about our consumers' reactions at any point in time. We can look at the ads through the clientele's eyes, and we can research outdoor advertising, TV advertising, goods packaging, and so on and so forth. So this lab has been created as part of our normal physiology department, and they're doing the research in this field. So I would like to thank my colleagues from the Higher School of Economics in Moscow. We have won the grants for a joint laboratory, for a mirror laboratory. We have been using state-of-the-art neurorehabilitation technologies. We have been applying virtual reality, robotics, and so on and so forth. As a result, we have developed a joint software that facilitates the rehabilitation of patients after cranial trauma and stroke. And I would also like to tell you a little bit about our research in neurorehabilitation so that you have more of a glimpse of our competences. Together with the ATS development company, we developed the Pirogov anatomical table. This is a 3D human body model, so it allows us to study the gross anatomy of the human body, the gross anatomy, normal anatomy, pathological anatomy, surgery, histology, pathomorphology. So we have been using PACS and viewer systems that allow us to come up with a 3D model of a specific individual. Therefore, we can evaluate the state of the patients, and we can select the management tactic in treatment of these patients. So I would like to say that that is something that's truly a breakthrough for the Russian Federation and the world, and this virtual 3D model is already in use. We have also created an educational VR simulator that allows us to have extremely realistic 3D rendering. We can model the doctor's performance. There are a lot of different elements. It could be also multi-user. The system, it allows for extensive system of accreditation. So it works with ophthalmology, endocrinology, and so on, as well as it has communicative stimulation. We have also developed the Autoplan surgical navigation system. That is the first system that has been fully tested and has been registered in Russia. So we have already integrated 10 of these systems across various centers in the Russian Federation. When we're talking about breakthrough ideas, we, of course, have to mention how important it is to educate and train our staff. So we have to start from high schools, and so we have set up special centers that are housed in our universities. So we work with undergraduate, postgraduate students, and so we are one of the first in this country to offer this training in medical IT system, medical diagnostic imaging, and so on and so forth. So we have developed a training product for PhD students of medicine. And this year, we introduced a new course in our university, which is medical cybernetics. And next year, we will open our doors to potential students. Another thing that I wanted to emphasize is that we have been developing more thorough integration of our products into medical education. We have been expanding our research into big data, into the system that provides support for medical decision making. This system uses AI. We have been introducing a pilot project to use experimental legal regulations, the so-called regulatory sandbox. And our university, our medical university in Samara, has been a part of the Research and Education Consortium. And so we have been taking part in a very important tender. Distinguished colleagues, I tried to be very brief in telling you about our achievements that came to be in the last year. We have also developed a program for further advancements over the next 5 years. So we have plans to make Samara Medical University one of the leading medical research universities in Russia. And so we do hope that our university will become known globally as well. I would like to tell you that this year mark a watershed for our university because we appeared in a very prestigious international rating, Time Education. We have become one of the top 200 global universities, 200 global medical universities in the world, and we have appeared in many subcategories of this ranking system, which also shows that we have chosen the right development vector. We have been developing bilingual learning environments. We have been inviting our international colleagues to take part in joint educational activities. We have set up student exchange programs, lecture exchange programs, and so on. So I do believe that joint development of our university and cooperation with the global leading medical universities and clinics will contribute to the development of medical science. As a provost of this medical university, I would like to assure you that I am going to give my full personal support and financial support to any new undertakings so that our medical university is fully integrated into the global development of neural technologies. I personally believe that neural technologies are the most promising medical technologies, and I think that we will see a substantial cumulative effect after these technologies have been introduced. I do hope that we are going to have a fascinating Neuro Week hosted by Samara Medical University. So many thanks to Alexander Kalsanov. And let me just tell you what it is that we're going to be doing this week. This is the sixth annual Neuro Week conference. It has been attended by more than 3,000 people in the last 6 years. But I think this year we're going to have a lot of more delegates because people can connect from all over the world. We have 20 countries that are taking part in this conference. So this year, this conference is a truly large-scale event because it has become a Neuro Week. So right now, we are going to open the BCI Samara 2020 conference. We are about to start or kick off the plenary session. And with this, I would like to give the floor to our host, to Professor Christoph Guger from Austria. Christoph, over to you.
sitting at the moment in Austria, so I missed the opportunity to come to Samara this year, so I was looking forward to be there. And we are already starting with our first speaker, which is Seong-Hwan Lee from Korea University. He's a world expert for machine learning, did a lot of work with brain-computer interface many years. He's also in the Academy of Science in Korea, so a very well-known man. And today he will show us a video about brain-to-speech decoding with a brain-computer interface using imagined speech. So he couldn't join us personally, and that's the reason why we will be recording from him. So I see already the video coming in. Speak out of your mind, brain to speech using imagined speech. And I will close my video so that the presentation becomes...
Hello, my name is Seong-Hwan Lee from Korea University, Seoul, Korea. I am very honored to give a talk in this Samara conference. The topic I am going to talk about today is brain-to-speech technology using imagined speech. Brain-computer interface is a technology that interprets the user's intention from brain signals and delivers to the external world without relying on the normal output pathways of peripheral nerves and muscles. In short, external environments are controlled using brain signals. Many BCI research projects are going on around the world. Typing by Brain project of Facebook aims for typing 100 words per minute using brain signals. Also, Human AI Hybrids project by Neuralink, owned by Elon Musk, aims for developing BCI communication to connect humans and computers based on AI. They are currently developing brain chip to detect human states in real time. BCI research is also actively underway in the automotive industry. Nissan is developing a self-driving technology to read the driver's intentions from brain signals. One of the key functions of BCI is to enable communication with external world only with the brain signals. BCI speller system is the most widely used BCI communication method, which enables typing with brain signals. Conventional BCI speller systems such as event-related potential speller, steady-state visual evoked potential speller, and motor imagery speller have shown robust performance in conveying the user's intention. However, these conventional BCI speller systems hold crucial limitations of relying on external stimuli and requiring display equipment for selecting the characters. This is because they operate with brain signals induced by external stimuli or brain signals unrelated to the language. Current BCI systems are orienting towards an intuitive system that users can operate easily. Since the conventional BCI communication system brings up issues of non-intuitiveness and conversation irrelevance, intuitive BCI communication based on speech-related BCI paradigm is recently gaining attention. Imagined speech is the emerging paradigm for an intuitive BCI communication that can directly convey the user's intention. It is an intuitive BCI paradigm since speech is a natural and most widely used form of human communication. Imagined speech is a signal that occurs when you imagine speaking without making a sound or moving the articulators. Language-associated brain areas over the temporal lobe is activated during the imagined speech. Specifically, Broca's area is related to generating language, whereas Wernicke's area is related to understanding language. As you can see on the table, there are various types of speech assorted by whether it involves voice output or actual motion of the articulators. Spoken speech is a natural speech that we speak out loud. Silent speech is a type of speech without making voice output but still moving your mouth and tongue. And imagined speech is imagining as if you are speaking without both voice output and the movement of the articulators. Let me take a look at the features of imagined speech. Time frequency features of imagined speech is an important component in interpreting the user's intention from brain signals. Low frequency band under 30 Hz reflects the features related to each syllables and the intensity of pronunciation. The high frequency band reflects the temporal features of the neuronal activity potentials that alters according to the pronunciation of words. High frequency activity is known to be shown on the speech control center during speech. For the special features, Broca's area and Wernicke's area on the temporal lobe is mainly known to be activated during the speech process. Besides the left temporal areas, the speech process involves widely distributed brain areas, which initiates utterances in frontal motor areas and ends with the superior temporal gyrus. Different spatial patterns are reported to be displayed on the temporal lobe depending on the pronunciations. The features of imagined speech is known to resemble a certain portion of spoken speech. As I mentioned before, the difference between imagined speech and spoken speech is whether it involves the utterance of sound and movement of the articulators. Although the imagined speech does not involve sound output nor movements, the brain signals of imagined speech displays similar patterns as the spoken speech. The envelope and the power spectrum of imagined speech brain signals have shown correlation with that of spoken speech. Using these features, there are two research streams of brain-to-speech. One is the imagined speech classification framework based on brain signal. Imagined speech classification framework is the most commonly used BCI framework, which consists of training and the classification process of predefined classes. The experiment can be designed as a sentence level, word level, or phoneme level classification. Feature extractor and classifier-based decoding framework is used to classify the imagined speech from brain signals. The BCI performance can be measured by accuracy, kappa value, sensitivity, and specificity. This classification framework allows relatively robust performance, but only limited number of pre-trained classes can be decoded. Another brain-to-speech research stream is the spoken speech reconstruction based on brain signals. This approach aims to synthesize spoken speech from brain signals. The experiment is designed by acquiring various sentences containing various phonemes. Encoder-decoder-based speech synthesis framework is mainly used, and the performance is measured by mean objective score, capsular distortion, or word error rate. When successfully developed, intuitive communication based on brain signals with a high degree of freedom is possible by the speech reconstruction framework. This table shows the imagined speech classification works. Imagined speech classification works using brain signals are rapidly developing. Relatively robust classification performances have been reported with both invasive and non-invasive methods. Although various architectures have been proposed for robust classification of imagined speech, research issues are still remaining. Compared to the conventional BCI paradigms, such as motor imagery or event-related potentials, the underlying intrinsic features of imagined speech is still remaining unrevealed. Issues about imagined speech, such as event-related synchronization or desynchronization patterns for motor imagery, is yet unknown. The frequency and the timing issues of imagined speech needs to be further discussed, and robust decoding with small cortical areas is challenging. Another issue of imagined speech classification is that the experimental design of imagined speech varies upon individual works. This may affect the results of imagined speech decoding. Now, there is no uniform standard of the experimental design of imagined speech. Some works provide auditory cue, and some other works provide visual cue during the imagined speech. There are issues of how to provide the cue for the subjects, how to treat the different length of imagery for different words, and how to set the conditions of the imagery phase. These are the spoken speech reconstruction works based on brain signals. As you can see, speech reconstruction works are reported mainly using invasive brain signals of spoken speech. Various methods are rapidly proposed to show the potential of speech reconstruction based BCI. Although spoken speech reconstruction based on BCI signals have shown their potentials, there are crucial issues to be solved to expand the speech reconstruction framework on imagined speech. Unlike the spoken speech, imagined speech do not have the vocal ground truth for training the speech synthesizer. Also, since we cannot find out the exact onset of imagined speech, issues of how to match the brain signal with the corresponding speech audio is another issue. Lastly, expanding the invasive BCI technologies to non-invasive BCI technologies is another critical issue to be solved for practical use. From now on, I would like to briefly introduce the recent research activities in our lab. We have mainly focused on the non-invasive BCI technologies. We named our works as BTS, which stands for brain to speech. In other words, this technology is to translate the user's imagined speech into voice output. Intuitive BCI communication is possible just by imagining the very thing that the user wants to say. Here is recent work on imagined speech reconstruction based on invasive brain signals.
Shipbuilding is a most fascinating process.
Shipbuilding is a most fascinating process.
The proof that you are seeking is not available in books.
The proof that you are seeking is not available in books.
We constructed a large database of imagined speech along with the spoken speech. 16 subjects participated in this study. In the imagined speech session, subjects were instructed to imagine pronouncing the clock after hearing the cue audio of clock. In the spoken speech session, subjects spoke out loud after hearing the cue audio. We used the audio of 12 words for the cue. 12 words contain 6 concrete words that have a specific form and 6 abstract words without specific form. We observed common features of imagined speech and spoken speech. We found speech-related potentials that have shown significant correlation between imagined speech and spoken speech. As you can see in the left figure, positive peak near 600 milliseconds from the onset and the negative peak near 1100 milliseconds was mainly found. Also, common spatial patterns of imagined speech and spoken speech have shown similar distributions between each other. The common spatial patterns of imagined speech have shown widely distributed patterns over sensory motor and temporal areas. Importantly, we found ERD-ERS patterns focus on the left frontotemporal area, which is related to speech production. The classes with low true positive rate had shown a relatively weak activation patterns on the temporal lobe. For the intuitive BCI communication, we compared the results of imagined speech with another intuitive paradigms, visual imagery. We classified the aforementioned 12 words into a total of 13 classes, including a rest state class. The 12 words contained vocabularies that are frequently used for patients' conversation. Our classification performance outperformed the confidence boundary in both the imagined speech and the visual imagery. Also, the binary classification accuracy was maintained when only using the channels from relevant brain signals. We further investigated the interesting features that affects the decoding of imagined speech by comparing the results of imagined speech with visual imagery. Interestingly, the results of imagined speech and visual imagery have shown a significant correlations, implying the effect of conceptual meaning on the decoding performance. We are currently working on applying the transfer learning to improve the imagined speech classification performance. We extracted the common features of imagined speech and spoken speech included in the high-frequency activation. Therefore, we are developing a domain transfer learning-based feature analysis technology optimized for the imagined speech classification. Let me show you the demo video of our imagined speech classification works.
Tom, help me.
I'm here. What can I do for you?
How's the weather today?
Look, it's sunny today. Do you need any more help?
Please turn on the TV.
Okay.
Beyond the classification issue, we developed a speech synthesis technology that reconstructs imagined speech using brain signals. We adjusted our BCI technology with current sentence-level speech synthesis technology based on feed-forward transformer network. Our model could reconstruct spoken speech using the EEG of spoken and silent speech. These are the audio of original and reconstructed speech.
저는 사촌들하고 아주 가깝게 지내요. 저는 사촌들하고 아주 가깝게 지내요. 저는 사촌들하고 아주 가깝게 지내요.
We are also working on adjusting our BTS technology on brain signals of imagined speech. Speech synthesis with spoken brain signal have shown possibility of successful BTS system. However, previous works are limited on invasive brain signals of spoken or listened speech. As I mentioned before, the imagined speech does not have proper speech audio and onset for the ground truth. By using the similar aspects between the imagined speech and the spoken speech, we are investigating the issues of imagined speech-based BTS system. This is the demo video of our brain-to-speech synthesis technology.
여기에서 가까운 곳에 서점이 있나요? 가까운 시일 내에 한번 댁으로 찾아가겠습니다. 범인은 20대 중반에서 후반의 남성으로 보입니다. 모든 게 궁금해. 여기에서 가까운 곳에 서점이 있나요? 거기서 가까운 곳에 서점이 있어요. 범인은 20대 중반에서 후반의 남성으로 보입니다. 범인을 50대 중반에서 꿀판을 단서도 보입니다.
In conclusion, we found the potential of imagined speech as a powerful paradigm for intuitive BCI communication, and the decoding performance could be improved using the relevant features. Also, brain-to-speech synthesis is a challenging and significant issue for intuitive BCI communication. For the future research, we are planning to improve the decoding performance using the intrinsic features. In addition, we are working on developing the imagined speech-based brain-to-speech technology. BCI technology is approaching closely towards an intuitive system for real-world application. Let's wait and see the development of brain-to-speech technology in the future. This is the end of my talk, and thank you for your attention.
So thank you very much. This was a very nice introduction and keynote talk about speech recognition with brain-computer interfaces. It's really an important topic, and many research like Gerwin Schalk and Dean Krosienski are doing that. And also one of the BCI award winners had this as a topic. There was also one question coming in. Is it possible to see the tinnitus activity with non-invasive methods? So this is a little bit tricky because the activity is normally very focused on a specific brain area. That's the reason why people are using mostly ECOG for that. But if you have a high resolution EEG, then it's at least possible to give it a try to find the tinnitus in the auditory centers. So if there's another question, please use the Q&A tab in Zoom. And you can also post it if you like into the chat, but better is to use the questions and answers tab because then they stay there and we can just systematically answer it. And our next speaker is Junichi Oshiba. I can already see him and he's waving. Nice to see you again, Junichi. I can also hear you. And you can press on the share screen button in Zoom to share your presentation. So Junichi is from Keio University in Japan. He works there for many, many years. So I met him first at the Society for Neuroscience meeting in the US. And we did at the exhibition a lot of brain-computer interface experiments. And he was just very good from the beginning on. This is what I remember, but this is 20 years ago. And the last time I met him, we did a stroke brain-computer interface rehabilitation workshop in Asilomar at the Brain-Computer Interface Conference. And this is also the topic that he's doing now for more than 10 years. So he's an expert for neurorehabilitation with BCIs for shoulder and finger motor functions. And I'm looking forward to hear your presentation, Junichi.
Okay, thank you very much. Thank you very much for introduction, Christoph. And thank you very much for the organizing and attendees for giving me such an honorable opportunity. I'm from Keio University in Japan and also from a university-based startup named Connect, which is for R&D company of a commercial medical device of a brain-computer interface for neurological disease. In this talk, I'll introduce EEG-based BCI, brain-computer interface for neural rehabilitation that detects sensory motor signal over the scalp and the link to the robotic action of the supporting paratic finger movement suffering from the post-stroke hemiplegia. This link and the brain and the robotic link creates a feedback through action observation of a somatic sensation. Even actual muscle contraction or finger movements is not seen and might promote functional unmasking of rest of the cortical muscular neural fibers, avoiding from the stroke or injury. So this is the prototype of our brain-computer interface rehabilitative device. So these headsets detected the motor signal from EEG and actuates a motor-driven orthophase. And the feedback through the action observation of a somatic sensation will promote the remodeling of a neural circuit in the post-stroke brain. So such exogenous manipulation of a cortical plasticity really attract us as a novel concept of therapeutics for people who are suffering with neurological disease and damage. And I'm really happy to share our recent experience with you today. So first, I will introduce some scientific evidences showing that non-invasive recording of EEG represents proper cortical signal. One EEG feature called sensory motor rhythm, or abbreviated as SMR, or even we could say sometimes a mu rhythm, is a widely used feature in the context of a BCI-based neural rehabilitation. So I'm going to share some evidences of this signal origin. Miller and his colleagues used ECOG, that is an invasive way of a cortical electrical signal recording technique, found a very important feature of the sensory motor rhythm, SMR, and its response to the motor imagery. They reported the low frequency band, LFB, in the 8 to 13.2 Hertz is decreased in the actual hand movements or even in the motor imagery. And the hotspot of this event-related desynchronization or abbreviated as ERD, is consistent with the hotspot of the hand motor area identified by the electrical cortical stimulation. Somatotopy of this event-related SMR-ERD is very clear and compatible with traditionally known motor map like this. Hand area was medially located to the tongue area, for example. Noted here that they also reported that the signal increase in the higher frequency band is also seen, but it might be neglected in my talk since the analog of this higher frequency power increase cannot be detected by EEG. So I only focus on the power decrease in the lower frequency band in my talk. So Miller and the colleague also reported that SMR-ERD was augmented by BCI-based neurofeedback. This panel is the SMR-ERD observed during the actual tongue movement, and the middle panel is that observed during the motor imagery. It's diminished, but the feedback again augmented this signal in the real time. So we could say that from this evidence that the neurofeedback of SMR-ERD is a great potential for potentiating a weakened sensory motor cortex by stroke. So our laboratory has tested a similar SMR-ERD neurofeedback, but we've used non-invasive EEG recording, not the electrocardiogram. As tested, we also confirmed that the similar SMR-ERD and its ERD from the electrode placed over the sensory motor cortex. The time frequency analysis showing the bottom left clearly shows that the SMR-ERD is observed in a frequency-specific and a task-specific manner. And the source localization technique supports this response is derived from the sensory motor cortex. So we could say that the EEG SMR-ERD might be an analog of electrocardiogram-based SMR-ERD. We further tested the physiological relevance of this phenomena using TMS technique. We applied a TMS pulse over the primary motor cortex to see how much extent the cortical muscular fiber excitability is associated with the EEG SMR-ERD during motor imagery. The participants in this experiment is a healthy individual, and they are asked to repeat motor imagery of wrist extension. The TMS was delivered to the contralateral primary motor cortex, and the result shows the targeted muscle-specific neuromodulatory effect. The top two panel is the result evoked potential evoked by the single pulse TMS, showing that the corticospinal tract excitability. As event-related desynchronization increased during the motor imagery, the evoked potential is increased in the agonist muscle, but not in the antagonist muscle. So it's a target muscle specific potentiation was seen. The double pulse TMS could be used to assess the intracortical inhibitory effect. It's a GABAergic effect. And we see that the disinhibition of the intracortical inhibitory effect was seen as the ERD is increased, but no change was seen in the antagonist muscle. The quantitative analysis data was this. The left panel is the result of the single pulse TMS. The corticospinal tract excitability is increased in the agonist muscle. And we also tested in the wrist flexion task, and if flexor muscle, only flexor muscle excitability is increased. So it's a targeted muscle specific amplification of the corticospinal tract excitability was seen. The double pulse TMS shows this inhibition of intracortical inhibition was seen in the agonist cortical muscular fibers like this. So through this electrophysics assessment, we could say that the EEG SMR-ERD is a good marker of sensory motor cortex excitability. So next, I'm going to show you how the BCI-based neurofeedback could be effective for people who are suffering with post-stroke hemiplegia. We place the electrode over the ipsilegional sensory motor cortex. We could see SMR during the resting state and diminished event-related desynchronization, ERD, during the hand motor attempting of the paralyzed hand. But it's not often seen. In many cases, there's oscillation, SMR, but no ERD was seen in these cases. So we judged this phenomenon as a failure of activated the ipsilegional sensory motor cortex. So we monitored this phenomenon using a BCI device, and only robotic action is triggered only in case where the ERD was seen during attempting the paratic finger opening. So in the trial and error manner, the patients learn to generate SMR ERD in the ipsilegional cortex during hand attempting. So what happened in the EEG response? At the very beginning, the EEG was not responsible during motor attempting. This plot shows the EEG status. X-axis is the ERD in the alpha frequency band. Y-axis is the SMR ERD in the beta band. So power decrease should be represented in the left bottom. And the blue data, dot data, is obtained during the resting state, and the red dot, EEG, is obtained in the motor attempting of a paratic hand movement. But the two classes are overlapped at the very beginning. But after repetition of a BMI, only single-day intervention shows that there are discrimination of two EEG status, meaning that the patients could learn to generate SMR ERD during motor attempting. So what's happened if we employed this daily intervention for 2 weeks to 1 month? Actually, the ipsilegional sensory motor cortex is reactivated, even though the BMI is detached in the very natural condition. Exaggerated motor activation in the beginning of our status, the focal sensory motor cortex activity was seen again. So that's the promotion of a functional recovery of from the patients using the BCI. The hand grasping function and the voluntary EMG was also again seen. So we believe that the unmasking of the remaining corticospinal tract avoided from stroke injury could be promoted by such BMI-based neurofeedback. So final topic, I'm going to show you how the advanced the BCI neurofeedback could be promoted. We are recently tried to target the contralesional or SM1 target, meaning that the non-damaged side corticospinal tract will be targeted by the BMI-based neurofeedback to functionally masking of this corticospinal tract. So actually, this is the healthy individual subject experiment. The participants are asked to try to elevate the shoulder movement. Either left side or right side hemispheric SMR ERD is given a feedback on the computer screen. But we have two types. One type, if we target the left hemisphere, the participants look at this computer screen feedback. X-axis is the left hemispheric ERD, and the Y-axis shows the ELS in the right hemisphere. In this condition, the participants learn to generate left ERD and the right ELS. But if we flip the XY coordinate in this feedback contents, the patients patients were asked to control the cursor to move the cursor to the top right, as the same as the previous session. But after the repetition of this neurofeedback, the right side of ELD was augmented, whereas the left side shows the ELS. So the patients were asked the same cursor movement task, but actually the neuromodulation effect was totally different. So actually the targeted neurofeedback promotion could be driven by this feedback. So what's happening if we give this for our stroke patients? Even if the patients have stroke damage in the left hemisphere and the right side hemiplegia, we targeted the right intact hemisphere and promote the BMI feedback. After 7 days of a BMI feedback, the muscle contraction, voluntary muscle contraction was augmented, even the BMI was detached. And the actual functional movement was seen from here to here. So we have so far tested 8 patients and see the functional improvement go beyond the minimally clinical important differences. So such targeted neuromodulatory feedback could be promising for functional recovery from severe chronic motor disturbances. So conclusion, the EEG-based BMI is a promising tool for neurorehabilitation. The further plan, the randomized control trial should be needed to prove the targeted neuromodulation using the BMI-based neurofeedback. And also international collaboration could promote a further larger scale of a clinical trial to pushing forward the BMI technology into the actual clinic. So thank you very much for attention.
So thank you very much for the nice and impressive talk. So you did a lot of work and many publications in the past years. If there are any questions, please post it in the Q&A tab or into the chat. There's one coming in from Gurgen. Is BCI better than any other conventional methods for neurorehabilitation?
Yes. At the present, BCI is the only solution for recovery of the hand-finger movements in the post-stroke hemiplegia. Since Lancet Neurology paper published in 2008 did the meta-analysis, and any types of other traditional interventions, such as robotic assistance, electrical stimulation, or constraint-induced therapy, these interventions shows are 0 of SMD, standard mean difference of outcome, meaning that there is no solution for finger movement recovery. But the BMI meta-analysis paper recently published and should prove that the BCI has a moderate to large clinical effect size for finger recovery. So the answer is yes, BCI is the only solution for functional recovery for finger movement.
Okay, very nice. So I would like to know, did you also work with lower limb treatment or language treatment with the BCI?
Language, yes. I think it would be applicable for language rehabilitation as well, since language or speaking stuff could be the very similar computational mechanism of sensory motor function inside the brain. So maybe in detecting the motor signal and giving the proper feedback could promote the functional recovery in speaking function or even other sensory motor integration function.
And did you work also on swallowing? Because swallowing is very often a problem with stroke patients.
I've never tested it before, but in the moderate or mild disturbances of a swallowing function, the rehabilitation researchers have tested the EMG-based biofeedback for swallowing function. So that they succeeded to improve the swallowing function as well. So maybe BCI could be also effective for severe swallowing dysfunction, I think.
Okay, and there's another question in the Q&A. How much will it be affordable for mass market?
It's a very difficult question. It's a very challenging in a commercial application. Maybe Christoph will have a better answer, but the BCI is a totally novel market, so everyone can't decide to pay the much amount of initial cost for introduction of this device. So maybe the novel or penetration strategy would be needed, I think, personally. For example, SaaS model in the international, the internet application services give the SaaS model for paying the small amount of money by the amount of use of the application. So similar to this, those of the intervention may be proportional to the paying cost, or some kind of these sales strategy could be good to make a commercial market for this novel field, I think.
Okay, so thank you very much for the nice answers and presentation. It was nice to see you again and see you in the Neurobar tonight. And we are moving on to the next speaker, which is Alexei Ostachi from Russia. So let's see if he's already coming online. I see his video. Yeah. You can see he has a real background, not a virtual one. And today he will speak about ECOG studies that he's doing in his lab in Russia. And he studied at Southern California University. So how was that?
That was great. It was a long time ago, though.
And also in Moscow. He is the director of the Cognitive Physio Lab in the university. And I'm looking forward to your presentation. So please just click on the share screen button.
Okay. Yeah.
And I see your presentation is loading. I can already see it. I can hear you very well.
Okay.
Please go ahead with your presentation.
Yeah. Thank you very much. Thank you very much, Christoph, for the introduction. And thank you. Let me scroll to the beginning. Thank you very much for the organizers of this conference of creating really, really gorgeous lineup of speakers. And of course, thank you for not forgetting us, who has supported this conference from its very beginning. And yes, today I'm going to be talking about describing you basically the progress we made over the last 2.5 years within the first Russian ECOG-based BCI project. This project is supported by the mega grant that has been won in 2018 by Mikhail Lebedev. And in response to this grant, High School of Economics has created a Center for Bioelectric Interfaces that is situated now in the center of Moscow. And we are doing this work, and in the parallel, we are doing a lot of accompanying projects, part of which I will tell you about now. Okay. So the basic idea of the project is to create a bidirectional ECOG-based neurointerface, and we had 3 years, and we basically had 3 tasks. The first task would be to create a decoder from the motor cortex, then to learn how to stimulate sensory cortex in order to provide some sort of sensory feedback to the subject. And then in the 3rd year, we were supposed to merge the first and the second goals and to create the bidirectional neurointerface. Okay. So let's see so now we are many. We have collaborators from different places in St. Petersburg and from clinical labs in Moscow, and we're also collaborating with some additional departments from HSC. So total we have now about 22 affiliates, out of them 7 whole PhDs, and we have 2 Doctor of Sciences, and our team is pretty young. many people are younger than 35. Okay, so we established 2 clinical partners because this project cannot be done without them, and because it's very interesting and fruitful to interact with the clinic. So the first one is the Plenary Institute in St. Petersburg, and Mikhail Alexandrov and Nastasia Arkhipova, the doctors there. And the second one, and I would say the main base that we are actively working with now, is that in the Third Medical University in Moscow, and its university clinic led by Vladimir Krylov, and the newly established lab for invasive neurointerfaces that HSC and the Third Medical University fund together, and it's led by Mikhail Sinkin, okay, a neurologist. Okay, so the first goal is kinematics decoding, so it's pretty simple in terms of conceptual setting. So we have ECOG recordings recorded from the ECOG grid implanted over the motor cortex. And we have certain kinematic parameters, let's say finger velocity, and we need to decode it. Okay, so in order to do that, in order to do research in this field, we set up an experimental setup, which comprises the microgrids, comprises the software, which merges together the data from EEG, from ECOG amplifier, from motion capture system, and basically in video stream, and then collect the data, and if needed, streams them to the high performance servers for decoding and for other online or offline analysis. Okay, so we arrange the work so that before we interact with the patient, we first streamline everything using the EMG, electromyographic recordings. On the one hand, it's easy and interesting. It's interesting to and very, very fruitful to actually prepare for the visit to the patient. And on the other hand, the EMG interfaces in itself a very, very promising field. And maybe in let's say in 80% of patients, or even 90% of patients, you don't really need to go into the brain and simulate the brain or decode from the brain. You can stimulate peripheral nerves and you can record from muscles, okay, in order to activate the prosthetics. So here is how our decoder works. See, the movements are smooth and you don't have to do any extra force to do the movement. On the right hand side is a real hand, the motion capture signal, and on the left-hand hand is decoded. We have also some videos on our website where you can play piano with this kind of interface. And we record the data with 64-channel EMG grid, and it's basically 4.5 centimeters squared area. And you can say that, okay, maybe it's not really needed, so many channels are not really needed, but in fact we can obtain up to 10 independent components from this small area, which I think is a very interesting and promising approach to read off muscle activity non-invasively. But anyway, this whole thing within this project is done primarily to prepare for the visit to the patient. And we developed decoders, which I will show you how to perform, but also we focused on not only the decoding itself, but also on developing the decoders which would allow us to interpret the parameters of decoding. Okay, so in order to understand which neuronal populations are harnessed in order to provide the decoding and the kinematic parameter, which neuronal population code these, we started developing these decoders from basic principles, which are the following. Okay, so when we have a grid of electrodes superimposed on the cortical surface, it records populations of neurons, the local field potentials produced by the activity of these populations, and from it's a well-known fact that the activity of these populations maps onto the sensors via a linear model. So in order to get access to a particular population, then we need to apply also a linear unmixing that would extract the activity of this particular source, right? This is one story. This is one known piece. And the other known piece that has already been mentioned, that the motor activity is accompanied by the changes in the rhythmic rhythmic activation patterns of the brain. So in particular, higher frequencies like gamma tend to synchronize, and low frequencies like alpha and beta tend to desynchronize. And what's interesting is that the alpha desynchronization, being the lowest frequency out of these three, tends to occupy a larger area as compared to beta, where beta is a higher frequency and the area is smaller, and the gamma synchronization happens in a very, very tiny spot, which allows us to more specifically localize, for instance, motor cortex related to the finger, find specific finger representation. Okay, so our phenomenological model of the design is the following. So we have a set of populations. These populations somehow act and influence the activity of muscles, which move the hand, the wrist, the fingers. And this very activity of these populations is recorded by the electrodes. The problem is that the electrodes record not only the populations which are important for the finger movement and hand movement for the specific motor task we are interested in, but it also records the activity of other populations, okay? And therefore, the measured data can be represented as a sum of the target activity and some non-target interference activity, which nevertheless leaks into the sensors, of course. So our goal is to find such mapping from X into the kinematics, and also interpret F in order to find the topographies, which would allow us then to localize the sources, and to find the spectral characteristics of temporal activations of these populations that would allow us to fit some sophisticated dynamical models and to understand the functioning of the entire process. Okay, so we attempted it by just creating this compact architecture that basically in the first layer does unmixing, which is a simple linear unmixing. Then we have a bandpass filter. Then we have a bandpass filter, and then we have the extractor of the envelope, and then the samples of the envelope are mixed together with the fully connected layer. Okay, the reason why we selected this kind of architecture, well, first of all, because each branch of this architecture is doing exactly something to counteract the mixing effect, which I just mentioned in the beginning, and also it's isolating the rhythmic activity and then making decisions based on this rhythmic activity, okay, based on the intensity of this rhythmic activity. That means that this kind of architecture is potentially interpretable. So we can, for instance, look at these spatial filtering weights and understand where the signal is coming from. We can look at the bandpass filter properties, or in general frequency domain filter properties, in order to get insights into the dynamical properties of activity of the population. Okay, so in general, if you think about these first two layers, the processing is spatial filtering first, the spatial filter multiplied by your data, and then convolved with some temporal filter. Here it's applied to a chunk of data, therefore convolution is just replaced by a product. Okay, so this architecture works pretty well. We applied it to our data, and we also applied it to the Berlin BCI competition. And as you can see, that our solution performs on par, maybe slightly better, somewhere slightly worse, but it does not, as compared to the winner of this competition, and it does not require any feature engineering. Okay. On the contrary, as I will show later, it allows interpretation of the weights and allows to get insights into the dynamic and spatial properties of the pivotal populations. Okay, so I can show you this example how it works. So this is a patient. She was given this pen just to help her. It doesn't click, but when you see this is the finger she's moving, and the decoding result is here. Now she's doing it without so the pace is repeated, and so yeah. So in order to make this whole thing work, however, we had to do iterative learning meaning that basically what happened is this: when we first recorded the data from this patient and trained the model, and then we applied this model to the basically to in real time to the new chunk of data, it just simply didn't work. And we realized that we had to train the patient to make the patient do the movements consciously. So we were showing to the patient certain profiles she had to follow with her finger movements, and gradually her performance improved. So we recorded one such chunk of data when she was following the certain profile. Then we created a decoder. Then we repeated this same process 3 or 4 times, and then we arrived to the decoding accuracy of about 80%. And you can see that this decoding is without a lag, okay, which is interesting and I think very promising. Okay, so here the black one is the true movements, and the blue one is the decoded trace. Okay, but the main goal is not even to create this decoder, but also to create an interpretable, to create an interpretation of the weights the decoder learned. Okay, so I will not go into the mathematical details here, but I'll just try to give you the intuition behind this whole thing. When in this architecture, the temporal filters, those providing frequency domain selectivity, and the spatial filters are learned, they are both not only trying to align themselves or align with the target source, but also they're trying to tune away or orthogonalize themselves from the interference. So when interpreting the weights, you have to take this into account, and this problem has been addressed in 2014 in a famous paper by Stefan Haufe when he applied it to a simple regression problem. Here we have a different problem. First of all, it's not a simple regression. We are, you see, we multiplying our data on both sides, so it's sort of a quadratic thing. And also we have multiple branches. So when interpreting spatial weights, we have to take into account the temporal context, the frequency domain context, which is provided by the temporal filter, okay? And on the contrary, when interpreting temporal filter weights and looking at seeking power spectral densities of activity of our populations, we have to take into account the specific spatial properties, spatial filter, okay? So we played with all this. We done simulations which show that the developed approach works properly. You see the blue and yellow lines coincide. This is a true pattern that was simulated, and the recovered pattern with yellow. Okay, so and other approaches do not work as accurately. And also then we did Monte Carlo simulations, and we showed that the blue ones, the spatial weights are recovered very nicely, and temporal weights also recovered much better than the competing solution. Okay, so we believe that this approach can be used to uncover the spatial and dynamic properties of the populations pivotal to decoding, which can be applied for instance, eloquent cortex mapping when the patient is involved in a motor task, and we are looking for the brain areas for the cortical regions representing specific fingers, for instance, like it's shown here. So we can see the locations, the topographies recovered. We can see that they agree with somatotopy. So the pinky is above, and the thumb occupies larger area and largely below. And also what's interesting is the temporal profiles. See, while the filters do emphasize higher frequencies, okay, if you look at the pattern of the activity, the spectral pattern of the activity of the pivotal population, you oftentimes get low frequency components like here, and the fact that filter emphasize higher frequency doesn't mean that there is no information in the low frequencies. It just means that there are other populations which are active in these low frequencies, and the filter is just trying to tune itself away from the activity in the low frequency because it's mixed together with non-informative components, and therefore it basically tunes itself away from them. Okay, so and then these models, these blue curves, for instance, can be fitted with some physiological models, which we are now in the process of playing with, together with the approach which was developed by Stephanie Jones in her simulator. Okay, so and also this kind of direct application to the intraoperative passive speech mapping, which we are also developing with our clinical partners. So the idea here is that we record the activity during picture naming task, and then analyze, or either look for these patterns or fit simpler models to determine which activity of which electrodes deviates during the task as compared to the rest period. Okay, and so far we have very good agreement, both in true positive and true negatives, and we are collecting more subjects, more data with our clinical partners now. Okay, so you can see about the poster about this work more, and you can talk about Artur Petrosyan, our PhD student. He can talk more about it. Now I will go to the second task. I will speed up a little bit here. So the second task was about sensory component of the interface in order to substitute the afferent pathway. So we developed a active touch paradigm in which subject has to explore the textures, but he or she didn't see the textures. So here the video, it just shows you the texture, but in fact the subject didn't see them. And every time the subject crossed the line, he or she would receive electrical stimulation of the cortex or of the finger. So we implemented both peripheral stimulation and direct cortical stimulation. Okay, so in order to do that, we first tried to find the cortical region in which we would be able to elicit sensory percept in an index finger, and in this process we discovered one interesting thing, that we played with patients who were implanted with microgrids and with macrogrids, and we found that the patients with microgrids were more likely to, as a result of stimulation, to produce sensory percepts, the orange bars, as compared to the microgrids, where the dominating reaction was motor reaction. Okay, this is interesting. This shows a potential promise of microgrids for eliciting sensory percepts, and also with proper analysis and proper modeling of the brain tissue and physiology of the multi-layered structure may give additional insights into organization of the sensory circuits, okay, in layer-wise organization. Okay, so then we had a patient, so far only a single patient, and unfortunately this patient was to be implanted with only a stripe of electrodes, and it was not a microgrid, and the distance between electrodes was 1 centimeter. So we first did MEG, and we stimulated the index finger, and we localized with and analyzed the magnetoencephalographic data and localized the sensory cortex, which is where the index finger is represented. Then we did MEG informed implantation. The doctors did this implantation. So we were pretty accurate because stimulation of between the third and the fourth electrodes, as we determined, was causing sensory percepts in the index finger. Okay, and then we compared with this patient, we did peripheral stimulation. So basically just directly the finger when he was moving, when he was exploring the texture. And we did cortical stimulation. So we had a technical problem with this third texture. We discovered it, already after we done it. So with cortical stimulation, we get about 67% of accuracy in this binary classification task where the subject has to decide which texture is denser, okay? And in peripheral stimulation, we got about 80% of accuracy. So the reason why this accuracy is not that high can be due to the fact that the grid is not microgrid, and also we encountered habituation in a way that as the session progressed, we had to increase the current, the stimulating current, a little bit, step by step. And after crossing some threshold, the subject started to feel started to generate motor reactions in addition to sensory percepts. So that all kind of confused the subject, and therefore this is the first experiment of this of ours with this cortical stimulation, and we're hoping to get another subject to also continue that work. Okay, you can see the poster by Maria Volodina, our research scientist, which describes exactly this in the poster session. And also, well, the third task is to implement the bidirectional ECOG interface. Here we implemented a virtual reality scenario. We developed our own stimulators that can be controlled through the computer, and it can deliver not only stimulation between two selected pins, but it can also deliver distributed in time and space stimulation at a fast pace. Okay, and now we have streamlined it with EMG, but we are waiting for the patient, and because of the COVID, we haven't had a patient for half a year. So here is the scenario. I just show you the scenario. For instance, a successful attempt would be to collect this fragile Christmas balls. So basically the subject controls the grasp, and then if when he or she touches the ball, he gets feedback, only sensory feedback, because as you can see, the index finger is not seen, is hidden. Then he has to stop pressing and do the action. At the same time, when you are pressing too much, like here, the ball drops. Okay, so this is the task that our subject has to fulfill, and we hope to be able to do it by the end of the year, but it all depends on the availability of the patient. Okay, so we are also developing, as I already mentioned, immediate clinical applications. One of them, as already mentioned, the speech mapping, passive speech mapping. The other one is lower limb controlled exoskeleton for the neuro rehab purposes. Here is the exoathlete. He is a paraplegic. He's leaning against crutches, generating severe muscle artifacts, which we are coping with, which our interface is coping with. And the interface is basically, the subject is asked either to stop, either to stay still, or to do the movement, because we wanted to test both the specificity and sensitivity. And it seems to work pretty nicely. We get about 70-75% of ROC, area under ROC curve in patients. We had already three true paraplegic patients we played with. And we are developing this technology with Exoathlete company. And we hope now to get some additional funds to proceed with this topic. Okay. So also, I would like to draw your attention to other research that is going in our center. We are improving the motor BCI using the EEG inverse problem solution, and we get very promising results. We're also active in the field of analysis of MEG, magnetoencephalographic data, for decoding the coupling, for trying to localize coupled sources in the brain and develop statistical tools for that. We have also done some significant work on neurofeedback, and we are exploring what low latency neurofeedback gives us. So far, we see that it improves the learning, it speeds it up, and makes the sustained effect stronger. Then also Masha Volodina had this very nice study where we really saw that EEG is informative about the way people meditate, and especially those which are experienced ones. We can see that there's delineation between two different groups of experienced meditators, but she will have a talk, so you can listen to the talk. Also, there is more fundamental work on perception of time when you're listening to the musical pieces, and familiar and unfamiliar musical pieces. And also this novel work with order-based brain-computer interface developed by Ivan Ninenko together with Mikhail Lebedev. Another work that is maybe not presented here, but it will be shown in other posters that you can see in the conference. So, so I'd like to conclude now that the working on the task of building decoders of ECOG into motor ECG data into motor activity, we can not only do this decoding, but we can also, with proper interpretation of the weights of the proper architectures, we can actually extract knowledge about the neurophysiology of the motor control. Okay, and this can be done with compact convolutional neural networks that we one of the solutions I've just showed to you. Okay, we applied this technology to motor speech mapping and motor cortex map, to passive speech mapping and motor cortex mapping. When you're doing stimulation via microgrids, we found that microgrids are more likely to generate sensory percepts, which is a potential insight, and also recent works, not by us, but by other groups, show that these microgrids can actually be used to navigate the places where to implant the probes for the stimulation and for decoding in patients, in paraplegic, quadriplegic patients. Okay, when implemented cortical active touch, we obtained about 67% of texture classification accuracy. The problem could be the low accuracy, this relatively low accuracy could be due to the use of macrogrid that happened due to medical reasons in that particular patient. And what I'm particularly excited is that, well, while it's quite clear that ECOG interfaces themselves cannot be used for the real control of the prosthetic devices, just because, you know, these ECOG grids are not designed for that. Okay, so but the ECOG grids record activity not of single neurons, but activity of large populations of neurons and local field potential, basically. And when such electrodes, biocompatible electrodes having the same properties, recording the same type of data, are developed, the technology that we develop in analyzing the data can be applied to then to transfer these technologies into real motor control and by myoelectric control, you know, the prosthetic control. So, and as I mentioned, we're also developing non-invasive BCI solutions for neuro rehab purposes. Okay, so basically that's it. I have a just a slide that we have like so many conference talks, so many publications in Q1, Q2, two chapters, new grants and stipends. This is our center, the entire center gets. We have a weekly seminar and journal club. And actually we'll be very, very happy if some of you would join us during the weekly seminar where we host talks by reputable scientists. And the next one is actually Stephanie Jones, who is going to be talking in the end of the month to us. And yeah, so, and then I would like to thank all of you and say that one more thing, that we have already also won a Mirror Lab grant with our center and Samara University. And we are working in the topic of neuro rehab and applying our real-time inverse solutions for this task. And we are now in a very nice premises, only 1.5 kilometers from Kremlin, and 256 square meters of lab space and office space. And we are part of the big Institute for Cognitive Neuroscience, the HSC. All right, so basically, thank you, Samara. Thank you, World Wide Web. Yeah, I'm anxious to hear your questions, if any. Thank you.
So this was very nice work that you're doing. There are a couple of questions in the Q&A, so you can also open it.
Okay, yes.
I guess, and Alexander, I cannot read it, is asking, is there any further plans for experiments with arm prosthetic patients? Feedback prostheses are already existing, as I know.
Sorry, can you repeat the question, or maybe I can read it?
He's asking if you have any plans for experiments with arm and prosthetic patients.
With ECO, well, okay, so our plans are actually continue developing this bidirectional story, right? So trying to achieve as much as possible when we stimulate the cortex through those microgrids, okay? And maybe some sophisticated models for stimulation, or maybe some associative learning can be used to make the stimulation produce more natural percepts in subjects. Experimenting with actual hands, I mean, it's possible, but we replace it with with avatars and with virtual things, because we are developing primarily the mathematical technology for that. So we are fine, but we would be interested if somebody could offer us a hand. We would be interested in setting up an experiment where we can control actual hand. Yes.
Valerie is asking if there's a possibility to do an internship with you.
Oh yes, absolutely. Everybody knows me. Everybody knows Mikhail Lebedev. And so again, HSC is Institute for Cognitive Neuroscience. If you just type and look for Center for Bioelectric Interfaces, there are emails, there are contacts. Please do send me an email. And of course, we can accommodate a student. And actually, I'm getting quite a bit of requests now we have some interview, and then we arrange, if we are both happy, then we arrange for a project and people do it. Yeah.
And he pays you a lot of money if you are doing an internship.
No, we are not. No, we are not like money. We hope to get actually. We submitted the prolongation request for this grant to the government, to the funding agency, and we are waiting for the result. We will know it in November. So they are kind of suspense state, but you know.
So Valerie asked him to pay a lot of money for the
internship. Okay. Well, if you are not funded, then he will have to.
And Vlad is asking, how can you raise up the accuracy? Is it possible to use, for example, nanotubes for each neuron?
See, the problem is here is that, the reason I mentioned in conclusions that I hope that what we are doing, trying to develop technology for decoding ECOG signals, is going to be useful in the future when the electrodes are not electrodes that are reading activity of single neurons, but rather, populations. So we are not working with single neurons, okay? When you have access to single neurons, like Mikhail Lebedev was doing in monkey, like other groups are doing with Utah array probes, right? When they really have intercortical probes, then the decoding task seems to be easier. The problem is that these electrodes are very damaging, and even the electrodes developed by Elon Musk now, those threads, right? They have problems they will soon encapsulate, and they will the decoding quality, the recording quality will decrease. Although there are methods which are coping with it, and Lee Miller was talking about these methods last Samara meeting. So we are primarily focused on macro recordings, and actually we are thinking of moving these grids not towards the neurons, but further away from the neurons onto the dura mater, so that we can implant the patient without opening dura mater to make the whole thing even more non-invasive. Yeah. So.
And the next question from Artyom is: can you use ECOG for rehabilitation of spinal cord injury?
Again. We had some contact with Pavel Musienko, who is a professor in St. Petersburg State, and who is doing this work, trying to create a device that would replace the broken spine circuits. Okay, and we had some idea with him about controlling this device through the brain-computer interface. The proper answer about ECOG, I don't know. Probably no, because you're not most likely going to have this patient implanted for a long time with ECOG. And if you implant ECOG grid, very often the ECOG grid floats. Although there are some examples when people implant it and people live with 3 months with this kind of grid and have P300 interface implemented. But implanting this grid into the brain and then using information from this grid to control, for instance, the movement center, right, in the in the spine. It's theoretically possible, but I don't think it's practical. I think more practical solution could be to use the electrodes that read activity of the depth structures, those which are implanted for DBS, for deep brain stimulation purposes. And there is work showing that you can decode the STN activity and you can predict the movement based on the STN activity. And then, because these electrodes are designed for chronic implantation, you can use it in patients to control the devices that replace the part of the spine that is, lost its conductivity. Yeah,
So this was very nice and impressive, and Alex has also a very nice publication recently in Brain with Michel Lebedev. So make sure to work with him. I'm sure you get nice publications.
Thank you very much. Yeah, thank you very much.
Thank you very much.
Yeah.
And we are moving to the next speaker, which is Sergei Shishkin. He's also a famous researcher doing a lot of MEG studies. So Sergei, I can already see you. Very good. Please unmute your microphone. So Sergei has a very nice background, as you can see. So he is from the Moscow State University, director of a BCI and neuroergonomics lab, which is very nice, and doing a lot of studies for many, many years with BCI. So I meet him all the time at different conferences because he's talking everywhere. And Sergei, please click on the share screen button so that your presentation is loading. And today he will show us his work about consciousness, set limits to brain-computer interfaces. So please go ahead.
Do you see my presentation?
I see your presentation. I can see the video and I hear you very well.
Okay. Thank you, Google. Thank you, Christoph. And I would like to thank all organizers for this nice conference. Yes, I'm now with Moscow State University of Psychology and Education, but until recently we were at Kurchatov Institute, so the lab, some people of the lab moved just some months ago. My talk will be with this very strange maybe title, and not much related to our current work. But I think we sometimes need to discuss such strange topics because they have a lot of relevance to planning of our research and to thinking about future. So, okay. Yes. So, what were just a few words what our group is doing. We work with fully non-invasive brain-computer interfaces, and we try to make the most powerful possible non-invasive interface by combining gaze and EEG and also MEG. And this is why we moved to MEG center of this university. But we actually didn't make many studies. We have no published journal papers so far on MEG, and tomorrow will be a talk by Anastasia Ovchinnikova. We just prepared a paper and is going to submit it in a few days about our first paper about MEG. But what I will talk in the rest of the this presentation will be related to the problem of connecting brain and machines from very broad perspective, not just not only helping paralyzed people or people with other disabilities, but also augmenting brain function and putting it to most possible highest level. So the idea is very basic and discussed for many years, for decades already, that we have a very powerful brain and more powerful computers, and they could complement each other. But unfortunately, the pathways are very weak. And the pathways between brain and computers are just the main obstacles for the effective collaborative work. And the very obvious idea is why cannot we make BCIs, which would be not just supplement, not just will replace or restore motor function, but perceptual function or speaking ability, but also make some much more powerful symbiosis. So, and it may sound just some fantastics, but it's already quite more and more widely discussed in popular media. Even here you see title in Forbes about merging of human and machine. And Elon Musk, probably it's his main motivation of his work is also making such symbiosis, and he directly mentioned that he's interested in such a thing. And even in scientific papers, it's sometimes already being discussed. So there was a very large and very interesting review last year in frontiers in neuroscience, and there is also the direct mentioning of merging the human brains and with computers. But what is common to most of such such discussions is that the problem is discussed only as an engineering problem. So we need to get some very powerful reading technology and uploading to the brain technology to decode the signals, or it's also often expected that the brain, because it's huge ability to adapt, huge plasticity, could get into contact with this technology and make best of it for after some time of adaptation. But actually they can be also not only technology level, technical limitation, which probably will be really possible to solve, to overcome, but also some higher level problems and limitations. So I will discuss, so actually my talk will be about two main limitations, about input and output limitations. And I will give only one example for each case. I think it's possible to find quite much more examples, but it will be maybe more clear if I will not go into many details, but just consider some clear cases. So for the input, yes, we can expect that the input problems are just a limitation of our perceptual systems, our sensory systems. And if we will connect to machine not just by usual vision system, but will be able to get information in other way, probably it could be much faster, faster connection. We'll have much faster connection. But there was a very nice paper also last year about comprehension of languages. And the authors in Science Advances, the authors studied 17 different languages from different families. Here are different language families. So they were really different. And we can expect that different languages are involved in such a way that sometimes they are very effective, sometimes less effective, and so they can have different information transfer rate. And then, in fact, there will consider information transfer rate, or not exactly, the information per syllable in a language. They are here for different languages. We see that it's really vary from about 4 to 8 syllables. Oh, sorry, here it's syllables per second. So it's, we can measure number of syllables per second, like here, and also amount of information per syllable. But here, the authors compared what is most important in our perspective, the information transfer rate, and it is appeared almost the same for all languages, about 40 bits per second, like here. And they made inference. I'm not sure if it's maybe not in this paper, maybe it was in some interview, that it may be indicative of that we have no, the main limitation is not perceptual, but it's at a cognitive level. So we have we cannot think too fast, and this is why we cannot listen to too fast speech, and this is why speakers adopt to this comprehension speed, and this typical speed of typical information transfer rate is so stable. Of course, it can be debated and it can be criticized that it's has such a very general application. These results have general application as I suggest, but I think it's at least very good demonstration of such limited abilities. Okay, now we'll go. Yes. Now let's go to output. And here I would like to suggest an example which is not from scientific literature, but it's quite interesting kind of experiment which is now is going on with with the smart home speakers like Amazon Echo. So the system which is you can have at your home, and many people already have it, and it's sensitive to your voice, and it can understand what you are talking, and it's working as such a smart conversational agent, and also can follow your commands. If you ask to do something, it can make some simple things. And there has been some quite strange, unexpected, and sometimes funny incidents with the systems, because it has been already installed in many homes. And one, maybe most famous of them, was when the system recorded a family conversation and sent in a random person in the contact list. And it was an employee of a husband. How it happened? When Amazon experts investigated the case, they found that the device understood something in the stock as call to it, and it was activated, and it understood that the conversation from other words should be recorded and sent. But after this, it asked several times, as they claim, asked several times to the family if it really should be done. So some precautions was really implement the system, and they follow it. They were used, and they confirmed that it understands as confirmation some words from their conversation. But they say that they haven't tell it such words. Anyway, it happened. So here we see that there are some errors can be quite possible in such a human-computer interaction, and probably inevitable, at least at a for very long time. And sometimes the errors can lead to dangerous consequences. Here it was not so dangerous, but we can imagine something more worse. And I think that this is a very clear case which shows how important to have conscious control over what is going on in the system. And according to this limitation with the input, we also will need to have sufficient time to understand what is going on. So if something going on without our conscious access, then we may miss the errors, and something may happen which we would not like to happen. Also, somebody can argue that we can have improvement of brain function, some augmentation of brain function, without just putting something as input or output, but in some maybe more direct way, like there are attempts to improve memory with using hippocampus implants. But here we also can apply the same logic. So something may happen out of our control, and something sometimes they can be errors. So it's sometimes serious errors. So in normal life, we have, of course, we understand we have the unconscious processes, and they are very important to our functions. But probably they are evolved in evolution of animals and humans, and also they are developing in many years of human individual development. And when we kept a machine connected, it was not going on through so long time of adapting to the brain, and brain probably will not have enough time to deal with all possible errors. So okay, so now I will just want to mention that why I'm speaking about consciousness here. This is not probably necessary, but first thing I wanted to mention is that from philosophical point of view, it's a very interesting area. And I wanted to present here some logics which should be applied from philosophical point of view, but just in the last moment I understood that I'm not too strong in philosophy and probably can be not very clear or even make some errors, consciously or unconsciously. So I just will mention that it's probably very good for philosophers to discuss such issues, and it will be also helpful for the development of BCI technology. But also what it means for scientists and engineers, why we should care. I think that it's still impossible to consider that it's a conscious process, not just something in the system, some technical sense. For two reasons. One is because when I was just discussing input and output problems, it was important that all time that it's we need to understand consciously and to control consciously. So it can be understood in terms of awareness, but awareness in many cases is almost the same as consciousness. So it's necessary for error monitoring, at least. And also it's important because prospective users and general lay public may worry about the technology from their own perspective. And their own perspective is perspective of their own consciousness, not about some systems, but everybody is concerned about his own consciousness, how he looks around and what he can actually see, and if he or she can control consciousness. And I would like to emphasize that it's for a user, it's not just some system or some user's brain is important, but his or her conscious mind. And probably we often should speak not only about brain computer or brain-machine interaction, but about mind-machine interaction. It will be more clear and more useful for understanding of such problems. Probably more studies of mind in such mind-machine interactions should be should be necessary. And I will just mention very briefly studies which we are doing in our group. It's just in progress, most of them, but one paper I hope will soon appear. So we have one of our guys is Ignat Dubinins. He's very, not only he's a psychophysiologist, but also a very talented engineer, and he designs various devices for experimental studies of human-machine interaction or mind-machine interaction. And he is a kind of model of exoskeleton, which helps in a reaction time task. And typically, in human-machine interaction, we consider either active movement or passive movement. Passive movement is made by machine only. But with exoskeleton technologies, there is often some mixture of agency, or agency means that who actually initiate who controls the movement, and there is a feeling of agency, and feeling of agency in exoskeletons is not very much studied. And he proposed, Ignat Dubin proposed that we should define as he calls active passive movements. So they are, for example, when a person initiate the movement and the exoskeleton completed, or they together try to complete it. And so I'll not go into details, but the resulting sense of agency appeared to behave in some sense tricky and not as we expected in this experiments. And another prospects for near future is also to use widely or to develop more neuroadaptive technologies, because they don't have this problem of conscious control. You only maybe need to concern about privacy, but generally there will be no problems if this technology understands something is incorrectly, because it's just adaptation of a machine. So it doesn't have such, will not have any serious terrible consequences. Of course, you should also use it carefully. And also there is a new journal, for instance, in neuroergonomics, and now is open topic for real-time modeling based on passive brain-computer interfacing. It's initiated by Torsten Sander, who was giving a plenary talk last year at this conference, and I'm happy he invited me also to co-edit it. So you can submit your research on passive interfaces and neuroadaptive modeling to this topic. You are very welcome. And I would like to mention our new group. It's all people who also worked together in Kurchatov Institute before, and also people who are some still in the Kurchatov Institute, and our graduates. We also collaborate with them, and also I would like to thank all these people and collaborators. And members of laboratory and Russian Science Foundation, which generously supports our research. And thank you for your attention.
So thank you very much, Sergei. This was very nice, and we have already many questions in the Q&A tab. So if you click on Q&A in Zoom, then you can already see it. Vlad, for example, is saying we can talk at speed of 40 bytes per second, but read more faster. If we have limits of absorption information, how it will impact a possible BCI?
Yes, of course, we read faster, but I'm not aware of exact measuring the information, but what I suspect is that we simply filter the information at a relatively low level here, and we also have a limit for reading. If we study some techniques for fast reading, it will help just make some low-level filtering. And we try to, in this case, we focus on the main part of information. And my own feeling, it's not maybe not very well grounded in some evidence, but my personal impression is that the speed of information consuming will be almost the same in reading and in listening. Yes, and what was the question?
From Vlad, what do you mean by the term consciousness?
Oh, okay. Yes, it's a difficult question because there are too many definitions of consciousness, but I personally, and I personally also cannot answer a very simple way, but okay, for me personally, it is consciousness is first of all the subjective experience, and this is in philosophy it's called phenomenal consciousness, and it's often separated from some different forms of consciousness. And I personally believe that there is only phenomenal consciousness, and other things are just some discussion of different properties. But in the context of this talk, I just meant what I meant. I was talking about awareness. I was talking about personal perspective. Actually, it was about subjective experience. If you want to study it more, I think we have to talk about what processes are in neural system are related to consciousness. I think there's the same, something which shouldn't be with the same information content like in phenomenological consciousness, but okay, it will be details. Okay, neuroadaptive technologies.
Yeah, Alexander is asking, what do you mean with neuroadaptive technologies?
Yes, sorry for not providing a definition. So neuroadaptive technologies means that we have in human-machine system, we try to adapt a machine, its state or its way of working as a to human brain state in such a way that we don't distribute the user. So the user just, you have, for example, EEG or some other signals from your brain monitored by the system, but the system reacts, just reacts to it, and you don't need to care. So it's very good in the sense that you do what you are doing exactly, but you just are adding a new channel. For this channel can be not maybe very fast and with high information transfer rate, but still will be useful.
Then Jacobo is asking, how do you think that conscious processes can be distinguished from unconscious background noise using EEG?
Yes, I don't think they can be very much distinguished. Typically, okay, here we probably need to go into details because for different technology, we can see different things. So for example, neuroadaptive technology can just adapt to your level of activity or a tiredness. If you are tired, you will probably will not mention, and it's not necessary to be conscious about it. But the system will work in such a way that help you to in this your state. And in sense of okay, I probably need to go to look the rest of the questions. Okay, so in the D5, there are many. So maybe I will try to.
Tomek, for example, is also saying
yes.
congratulations to your promotion. So promotion is always good. Well done.
Thanks, Tomek.
And he's asking, how would you comment on the relationship of slower reaction times in older adults due to brain atrophy?
Actually, I don't know. So it's it could be related to different things, both to this and to perceptual level. So I am unfortunately I don't have no good knowledge of this area.
And Olga is asking, do you think that there's a hormonal influence on BCIs?
Of course, they could be, but they can influence all physiology. So the physiology would influence BCI functioning. So yes, sure. Yes, maybe I will try if I have some little time to the rest of the question of Jacopo Arujo. So about sufficient technology of focus of consciousness, probably, as I understand.
So a second part of Jacobi's, and do you believe EEG could be sufficient technology to identify and track point of focus?
Yes, but it's, of course with some limitations. Yes, it's not EEG is not very powerful technology, but maybe we will with machine learning we can still improve, but we can do it.
Okay, Sergi, thank you very much. This was very interesting, very nice presentation, a lot of questions, and we are supposed to drink some coffee now, or maybe tea, and we are breaking for 15 minutes. So we see us again at 10:40 in 15 minutes, and then we have the next keynote speaker.
Thank you, Christoph. And we have some break.
В данный момент перерыв. Спасибо большое всем участникам. Мы пока ушли на 15 минут. С нами все-таки пока что остается. Мы покажем ролики, которые напомнят нам о предыдущих конференциях.
Decide to remain with us. We will show you the videos on our past conferences.
Самое главное – это коммуникативная площадка. Площадка для общения ученых со всего мира, потому что вот именно во время общения возникают какие-то новые идеи. Эта конференция сейчас в стране, она ведущая по этой теме, что тоже важно для Самарского государственного медицинского университета и в целом региона и практического здравоохранения.
Это одна из топовых конференций, можно сказать, в мире. Мы имеем топовых лекторов прямо в одном городе. Пожалуйста, наши коллеги могут приезжать в Самару, а не разъезжаться по всем странам мира, по конференциям и ловить этих лекторов где-то как-то.
Это продукт Reviver, уже достаточно известный, который мы ставим в медицинские учреждения, посвященный реабилитации больных после инсульта, и продукт Remotion, в первую очередь для реабилитации больных ДЦП.
Хотим напомнить, что помимо Фейсбука и Ютуба у нас идет трансляция Zoom.
Apart from
И вы
YouTube, you can also join our Zoom broadcast. So you can join our Zoom conference after you register
BCISamara.com.
at the BCI Samara.com website. Following the registration, you'll have access to other events.
Открытые лекции, постерная сессия. Нет, открытые лекции у нас и так доступны. Вам будет доступен нейробар. Алексей, давай расскажем, что такое нейробар.
Let's tell everybody about the Neurobar, Alexei. This is a really interesting event. I think it's only the second time that we're organizing it. Yeah. Thank you very much, Julia. Neurobar will give you a wonderful opportunity to rub the shoulders, so to speak, with our speakers. So you'll be able to join our virtual Neurobar in Zoom. Basically, it'll be the Neurobar will give you an opportunity to have a virtual hangout with everybody who registered for the conference. Apart from this, you'll be able to participate in all of our sessions. You can submit questions using Zoom interface. We actually received a lot of questions already. We answered these questions. And let me remind you that the first conference was organized back in 2015. That was the BCI conference. After 2015, the conference had grown. It had a lot of satellite events, neurothlon, open lectures, workshops. So this year, the conference transformed into a Neuro Week. So we have a lot of events scheduled for this week. Tomorrow we're going to have two conferences running at the same time. One is BCI. The second is Neuroscience for Cognitive Health and Longevity. I would like to say that when we mentioned that you can submit questions, so please do not submit your questions to chat, but do use the Q&A function in Zoom. And what is the chat about? Well, that's not about submitting the questions. What else we're going to have this week? We're going to have a Neuro Symposium. And during the Neuro Symposium, we're going to talk about different ways to apply BCI, from processing scenarios to practical implications that already exist or hold a lot of promise for the future. We are going to have a lot of workshops for our participants, for medical students. We're going to have a workshop on TMS. We're going to have a workshop on communication. We will have an opportunity to discuss the current state of knowledge in neuroscience that maybe still don't have an application, but all of this knowledge is important for the neuroscience. So there will also be an event that is called Monsters Discussing Elon Musk. So we will have an opportunity to discuss all of the undertakings by Elon Musk, and we'll be able to discuss all of the latest advancements in BCI. We're also going to have several hackathon events. We're going to have like, a hackathon is a competition. We are going to talk about different neurotechnologies, different teams will have an opportunity to present their projects. So now, this week, we're going to have the finals. Let's tell a little bit about the hackathon. The hackathon is going to take up the whole day. So basically, the way it's going to look is going to be like this. There'll be several teams. They will be given a task. They'll be hacking using Zoom. And then we will talk to them throughout the day. And then we will broadcast the finals of the hackathon. Well, there'll be also a lot of special sessions. We've planned a lot of interesting events. We are also going to have 2 open lectures. So will be more in the realm of popular science. It will be on Saturday from 4 to 6 p.m. Moscow time. These lectures will be given by the leading scientists. So we'll have a lot of interesting events, but let me just tell you one more time that you can access our program on the bcisamara.com website. You can see the program. Even if you look at the printed version of this program, you see that it has a gazillion of pages, but it is much easier just to log onto our website so that you highlight the events which are the most interesting for you. Apart from the conference itself, we have also organized an Olympiad in neurophysiology. This Olympiad has been organized by the Samara University. So the Olympiad is also held online. This Olympiad is intended for medical students. I think we're also going to have a short broadcast during the kickoff of the Olympiad and also during the finals. Julia also mentioned that there'll be an opportunity to see a video. Yes, you will be able to see not actually a video, but a movie, because we've partnered with Popular Science Movie Foundation. So this is an event that is also organized online. So on the 10th and the 11th of October, we're going to show you 6 science documentaries. They'll be completely different documentaries. Also, you can log in to the festival website, so you can select what it is that you want to watch. Again, all of the links can be found on the bcisamara.com. Yeah. We are also going to have a virtual exhibition, the virtual exhibition or the virtual expo. We'll talk about it a little bit more, but we're going to have 2 online events. We're going to have a poster session where you can look at different posters, talk to the researchers behind these posters. We're also going to have a virtual expo, and you'll also have an opportunity to talk to people who are exhibiting their achievements. So we're going to have a big break from 2 to 4 p.m. And during this break, we're going to have a couple of interviews with renowned scientists, and you'll also have a chance to look at virtual posters. So do log in. You can go to this little booth, so to speak. So it'll be done on an impromptu basis, but I do hope that we'll be able to talk to the exhibitors and broadcast our interviews. It'll be organized in the same way at the poster session as well. So I think that exhibitors will also be there, so you'll have an opportunity to ask them whatever questions you want. Well, I think that our break is about to be over. And we are going to start the second part of our plenary session. In the second part of our plenary session, we have two speakers. So the second part of the first session, the second part of the first plenary session, we will have two speakers, Vadim Nikulin and Alexander Kaplan. And I would like to give the floor to Christoph Guger. Christoph, are you with us?
Our talk session, and thank you very much for the entertainment in the break. And our next speaker is Vadim Nikulin from the Max Planck Institute in Germany. So Vadim, please start your Zoom again so that I can see and hear you. So he's the head of the Neural Interactions Group at the Max Planck Institute. Max Planck Institute is a famous and huge research organization in Germany, and he is located in Leibniz. So that's also a big part of Max Planck. Just trying to get a hold of Vadim. Maybe I can help him when I enable his microphone and also the video. Let's see where he is. Vadim, please get online. So Vadim is not in the meeting at the moment. Maybe he went to the speaker's room. So he studied also in Finland and also in Russia. And today he will speak about neurophysiological predictors in BCI performance.
Organizer says that we have 2 minutes waiting. He's connecting.
Seems he logged out a few minutes ago and now he's reconnecting again. So you got also this nice background behind you is the iceberg. So Maria raised a hand. Do you have any questions that we could answer in the meantime? Maria, you can use the Q&A tab or also the chat function, and then we can answer your question, or I could also promote you to the speaker room if you want to say something. Just let me know in the chat. So up to now we answered 13 questions. So you can ask us much more. I'm pretty sure today we can do 100 questions.
Hello.
Hello, Vadim?
Yes.
Very nice. I can hear you.
Yeah, so I had some problems with the connection.
Yeah, no problem. We had something to do in the meantime. So please enable your camera if you have one.
Yeah, but the camera is also, there is some, let's see whether the presentation will, okay?
Yeah, please press on the share screen button.
Yeah, just a moment.
And just select your presentation or the whole computer, and then it's already loading.
Can you see me?
Yes, I see your presentation. You can just start it. So that
just a moment.
Gets full screen.
You can probably see me too.
I see you also, and you got also this nice background. I already introduced you, and please go ahead with your presentation.
Yes, and so I'm very thankful to organizers for inviting for this very nice conference. It's the second year I participate here. So I will be talking about neurophysiological predictors of brain-computer interface. So it will be with a little bit more neurophysiological and technical details. So mostly I will be talking about predictors of sensory motor BCI. So specifically I will update you about the role of oscillatory signals, signal-to-noise ratio, and how they can manifest in amplitude modulation, which plays a paramount importance for BCI. Then I will show you how temporal dynamics in neuronal signals and the proximity to so-called critical state benefit tremendously brain-computer interface. And finally, I will show you how the integration of motor and somatosensory information through functional connectivity also actually biases in a good way your performance in BCI. So now I will mostly talk about sensory-motor BCI, as I mentioned, and I will primarily focus on motor imagery. So kinesthetic motor imagery is defined as a mental neuronal simulation of an action without activation of the effectors. So there is a very nice recent meta-review study showing that motor imagery shares a lot of neuronal activations similar to movement execution, including motor areas and even cerebellum. So now activation of these neuronal structures is important for effective modulation of sensory motor oscillations, which serve as a main source of a control signal. So now, of course, sensory motor BCI is of paramount importance, as we also heard during the previous talks, for rehabilitation in stroke. So now, just to show you briefly the sensory motor features in BCI, this is a classic example of imagining, for instance, left and right hand. And what you see here when you're imagining left hand, you have activation over the contralateral hemisphere. And this activation is manifested in a massive suppression of sensory motor oscillations. So the same thing happens when you're imagining right hand, you have activation of the left hemisphere. So I will be talking about these signals which serve as a basis for sensory motor BCI. So now just briefly to tell you our main pipeline for Berlin brain-computer interface, which we repeatedly use in our studies. So of course we start with raw data, and then people are doing training with imagining different limb movements, let's say hand movements or leg movements. So then we have heuristics for finding the best frequency range and time interval. And then on the basis of this information, we are having this common spatial pattern analysis, which extracts neuronal components which are best discriminating variants of neuronal signals between different classes. Then you can feed in this information to classifiers, which could be based on SVM. In our case, it's LDA. And then naturally you can apply all of this pipeline to either test data or to online data. So now there have been a paper in 2010 when our researchers showed that the success in performing brain-computer interface depends on the height of sensory motor peak, which you can measure with C3 and C4 Laplace. So now this height of the peak is measured as how much oscillations stand above the 1/f part of the spectrum. And what was shown that the stronger you have this peak, the better is your brain-computer interface. So now I would like to show you neurophysiologically what it means, because the fact that you have strong oscillatory power does not necessarily mean that you will be a good performer. So there should be a neurophysiological explanation for this. So now this is a study which I would like to show you how so-called attenuation of event-related desynchronization of oscillations look like in the same subject when you bin your responses or group your responses on the basis of pre-stimulus sensory motor or alpha oscillations. So what you can see is that if you have very strong sensory motor activity in pre-stimulus interval, then you will have a massive attenuation of oscillations. So this beautiful contrast actually leads to a possibility to have a very effective feature of brain-computer interface. Because if you have trials or if you have subjects with very small pre-stimulus activity, then the noise might be so high that it will be kicking post-stimulus interval amplitudes of oscillations up and down, so the discrimination between classes will not be very strong. So it's actually all about making a contrast between pre-stimulus and post-stimulus activity. Just to show you it even further, so these are 80 subjects, and if you look at the training data, and if you measure SNR the way I just showed you, then you can see that signal-to-noise ratio is correlated, of course, with event-related desynchronization, which you can also see from this figure. The larger you have a peak, the stronger will be the contrast between pre- and post-stimulus intervals. So, of course, we replicate the previous results showing the signal-to-noise ratio predict your brain-computer interface performance. But what is more important, that if you look at the strengths of the prediction, it is even stronger if you measure the strengths of EAD in the training session, which predicts BCI accuracy in a better way. Again, the main result is that the peak, the height of the peak and the spectrum is important, but even more important is the way your amplitude modulation occurs in sensory motor oscillation. So this is the most important part. So now we move to a second part of predictions, and this relates to temporal dynamics of sensory motor oscillations. So now I would like to show you here 10 minutes of amplitude envelope of mu oscillations. So basically, if you look at the way the amplitude of oscillation is changing in time, then you can see that regardless at the time scale at which you look at the activity, it qualitatively looks exactly like what you see at 10 minutes. So if you look at the activity at 10 minutes versus, for instance, 30 seconds or 10 seconds, then you can see that there are bursts within bursts of sensory motor oscillations. So qualitatively, it looks like there is kind of a self-similarity structure. And this self-similarity structure is very typical for complex systems, for general, for any physical complex system. And of course, the brain is another example of a very complex system where the part looks like a whole. So now these systems often refer to the class display so-called critical dynamics. And just to show you what it means for neuronal activity. So imagine that you have neuronal networks and there is a different probability of each neuron to excite any other neuron. So if you look at the upper panel here, if the probability of any neuron to excite any other is very high, then as time goes by, there is a complete saturation of networks. So you can imagine that it's not possible to code information in this case. Another extreme is when you have a very low probability of excitation. And as time goes by, there is a complete termination of activity, also not very useful. But you can imagine that there is an intermediate level of excitation and inhibition where the activity could be present as time goes by. And actually at exactly this state, you have the richest repertoire of neuronal dynamics. In previous studies, both empirical in vitro studies and theoretical, showed that exactly these intermediate metastable states correspond to the largest dynamic range of stimuli, which neuronal networks can process, to the best information transmission and information capacity. So now, we can also measure this critical dynamics non-invasively with EEG, using an idea of long-range temporal correlations, which are typically present in complex systems at a critical state. So in this case, we extract amplitude envelopes of oscillations, and we measure so-called autocorrelation between these envelopes. Well, autocorrelation shows you how the signal is correlated with itself when being shifted by a specific amount of time, tau. So we say that autocorrelation decays slowly according to power law, and that in turn indicates a presence of long-range temporal correlations. So in order to measure this decay, we use the trended fluctuation analysis, which shows you how the variance of the signal is changing depending on the time window at which you measure this variance. So typically, the scaling exponents, which is also called Hertz exponent, is 0.5 for white noise. And if you have it somewhere in the range between 0.5 and 1, then it indicates persistent correlations, which are typical for critical systems. And there are theoretical papers showing that the closer you get with LRTC to the value 1, the closer you get to these critical states. So now what we hypothesized, that neuronal networks in different subjects, which are closer to this critical state, they would be better off for performing brain-computer interface, because in brain-computer interface, neuronal networks need to do a fast switching and then between different neuronal states, and they also have to encode different sensory motor memory states. And as I told you before, exactly these operations are maximized at the critical state. And this is indeed what we showed. So if you have here 90 subjects, where the performance of subject is sorted in an ascending order in such a way that the best performing subjects are on the top here, the long-range temporal correlations, which are also called Hertz exponents, are actually displayed here in color. So the red means stronger correlations. And what you can see here, that if we measure LRTC before online BCI sessions, then the subjects performing brain-computer interface in the best way, they also happen to have strongest long-range temporal correlations approaching value 1. And of course, we carefully control for signal-to-noise ratio in order to make sure that the effects we observed are not due to trivial effects of the amplitude of oscillations. So now, in order to convince you further that criticality might indeed exist in sensory motor networks, we recently did a study where we investigated long-range temporal correlations and criticality, not only in ongoing oscillations, but rather using a probing approach. So what we had here, we would have a median nerve stimulation, for instance, stimulating median nerve 1,000 times with an interstimulus interval of 700 milliseconds. So then what we did, we were able to extract in single trials the amplitude of N20 response, as you can see here. So this is a very beautiful response because it allows you non-invasively to track excitatory postsynaptic potentials on pyramidal cells on the fourth layer. So yes, you can be that specific in time and in space. So now the idea was that we wanted to see how the amplitude of these responses is changing as a function of time, because if it fluctuates in a certain way, that would again demonstrate that we have criticality in our sensory motor networks. And indeed, we did also inverse modeling. We showed that our activity originates from area 3B, from a hand area, so it's all nice. And just to show you that, for instance, this is a specific example from one of the subjects where you see all 1,000 trials. You see this beautifully extracted N20 response in single trials. And if you look at it, how it is manifested in time during the experiment, you see that it fluctuates. And when we do this scaling analysis, again, we detect the scaling exponent around N20 latency, which shows the presence of critical states. So now again, this is another confirmation that criticality might exist, and you can detect it with probing approach. And in turn, as I showed you, it can benefit brain-computer interface. So now I would like to move to the third part, and this is about the importance of integration of information between motor and somatosensory networks. So now what we would like to show in this study is to show that there are benefits when you train your classifiers using both motor imagery and functional electric stimulation. So what we did in this study, we had one training session where we would have motor imagery alone, where we would have functional electric stimulation of biceps, left and right, or tibialis anterior, left and right. And the third session, we would have a combination of motor imagery and stimulation. So now the main idea here was to show that once you have a combination of motor imagery and stimulation, you are mimicking like real movements, because you're not only imagining, but you're also receiving a feedback. So now I would like to show you a scheme for the analysis. Please don't be intimidated by this. I will guide you through this. So now again, we had different runs, training runs for motor imagery, for pure stimulation, and for combined motor imagery and stimulation. And then, of course, we would do the pipeline, which I showed you before, CSP, LDA. But the most important part is here. So in our test data set, we would apply CSP patterns to pure motor imagery. But we would apply CSP pattern, which we obtain either from motor imagery, from a combination of motor imagery and stimulation, or only from stimulation, as you can see here. So now, and if indeed what we were able to show, that if you look at the worst motor imagery class pair, then the arrow for combined use of classifiers when you use stimulation and motor imagery will be smaller. You can see these points going along this main diagonal to the right, than if you use CSP trained only on motor imagery. So now, of course, we also use this in online scenario, again, where we showed that you have a benefit from using CSP trained on using both motor imagery and stimulation. So this indicates that simultaneous presence of both motor imagery and muscle stimulation provides stronger discriminative features, application of which can also be generalized to the testing set. So now, basically such sensory motor integration is likely to be captured through the presence of connectivity between somatosensory and motor systems. And of course, we can measure this connectivity with EEG, for instance, using coherence, which allows you to see how different rhythms are coupled across different spatial locations. But before doing so, I would like briefly to tell you that whenever you hear any presentation about the connectivities with EEG or MEG, you should immediately ask about the effects of volume conduction. So just to tell you what volume conduction is for us. So even if you would have only 3 sources in the brain, which is completely unrealistic, and you have 60 channels, so because brain is a conducting tissue, you will see activity of each of the sources simultaneously in all of the channels. So you can see that source 1, red, immediately is visible by all other channels. So this is because your activity X, for instance, is just a mapping of your sources through some mixing or lit field matrix. So therefore, you need to get rid of these volume conduction effects, otherwise you will detect so-called spurious interactions. So, but just what you need to remember that volume conduction would lead to the appearance of the signals which would have either exactly the same phase delay, or phase delay will be flipped by exactly pi because of the polarity. So now in order to compensate for this, we of course use a coherence measure, but instead of using absolute part of coherency, we used imaginary part of coherency. And just let me briefly explain you what it means. So coherency is measured as the strength or as the magnitude of this vector. But what we are measuring, we want to have a situation when we do not have either zero lag between 2 sources or pi. And as you can see here, this would correspond to a situation when your imaginary part is non-zero. So by using not an absolute value, but an imaginary part of coherency, you can actually detect interactions which would not reflect spurious, but only genuine activity. So, and this is indeed what we showed in that offline study, that in case when you have a stimulation in combination with motor imagery, the connectivity is stronger for this session. And importantly, we observed that motor imagery connectivity can predict BCI performance. So the connectivity between sensory and motor areas is predictive of BCI performance. So, but now, of course, that study has been done only for offline data. So what we want to do, we of course want to show that it's relevant for online scenario. So now here we had 80 subjects. We would again look at the connectivity both between somatosensory cortex and motor cortex, but also between 2 hemispheres. So now, and we would like to predict BCI performance on the basis of connectivity measured before the online BCI performance. So now, of course, we would do the pipeline, like I explained to you before, but in addition, we would also control for the effect of signal-to-noise ratio, which strongly affects your connectivity measures. Because the stronger you have your peak of sensory motor oscillation, the better will be your connectivity, because your phase portrait of the signal is very well defined. But I will show you that we also took care of this nuisance. So now, indeed, what we were able to show that if you use within hemisphere connectivity, then you can predict feedback accuracy. So what is important that we show that connectivity both in pre-stimulus and in post-stimulus is equally predictive of your BCI performance. That means that it's not task-related connectivity, but an already existing background connectivity which defines your BCI performance. So now, to summarize this, I would like to show you the main ideas about the neural predictors. So I showed you that the strength of oscillatory sensory motor peak through amplitude modulation of this oscillation can serve as a very good predictor of your sensory motor BCI performance. I showed you that the temporal dynamics approaching a critical state is another good predictor for your good BCI performance. And finally, I also showed you that sensory motor integration between motor and somatosensory networks can also be a very useful indicator of your successful BCI performance. So now, as an outlook, I would like to suggest the following. So you can actually do stratification or selection of subjects and patients on the basis of oscillatory SNR temporal dynamics and connectivity. So for instance, if you would like to see who from stroke patients would benefit best from sensorimotor BCI, you can, for instance, assign these people to a more successful or less successful group. So now, but even though some of your participants or patients would not have these features, there are recent studies showing that you can enhance them. You can enhance both the amplitude of oscillations and the connectivity, and even you can actually get closer to critical state, for instance, using neurofeedback. So now I would like to show you colleagues who contributed to different parts of this study. Thank you, and I'm looking forward to your questions.
Thank you very much for the nice presentation. So you did a lot of work in the past years. Looks very nice. Any questions? Please let us know in the Q&A or in the chat. So we do, for example, a lot of work with stroke patients, and we take them into our treatment if they have a cortical or subcortical or even a stroke in the cerebellum. But it would be very nice to predict, you know, if there is an improvement and how big the improvement is, and also when the improvement will happen. How do you see this? Is this possible in future to do this?
So what you're referring to is to say not only whether you can in general do BCI, but whether application of BCI might be successful for rehabilitation purposes. Is that what you mean?
Yes.
Okay, so now, of course, these are two things. So first of all, the first prerequisite which I showed you, that you need to have these neuronal features to do BCI to begin with, okay, to approach this. And I would say that to a very, like if you would, importantly, what I would like to emphasize, if you would combine all three aspects, the presence of sensorimotor oscillations, very pronounced, the proximity to criticality, and also the connectivity. So I would say that in case when you have all these three, then it will be a good kind of indicator. But then, of course, you can say, well, but if I have all of this, maybe my networks are already super healthy anyway. So what can I do? So I would say that in general, like just by measuring these features before doing rehabilitation, I don't think it's very likely that you can make a very good prognosis. But also, as we know, for instance, in stroke, if you have residual motor evoked potentials evoked with TMS, then your success in rehabilitation will be better. So therefore, I would say that if at least one of these aspects, which I mentioned, if at least one of these is preserved, then at least that will be like an anchor on the basis of which your rehabilitation can work. So that if at least one of them is strongly pronounced, not all, but one, that will be already a good indicator.
Okay, makes sense. And Olga Vasanova is asking, what do you think about individual alpha peak frequency as a predictor for BCI performance?
Yes, so that's a very good question, actually, because nowadays there is a lot of literature out there showing that faster brains are smarter, meaning that the faster alpha peaks, for instance, correspond to better cognitive performance. So there are many papers out, and also the fluctuation and instantaneous frequency are very important. So we know that, for instance, sensorimotor BCI is based on mu rhythm, which has a frequency which is approximately 0.5 hertz higher than occipital-parietal alpha. And what I was able to see that people, I mean, maybe who are at 10.7 or 10.8, they have this peak, they might be better off than people who have lower frequency, because there you also have a very strong mixing from parietal sources, where the classifiers might have additional mixing problems. So therefore, I would say, if you would manage to have a primarily sensorimotor subjects, and we know from competitions of BCI competition that expert subjects, they usually have very strong mu rhythms. I mean, they might have also occipital alpha rhythm, but if you particularly blessed with having sensorimotor oscillation, then you'll be a good performer, which in turn means that you should have a little bit higher peak frequency for sensorimotor BCI.
Okay, and Krishanovsky is asking what errors can be there in the data in this kind of analysis and how to fix them or prevent
them. Sorry, again?
Which errors can you find in the data, and how can you avoid the errors? So, like,
I mean, this is a huge topic, right? So if you are talking about, for instance, artifacts, data cleaning, so this is, of course, nowadays we are blessed with having very nice and automatic pipelines, which treat both outliers in terms of muscle activity, eye movements, postural changes, breathing artifacts, heartbeats artifacts. So there is a whole zoo of enemies for our delicate neuronal signals. And of course, all of it can affect it. So I have seen so-called very successful transfer learning, deep learning algorithms, which transfer information from one subject to another very reliably. Only later on, where researchers would realize that the transfer is beautiful because they transfer eye movement artifacts because they're the same as all subjects. But they are in disguise. Even if you use ICA very nicely, there will be some little residuals which are still enough for deep learning networks to figure it out. So therefore, answering your question, it's like, it's many points you need to take into account even at the cleaning state. But then there are many things relating to non-stationarity of neuronal sources where you need also to have certain adaptation protocols and so on. So, I mean, just briefly answering it, but I can go on for half an hour or 1 hour on this.
Okay, thank you very much, Vadim. This was very interesting, very nice keynote lecture. And
thank you.
We are moving on to Alexander Kaplan. I can already see him in the panel list. So, Alexander, you're already unmuted.
Yes, I'm here.
I can hear you. Please start your video. I can already see you, and now you can click on the share screen button at the bottom of Zoom to start your presentation. So I met Alexander in Graz many years ago, the first time at the Brain-Computer Interface Conference. And he participated in all the experiments, and he was just very good controlling the brain-computer interface. And he's doing a lot of work at his university for many years. So we will get a very nice overview of current trends in the development of brain-computer interfaces from him. Alexander, do you find the share screen button?
Yeah. Do you see my screen?
Not yet. I see your video and I can hear you very well.
Why? Meeting. I just screen demonstration.
You can either select the PowerPoint in share screen, or you just take the whole desktop and then you can
take a file or maybe. Interesting here.
Did you open your PowerPoint already?
Yeah, already.
Then
now it's already on my screen.
I don't have it here.
Yeah.
Maybe I capture my screen.
What about now? No.
No, it's not loading. Maybe you close it again and you just try it again.
Yeah.
No, it's loading. Looks good.
Yeah. Okay. Okay.
So you can see Alexander Kaplan is from MSU in Russia, and the talk is about current trends in research and development of brain-computer interface technologies. So I'm looking forward to your talk.
Yeah, MSU at Moscow State University at Moscow. Yeah, thank you very much. Dear my friends from abroad and dear Christoph, could you let me speak Russian? Because it will be much more comfortable for 95% of the participants. And just because my English, it's too far from perfect.
Sure, speak in Russian, then I can test the English translator and so on.
Yeah. Of course, it's a great honor for me to be invited to so famous conference Samara BCI 2020, and to join so famous speaker company. I already impressed the presentation of Samvan Lee and Janishi Yusheba, and also Alex Asachi and Sergei Shishkin and Vadim Nikulin, and a lot of thoughts came to my head and was born in my head, but nobody read that thoughts by BCI technology. Why? What has happened 30 years after the first good system for BCI technology? In Russian. So, действительно, главная задача, которая, вообще-то говоря, стояла перед нейроинтерфейсными
that was faced by all of the BCI technologies was mind reading. I'm not sure how to translate it into Russian correctly. So we started developing BCI interfaces to read the minds or to read the thoughts of different people. Unfortunately, this task still remains unresolved. We have developed many different methods, but I would like to take a bird's eye view of the problem. During this week's conference, we will present several speeches on this issue. We will talk about different applications of BCI technologies, but I would like to take a bird's eye view of the problem, as I had already mentioned. So let's look at the brain computer interface markets by type and application. What is happening when we look at the number of different application cases, or on the when we're looking at the number of different developments in the world. Of course, all of the technologies can be split into two big groups: invasive, non-invasive. There are also semi-invasive technologies. For instance, when the electrodes have passed the cranium but haven't touched the dura matter. So once the dura matter has been penetrated, the technology becomes fully invasive. What Alex Asachi has shown can be attributed to semi-invasive technologies because we do not touch upon the cortex itself. All of the microgrid has been placed on the brain. So what is happening with invasive and non-invasive technologies? As you can see, the year 2019 marked a significant difference between invasive and non-invasive technologies. But if we were to talk about the trend that is developing until the year of 2027, then we will see that the number of non-invasive technologies will multiply, but the invasive technologies will multiply even more by the year 2027. So such a difference between invasive and non-invasive technologies, if you look at these two columns and the height of these two columns, this difference should also be correlated or adjusted, because when we're talking about non-invasive technologies, of course, we are talking about visual games, technologies, entertainment, but invasive technologies are only limited to healthcare and medicine. Let's see what happens with different applications. As you can see here, when it comes to applications, video games and entertainment are leading the way, but closely followed by technologies developed for the healthcare. It might appear a bit strange, but there are also some BCI systems being developed for the smart home applications. Healthcare is the leading application field for BCI. So from this point on, I will only be talking about healthcare applications of BCI. You all know about the BCI Horizon 2020 European program, and under this program, you see a pipeline that's been developed. You see on the y-axis the reliability, speed, and accuracy of BCI systems. And here, well, here we are, somewhere in the middle of this graph. As you can see, invasive technologies gain popularity are gaining popularity as we speak, which means that by the year 2025 or 2030, they will have acquired full speed. Therefore, both implantable, semi-implantable, and wearable technologies, invasive and non-invasive technologies will coexist together in the future. But why do we need non-invasive technologies? Well, the European program gives us 5 categories to replace a lost function, such as spellery. The way that the spellers are used, well, we do not fully restore the speech function, but we can replace it. The second way is to restore a function. For instance, we can restore motor functions and so on. We can enhance a function or optimize a function. For instance, if we have BCI systems which use neurophysiological data to detect a person's cognitive load at any point in time, and they can optimize information input. The next way to use BCI technologies is to improve an existing input. For instance, in our lab, we developed an approach using transcranial magnetic stimulation to gain an advantage during motor imaging training. And the last area of application of BCI is research. So when it is used for research and the advancement of science. I used to believe that BCI technologies are not just developed to address an existing problem, but it is a really powerful paradigm to understand the human brain.
This was an overall overview and a general overview. We have everything represented now. Some is more or less developed, but everything is there. By 2035, the words will be decoded and the entire speech will be decoded in 2035. When we talk about restoring movement, if we already decode some movement signals in 2035, there will be complicated movements that be decoded. There's intentions for a complicated movement. This progress is quite significant in the next 10 to 15 years. At the same time, it doesn't say that we will be able to fully ensure direct interaction between the brain and the external actuators. What do we have now? For people who are fully in a coma, or there are technologies to get connected to them, of course, controlling neuroprosthesis, it already exists, and we are all aware of 2012 when a couple of American laboratories showed a patient controlling the manipulator with, of course, invasive technologies, some hybrid technologies. When BCIs are controlled, or rather control the muscles of the body. This FES is used. This intention to move is marked as a movement of a muscle. If something happened not in nerves or muscles, but in the coordination of neurons on the cortex, which cannot issue the command to the muscle. And of course, finally, we have those devices that replace or restore speech. And we have our NeuroChat technology, not just a speller, but a commander that can issue commands to external actuators and and you get emails and go online and so on. That's full replacement of communications that already exist. Finally, another technology that we really need, when you stimulate the spinal cord, but instead of using buttons, when the patient himself or herself turns on, the stimulation has to be turned on by the person's intention. It has to be connected to the spinal cord. And some works like that are already there, and this is the technology that we already have. Without BCI, we had deep stimulation technologies for a number of reasons, to work with tremor or epilepsy, and that already exists, but these devices are being developed and they need feedback. They need to be able to monitor how efficient that stimulation inside the brain is, and then we will have a real BCI system. It already works, and it's already being studied, and there are about 200,000 people in the world living among us, and they don't feel epilepsy or seizure due to the help of these technologies. Finally, bionic prosthesis and bionic hands existed for a long time, and Russia actually is the birthplace of those prostheses. But controlling these prostheses is quite complicated. Some of them are already in the market, but they need to get this controls or feedback from the brain. At least our next task is to make them be able to feel the touch in such a way that we could send this feeling directly to the brain. The brain should feel that the prosthesis touches different objects. That's already well known. It was already presented here in Samara too. What else do we have in the pipeline? We need to somehow help the cognitive abilities of humans. As we use EEG or other neurographic or biographic values for the activity of brain, we need to understand how high the cognitive load is. It's very important during training. If you give too much load, people won't be able to do it. But if you combine it with some additional BCI systems, and the system would know how much the brain can take in, not even consciously, but how much of information the brain can take in, the training systems will be more efficient. This is also in development. I have not found any conclusive data on that. Of course, here we have computer games, and we enhance people's gamer abilities, but in reality, these are cognitive abilities. This is short-term memory, attention, not just time for motor response, but to sensor motor response to what you see in front of you. All these functions can be trained, and there are lots of developments about adding BCI technologies into gaming or gaming control. Also, it's moving BCI technologies to understanding what the brain does. We had a debate already here, started by Sergei Shishkin, about consciousness. This is one of the higher functions of the brain. It has lots of functions, but even if consciousness is out, the brain keeps working how to get in touch with it. That's the task for the BCI technologies. And you can look at the brain mechanisms at the subconscious or unconscious level, and there are lots of them. That's very important. And finally, neural interfaces in the reverse sense, not the ones that transform brain commands to external devices, but on the contrary, take extra external commands and send them to the brain. We are all aware of cochlear implants and even retinal prosthesis, and this technology already works. There's a broad range of technologies that even now are in operation, but there are also limitations. I show some of them here that exist, and they have been with us for a number of years, and it's really hard to overcome them. What are these limitations? There's a very slow command transfer rate, 20 bits per minute, 5 to 8 letters per minute. If we talk about a speller, that's not enough for a healthy person, while they can type 100 letters a minute from the keyboard. And these limitations are still there. The second limitation is that there's too much resources for memory and attention are taken by these technologies. The subject has to be as attentive as they can when they imagine a motor image for the BCI to work. Will it be useful for a healthy individual? Imagine that you cannot learn the subconscious control of the bicycle. Imagine that you have to control every movement while you are on the bike. But this is what is not happening with BCI. Or there's very little progress. Our short-term memory and attention and vigilance are overloaded. You cannot do anything else but work in the BCI contour. Let's get back to decoding the intentions of thoughts. It's really hard. Today, when we talk about motor images, we can decode 4 or 5. Correct me if I'm wrong. We can decode 5 or even maybe even 6, but with 5 you get lots of errors. Why is that? Why cannot we decode using EEG? Why cannot we decode, I don't know, an orange or a steam engine or something else? What prevents us there? All right, EEG is not the brain doesn't use EEG for information exchange, but it's really hard to do even if you use invasive technologies to sort of dig into your specific thoughts invasively. And the main limitation here is that we are using to detect different subjective psychological factors. We use correlates, neurological correlates of those psychological acts, but not the actual codes that the brain actually uses. My next point, I already said how we cannot detect more than 4 to 6 images. The accuracy is insufficient. There are lots of errors. Even if we make a random selection 1 out of 2, you get 20–30% error rate, even in the best systems. And finally, what I want to mention, any such system, for them to work reliably, they have to be trained for a long time, from 50 to 100 sessions. So in conclusion, are there any prospects for the future? This is a very quick spelling interface, 175 bits per minute, as opposed to 24 bits per minute, working using induced or event-related potentials or evoked potentials. And you can see how the letters are typed really quickly. This technology allows you to type really fast, but the environment is so aggressive you cannot stand it for too long. We had a system like that in our laboratory that got 149 bit, but it's more milder on the patient. And we also spoke about decoding and detecting speech, but how much of that is decoded really from 42 to maybe 30%, and that's with limited amount of words. So that's a long way from decoding normal speech. And as we decode movements rather precisely, but there are still quite a few errors with only a few commands. And this is my conclusion. The main problem of our reason why we cannot talk to the brain directly is because we don't know the code of the brain. If we knew those information modules that communicate within the brain, we would intercept these signals. That if we knew those codes, it would be easy for us to control. But we don't know it. We use the correlates that sort of look for those signals through trial and error by training the artificial neuron networks. Is there a way out of the situation? Yes, there is. And our latest studies that I have shown indicate that if we combine BCIs with AI, but not to create classifiers of what's already in the brain, but for them to talk to another, the brain is quite flexible. It will find a way to change its electric activity to make the AI understand its activity better. And the AI, on its part, as it trains, will be finding the meaningful facts that will give you results. And in this two-way channel, there will be this real brain-machine language of speech. And this will be a new signature on the new foundation, after which you will get real interactive interfaces where brain interacts with computer or AI directly. Thank you for your attention.
Example, asking, do you think that invasive BCIs will be used only in healthcare, or is it also possible to use it in entertainment industry?
Yes, of course. Please imagine if the healthy person, how you could find the healthy person to do some hole inside of the scalp. It's impossible. I guess it's just a big problem with ethical problem, moral problem, and so.
Then Tomek is asking, do you think it's useful to use EG and FNIRS together to improve the current?
Yes, we try to do that. But of course it will be better than just BCI, than just EG. The combine EG plus NIRS plus eye tracker, it will be good system for the connections, direct connections with the brain.
And then from Alex is a question, what do you think about MEG for brain-computer interfaces? MEG. Yeah, MEG.
It's too heavy. It's just too heavy. MEG, of course, it's nice technology, but it's practical to the BCI technology. Just only that thought.
Okay, then thank you very much, Alexander, for the nice presentation and answering all the questions. Impressive, all the work that you did.
Thank you.
And the last presentation would be from Mark Stark from the Institute of Molecular Biology and Biophysics from Russia. But unfortunately, he is ill. And that's the reason why we don't get this presentation today. And I can already see Alexei.
Christoph, no. Mark's not here. He is ill.
Mm-hmm.
And now we ended our session.
Yes, this is what I was explaining.
And now we proceed to interviews. And first, with you, Christoph, short interview, if you can.
Sure, pleasure.
And my first question is about our morning. How you can estimate first talks? What level? What your comments about these talks?
Yeah, we got a very nice overview of the trends which are happening at the moment. So we had neural recordings, we had recordings with macro and microgrids, and we had also EEG people on board, also MEG, and all these technologies are advancing a lot. So we have seen in the presentations that a lot of new applications are appearing, and it's also very good that a lot of work is happening in Russia. And you can also see the present publications that all the researchers are doing. They are in very high impact journals, and this shows how brain-computer interfaces are becoming more and more important in all over the world.
My second question is about your handling. It's very noisy presentation in Word. Can you tell about this work?
Yeah, our Pangolin system is a 1024 channel EEG system that we just released, and maybe I just quickly share the screen because otherwise it's really difficult to know what it is. Here you can already see the Pangolin mounted on a shaved head. So in total we have 1024 channels on this woman. You can see these electrodes are polygon shaped. Each polygon has 16 channels. So the EEG electrodes are really tiny. Here you can see it a little bit. They're made of gold. And with that you can glue it onto the head. Important is also that there's a head stage amplifier. So the amplifier must be as close as possible to the electrode. It's almost an ECOG grid on the head. And then you get a never seen resolution. So here you can see, for example, more than 300 channels just on the sensory motor cortex. This allows us, for example, to decode single fingers with EEG technology, so you don't need an implant anymore.
It's work only on shaved head?
No, you have to shave the head, but with the advantage that you will get a never seen resolution in EEG than before. So basically you can replicate every single neuroscience experiment with this never seen resolution. You get much more resolution for brain-computer interfacing. And if you think about healthcare industry, so for an epilepsy patient, for example, it's much easier to shave the head and to get a high frequency oscillation recording with this technology compared to an implant.
Thank you. And I want to ask you my question that I want to ask Alexander. What do you mean? What main fundamental barriers is in the way of the development of BCI at all?
To whom is this questions?
To Christoph.
I thought
Now to Christoph.
I thought it's for Alexander. Yeah, there are many fundamental things, but it's very much driven by the application. So EEG recordings are perfectly suited, for example, for stroke rehabilitation, because you get exactly the resolution that you need for treating lower or upper limb deficits. If you think about single finger control of an avatar or of a prosthetic device, then this is not the resolution that you get with EEG devices, and then you need an implant. And you have to fulfill all the medical requirements to leave the implant inside the body for a couple of years. Then you need power supply. You have to transfer all the information to the computer, which needs again a lot of battery. And for the EEG, the usability is the biggest part. So in a daily life, you don't want to put on an EEG headset just to get a remote control for your TV headset. So it must be inside of your body and work all the time to make it usable. So basically, researchers can work on electrodes, on amplifier technology, on signal processing, on better experimental paradigms, on new clinical studies. So there are a lot of things to do in future. Alexei, you are muted.
Thank you, Christoph. We will wait you on the second part of our plenary section. And now we invite to short interview Vadim Nikulin. Are you here?
Yes, hi.
На русском, да.
Хорошо.
So the interview will be in Russian. Julie is here. Yes. For those of you who just joined us, I would like to say that you have logged on to the Neuro Week Samara 2020. So we will be online from morning till evening. We have short breaks in between. Well, this is one of these breaks. We're interviewing different scientists. So please submit your questions and we will ask our presenters. So right now, Vladimir Nikulin has joined us for a short interview. Vadim, could you please tell us very briefly, for people who just joined us, well, you had a speech. So what was your speech about? Well, when we're talking about BCI, well, BCI itself is a very interesting concept itself, but which neuronal indicators can we use in order to see whether the application of BCI technology will be successful or not? So depending on the types of signals generated by neurons in the brain, we can predict whether the neuronal interface between your brain and computer will be successful. So your neuronal activity or neural activity of a person will define or predict the success of a BCI system. So what can we do if we see that BCI might not be successful? Well, it is not utterly hopeless, because then when we can use neural biofeedback. I was talking a lot about sensory motor systems, and the sensory motor systems come down to the fact that a human being can modulate the amplitude of neuromotor oscillations. So if these oscillations are at a lower amplitude, you can increase this amplitude using biofeedback. Let's say we put a person who sits in front of the screen, and on the screen we will project the amplitude of the oscillation using EEG, so therefore a person will be able to increase the amplitude of the oscillation, and maybe following that, so a person would be a better user of a BCI system. But what I also talked about is that I'm a neurophysiologist, electrophysiologist by training, and apart from BCI, which is an applied area of my research, I also look into fundamental brain activity. So I'm looking into criticality, and criticality is one of the fundamental theories which explains how our brain functions and which is attempting to explain how such a vast quantity of neurons are connected to one another. So we had this idea that the criticality is related to an optimal brain performance and to an optimal information processing. So we believe that criticality can also be relevant for BCI. We have ways that will allow us to show how we can non-invasively measure a person's brain signals and tell whether the brain is performing at optimal capacity. Depending on this optimal capacity, we can predict whether the person will be a better or a worse user of a BCI system. And which are the optimal criteria? Answer. Well, I think everybody probably heard that in the brain we have excitatory and inhibitory processes. For instance, when we have too many excitatory processes, that's bad. It leads to epilepsy. When everything is inhibited, it's also not so good. So here we need to find a balance between excitation and inhibition. So we can use electrophysiological parameters to measure this balance. And depending how close you are to this golden mean between the excitation and the inhibition, we will be able to determine whether you'll be an optimal user of a BCI. So before we use a BCI, we need to thoroughly research a person. No. You must not. I was just talking about these predictors and whether these predictors should be used. So using predictors, we can try and determine which neuronal processes are responsible for BCI performance. But let's see, we are using a BCI system in a rehabilitation program. So before we tell a patient that you have to go through a certain rehabilitation modality, we would have to assess whether this patient would be successful in rehabilitation, or maybe for this particular stroke patient, a different procedure would be more beneficial, such as transcranial magnetic stimulation. Question, Alexei, do you have any questions on that topic? No, I don't at the moment. So, Vadim, could you please tell me what are you looking into now? What can we start looking forward to hear from you at the next conference? Well, I didn't have a chance to present other research into BCI because we're also working with visual activation and a number of other topics. But I think that at the next conference, I would like to talk about the potential use of BCI technologies, not just as a part of a BCI paradigm, but maybe in different areas. For instance, in the adaptive brain stimulation. What is adaptive brain stimulation? We can use non-invasive magnetic electric fields to stimulate the brain. So the effectiveness of this stimulation comes down to a neuronal state of a subject. So we can monitor the current state with the precision of several milliseconds, and then we can estimate whether this stimulation should be applied. Why do we use the stimulation? Well, there are different protocols that are related to an increase of brain neuroplasticity. And brain neuroplasticity basically encompasses all training, education, neuro rehabilitation, neurological, psychiatric conditions that we are trying to address through neuroplasticity. Therefore, the developments in BCI and the way that we can monitor the current brain state, and basically when we're talking about BCI, we need the current state in order to control, let's say, a robot or a certain software, but we would like to use it to control brain stimulation, to make brain stimulation more efficient. So this is one of my areas of research, and maybe if I have a chance, I'll talk about this during the next conference. And you're talking about invasive interface. No, I'm talking about non-invasive interface. And how can you stimulate it using non-invasive technologies? Well, you can use non-invasive technologies such as magnetic fields stimulation, but there is also transcranial direct electrical current stimulation. People can even do it at home. I do not recommend that you try it at home because you need to know the current parameters, you need to place the electrodes carefully. But such a brain stimulation is used to increase self-control, which would be very relevant for people who have impulse control issues. How do I stop myself from eating another chocolate bar? And people, for instance, with obesity, well, they have very poor impulse control. So we can use non-invasive brain stimulation in order to upregulate certain cortical activity to achieve better behavior control. But we do know that TMS only produces short-term effects. Well, that is not entirely true. They might be short-term effects over, let's say, one session, but if you use a certain TMS protocol, let's say for 10 minutes, the effect that is achieved might last for an hour. But then again, if you keep applying this stimulation over a week, over a month, then we will be able to reach a cumulative effect. All of these stimulations are related to the changes in membrane processes, and not a lot here relates to the change in neuronal synapses. So basically, what we do, there are a lot of things that change in the synaptic junctions between the neurons. So when we apply the stimulation, certain things start performing better. How can we use BMI here? Well, I think there are BMI and TMS. Well, there are a lot of different options when it comes down to this. I would say that the key methodology behind BCI, what is the key principle between BCI is to get a very high quality control signal, a signal that would allow us to control a prosthetic or a piece of software, or in case of my research, it might allow us to kick off the stimulation. So I think there is another area of research that we can talk about. We can use TMS, and that is a non-invasive method. So we can use TMS to change sensor motor oscillations. So the sensor motor oscillations are used for BCI. So basically, I can wear, let's say, helmets and press a button, and there you go, brain stimulation occurs. It doesn't really work like this. But somebody in the chat is writing that they can't hear the discussion. I don't know. The discussion. No. They can hear the discussion. Don't worry. Oh, sorry, Julia. Could you please repeat your last question? Well, I'm just trying to fantasize here. So how is it going to look maybe in the future? Let's say a person would have a device that can use the power of thought to control something. No. It's not going to look quite like that. Well, when I mentioned BCI reads neuronal signals, and then later we use this information for something else. But in my case, I'm saying that it's not going to look like I'm going to use BCI to initiate this stimulation, but rather BCI will monitor my current state, and BCI will switch on the stimulation if needed. What is the question? There is a question that we received in the chat.
Chat, but you can also say it.
Okay, I copy paste.
No, anything what is good for you. Anything.
I read. How many brain states we could monitor using critically theory-related tools? DFA, 1F. It's only awakes versus asleep, etc.
I see. So probably I see the way. I mean, should I answer it in English? I guess, of course.
Yep.
So, well, the point is that first of all, we have different brain areas. So we are not talking about cortex as one area. So depending actually on the task engagement, your different areas show different activations of the scaling exponents. So for instance, if I would use some sensory stimulation, then I would primarily change and attenuate scaling exponents in the sensory motor area, while in other areas it will be a different story. So while you that the levels of vigilance could be easily tracked with 1/f a spectra of 1/f noise, and with this long-range temporations, we can more accurately it if we are using, for instance, inverse modeling, can extract this exponent for each voxel specifically. So I wouldn't say that this is a good measure for tracking instantaneous changes, because per definition, the calculation of LRTC, let's put it this way, minutes of neuronal data. So there are papers showing how you can do and apply the trend fluctuation analysis on the short-term segments, let's say over like 20 seconds. But that's not the idea. The idea of this analysis is just to show and to reveal fundamental aspects of neuronal processing in the human brain. However, I would not use this for tracking brain states. For that, I would rather use something like the amplitude of oscillations, or probing it with evoked responses, as I showed you. You very well know, like SSVPs and so on and so forth. And also using very transient, within 1 second, the connectivity matrices between different brain areas, but not really the LRTCs themselves, because they rather address a different question.
Thank you. Thank you. And
все, вопросы закончились. Вадим, спасибо большое вам за интервью.
Thank you, Vadim, for this interview. Looking forward to working with you during the next conference. I hope our next conference will be in the real world. And now we have Alexander Kaplan on the line. Okay, I'm here.
Unici. But now, Alexander.
Alexander. All right, Alexander. We have a number of questions in Russian, which Christoph didn't ask you. Let me ask the number one. It's from Timur Garavinov. Yes, DARPA actively supports BCI research, and you can see its logo at a variety of resources. Is Russian Defense Ministry interested in the BCI technologies? Can they be practically used, or can they support somehow scientific research? I don't know anything about the Defense Ministry and what they can or want to do. But of course, they can support the research work by financing or by goal setting, but that's just only theoretically. Another question. In your opinion, when we don't really understand yet how memory or consciousness works, should we change the methods of studying the brain? How can BCI help us in that? Well, a brain is a highly complicated object, and we ran out of methods of study, experimental methods of study that would allow us to go deeply into the brain. We think about molecular or genetic mechanisms, but we don't know how the entire system works, how those billions of cells get together and synapses, how they are organized and controlled. We know very little. We know less than we used to think in the past, and that's probably the most complicated object that humans ever faced. It's quite possible that we will never understand how brain actually works. From Artyom Kozhanovsky, what are the obstacles to the development of BCI as we rehabilitate heavy cases of limb paralysis and other and I see prospects for such patients with problems with spinal cords because the BCI technologies never help them. And it's not about restoring, it's about restarting the link between the cerebrum and the spinal cord. It's below the damage spot. It's possible. There were some technologies done with rats when intentions of human beings were sent as electrical stimulation for the spinal cord. The locomotive mechanism is in the spinal cord. If you activate them, then the locomotive motions will start. How to activate them? You can use BCI. The BCI will detect the intention of a human being to make a movement, and then you turn on the stimulator, which activates the movement itself. This group of patients will definitely get those devices in the next 1 or 2 years. Next question is from Vadim Nikulin from Moscow. Hello, Alexander. I agree with many of the things that you're saying, especially using BCI in neurocognitive tasks, not necessarily BCI for BCI. It's about symbiosis between man and machine. Let's say we can implant a chip that will augment or even improve the work of the brain. But as a biologist, you know that in the evolution is rather lazy and slow. It chooses the simplest way. Let's imagine that we implant a really good chip into a brain, and the brain becomes lazy in a sense because many of its functions are going to be now performed with this chip. In other words, it might lead to degradation of main neuronal functions because the brain will be part of the activity where the chip is an important part. So on the one hand, we will be improving neuronal functions. On the other hand, we will be deteriorating them because if this chip fails, then everything falls apart. What do you think about this danger? I'm a neurophysiologist like yourself, and I don't think the evolution will help us there because when a child is born, he will be without a chip, and it won't help. And I'm talking about something else. I'm talking about the fact that there will be some category of people who will be able to use it better and probably pass it on to their posterity. And I agree with the main idea here. We can use, even now, as we use calculators and internet, it means that humans have less short-term knowledge, operational knowledge. In the past, we had to use lots of operational knowledge. Now we hope that we will be able to use internet. It's not in our brain. And And we are slower, lazier, but the activities of our brain, the higher psychic functions, are sort of leftovers of what's left in the brain. Exactly. So it's not only an issue of genetics. If you implant this chip, your neural pathways will all be connected to this chip. And if you then remove it, then it's done. That's it. I don't believe in this. We started from the internet, an external assistive device for the brain. Why do we need a chip in the brain? For me, this is something that we don't need. It will be impossible to implant this chip. All those fairy tales of Elon Musk that he will implant 100,000 electrodes, it won't give us anything because this 100,000 electrodes will feel 100,000 impulses from 100,000 neural cells, but who will be decoding all this? We don't know the code. We don't know how they talk to one another, what they're discussing, those cells. We won't be able to give this chip any real intellectual work. It will be just an auxiliary device to maybe correct or read the intention of moving one's hand, but these are only basic things that won't give us any foundation. I agree with you. I quite agree with what you're saying. And there are ethical points there. It's still in the long distant future when we will be implanting chips into healthy people's brains. And I deal a lot with Parkinson's disease where we implant lots of chips. Well, that's a different story. But even in the Parkinson's case and the epilepsy, when you implant electrodes, still only a few channels are used, and they are there only to deal with seizures, only to detect the birth of a seizure, and that's not enough to interact with the brain. We used to have 3 contacts or channels. Now we have 8 or 16. It's improving. It's something that we need, but it's required for a specific function or to send the current with that particular micro area, which helps with the seizure. But it's important in the clinical tasks. I apologize for interrupting all others, but that's an important issue, and I was glad to be able to listen to your lecture. There were lots of great ideas. Thank you, Vadim. There's this interesting format of a discussion. We might repeat it again when a couple of scientists and researchers discuss certain issues. We have you told us about this additional system of processing. I have a similar question to the one I asked to Christoph, and then we'll move on to our Japanese colleague. But my question to Alexander, it's a question about fundamental issues. What are the fundamental questions or barriers that prevent us from developing BCI? As I said, we have run out of resources to detect correlates of psychic acts, not the information that goes through the brain. We cannot decipher it, decode it, but only external signs that you might have some intentions. Here we did a pretty good job, and the saturation, we need some sort of breakthrough for the brain to really be able to have this full contact with an external partner, with an external electronic partner. So far, all BCI systems work as follows. You detect a sign of a certain process in your head. What kind of letter do I have in my head? What kind of movement I intend to make? And then send it to the actuator. And this is over. And on the other hand, we have to have an equal partner rather than a device that simply performs some functions that would guess what I have in mind and giving me the feedback, showing me the options of what they think. My brain is quite flexible. If the brain sees that the guess is inaccurate, it will adjust its electric activity in such a way that this partner would really guess what the brain wants. We need to come up with this interactive channel of interaction between the brain and intellectual tools. I'm not using the word AI because it doesn't exist. There are tools of artificial intelligence. We need this interactive channel for them to agree between themselves. In 2005, there was this first article written in from Russia in a foreign publication how the brain agrees with the external device. This was my article where I described the brain connected with the monitor and the RGB engine of the monitor. If this person had a preference, if his brain preferred one of the colors, he had three colors, blue, red, and yellow, and they could move it with the rhythms of the brain. And it turned out that the brain was willing to establish such communication, even if the subject was not aware of that intention. They need to be able to understand each other. And if we build this channel, it will give us a new language of communication between the brain and the actuator, the executing device. They will be speaking the same language. Thank you. And now moving on to our interview with Junichi. Junichi, hope you are online.
Nice to see you. Hi.
Thank you for your great talk. It's very interesting for me. And I want to ask you some questions. And first is, you talk about rehabilitation from the for after the stroke, yes? And in your talk, you say what you're doing and what is a result for your manipulation, for your working with BCI. But what is in our brain in this moment? What is changing in brain from as a result for using BCI?
We have several results so far. For example, we use MRI scan study. The stroke patient's brain remodel the motor-related circuit inside the brain in the ipsilegional side. Even the brain, one side of the brain has damage, there are still some residual neural network inside the brain. So these rest of undamaged neural circuits is reactivated by the BCI training. So the fMRI shows that such spared neural circuit activity after BCI training. So patients learned to control the rest of the neural network for sending the motor commands to the paratic arm. That's the one result. the another result is that they're using the transcranial magnetic stimulation. We apply the stimulation to the damaged brain. And this stimulation also results the muscle twitch after BCI training. That also supports the evidence that the remaining neural circuit is functionally unmasked to help to sending the motor command from brain to the muscle. So such neural functional reorganization in the rest of the neural network will be promoted even after the stroke event.
You use only usual MRI or the tractography?
Oh yes, we are now doing the tractography and volume-based morphometry, which are showing the structural plasticity. It's still undergoing, but another researcher in the United States already published such tractography and VBM analysis for stroke patients who received the EEG-based BCI. That paper shows the very positive results that the remaining cortical muscular fiber structurally changes its property for helping sending the motor command from brain to the muscle.
You use uninvasive BCI in your work, yes?
Sorry?
You in your work you use no invasive BCI.
Non-invasive EEG-based BCI.
Yes, EEG based. What do you mean? Does this invasive BCI have a potential to the neurorehabilitation after the heavy stroke?
Yes, I think so. Since invasive type of cortical activity recording, such as the electrocardiogram, is a high resolution of the brain signal detection rather than EEG. So such device may promote a further amount of neuroplasticity when the ECOG-based neurofeedback is given to the post-stroke brain. So I'm very positive to use invasive type of neurofeedback for promoting a larger scale of plasticity. But unfortunately, I don't have such opportunity to do this study. But we have much experiences to promote the plasticity in non-invasive way. So we are ready to supply such know-how or experience to the potential collaborators. So I'm wondering if we could make some international collaboration in the invasive BCI platform for exploring further potential of a new BCI-based neurofeedback for functional recovery.
Thank you. And the last question is, you use BCI to the post-stroke rehabilitation in shoulder and finger motor function.
Yes.
What do you say about rehabilitation in speech functions? BCI in rehabilitation to speech function or etc.
Yes, that's also very promising, since when we think about the computational process of sensory information and the motor command, there are very similar overlapped mechanism between the vocalization and limb movements. Since both in the vocalization function and the online processing of the sensory hearing information and reflects the motor command that changes the facial muscle or tongue movement. So it's quite similar online feedback mechanism for processing, making such vocalization. So the motor learning process that we have been explored using the BCI paradigm could be easily applicable for vocalization rehabilitation in the same manner. In the rehabilitation research field, they already tested EMG-based biofeedback treatment. So already traditionally saying that such online biofeedback, including EEG neural feedback would be promising for functional recovery of vocalization. That's a very interesting research topic, I think.
Thank you very much, and we will let you in an hour and a half in part 2. Thank you.
Thank you very much.
Thank you.
Что, у нас закончились интервью. Вторую часть мы
Well, I think
ожидаем
our interviews are over, and the
4 часа
second part of
самарскому
our
времени.
plenary session will be
Будет 3
held
часа
at
по Москве.
4 p.m. Samara time or
Будет
3
вторая
p.m.
часть
Moscow time. So that will be the time
пленарной сессии.
when we will have the second part of our plenary session. And Professor Ushiba will be the moderator of the second part of the plenary session. Right now, we are going to show you a short but extremely beautiful video, and after that, we shall continue.
Давай анонсируем, кто выступает во второй пленарной сессии.
Oh, maybe we should announce the speakers for the second part of the plenary session. Okay. The second part of the plenary session has a very representative panel of speakers, not unlike the panel of speakers we had for the first part of the plenary session. So we are going to have Christoph Guger, who was the moderator of the first session. Then we're going to have Mikhail Lebedev, Peter Brunner, from the Washington University School of Medicine in St. Louis, USA. He will talk about adaptive neurotechnologies. We will also have Sliman Benzmaya. He visited Samara before. He will talk to us about a biomimetic approach to artificial touch. We will have Lee Miller, who we saw last year from the Northwestern University, USA. He will talk about adapting brain-computer interfaces to real-world behaviors. And our last speaker will be a classic BCI researcher, Jonathan Walpole, from the National Center for Adaptive Neurotechnologies, Albany Stratton VA Medical Center. He will talk about the substrates of BCA-based behaviors. So the second part of our plenary session will go on from 4 p.m. to 7 p.m. And then starting from 7 p.m., we have an online NeuroBar. You will be able to attend the NeuroBar if you're a registered user. So if you haven't registered yet, please log on to bcisamara.com and go ahead with the registration. And you will have full access, not just to the NeuroBar, but to a whole host of our online events. And right now we are launching the video.
Топовых лекторов прямо в одном городе, пожалуйста, наши коллеги могут приезжать в Самару, а не разъезжаться по всем странам мира, по конференциям и ловить этих лекторов где-то как-то.
Действительно, вы собрали фантастическим образом, в Москву людей не зазвать. Здесь вы собрали абсолютно топовых докладчиков со всего мира.
To be perfectly honest, I've never been to Russia before, and I thought it sounded like a very good opportunity. And I think the development of brain-computer interfaces is a very exciting new field, and I'm glad to see that Russia is becoming more significantly involved in the process, and so I'm happy to come to this conference and offer my own research.
So the brain research in Russia is very strong, so I really want to collaborate a lot more. And basically during my lecture today I will talk about the brain-computer interface.
It's a very good forum for exchange, also between the different countries. So we have people from the US and from Japan and from Europe. And it's a very good opportunity to talk with the Russian community, obviously.
Это продукт Reviver, уже достаточно известный, который мы ставим в медицинские учреждения, посвященный реабилитации больных после инсульта, и продукт Motion в первую очередь для реабилитации больных ДЦП.
So we're back on. I hope you can see us. I hope you can hear us. So now Alexei and I are going to visit our virtual poster session, and do join us, please. Let me share my screen. Alexei, could you please maybe tell us a little bit about the poster session? We're also going to be giving the Best Poster Awards. Well, yeah, that will come a little bit later. We do have a common virtual room. And so, see, here we have different rooms. We have an exhibition. We have a poster session. So let's go visit the exhibition. Here we logged on together with you, so we will have an opportunity to learn how to use this virtual expo together. Oh, look what we have right here. We have a video chat. So basically, there is a video chat located at each virtual booth. And we can visit a booth. Let's say, let's go visit a booth. Why don't we? Let's go to this one. Well, how do I use it? How do I do it? Let me see. So the posters are here. Expand your browser window and make it full screen, please. Oh, look. Where did we end up? Well, we ended up exactly where we wanted to be. So right now we're visiting the GTEC booth. And here GTEC is telling us how they make the pangolin device. So basically here you enter your name and you can watch a video. Enter your login. Let's see, you're a patient, or what's your name? Oh, not a login, but a name. You just enter your name. There you go. So we are in this virtual room. So what can we see here? Oh, there's nobody here. Oh, there's nobody here. Oh, I finally got the idea behind this virtual expo. What happens is that we log into different virtual booths. We come to virtual labs, and there we should be greeted by real people. Unfortunately, this virtual booth is empty. Now, how do I get out of here? See, it's not so easy basically to try and visit a booth at a virtual expo. We are all really looking forward to a real life event. Let me tell you this. So, Alexei, what do I click? How do I log out? What do I do? Wow, that looks like a bit of a quest. Let's continue. We are online. Oh no, this is just a welcome screen. So basically, we log in and it should open using a new link. Well, what happened to my camera? Why can't I see myself? So basically, we logged into here. You just click on whatever you want to visit. Make sure you choose your preferred language. You have chat. You have technical support. You can click on a PowerPoint presentation. So you have all of the contact details. And if you want to talk to somebody, you log into here. Then a new link pops up. You click on the link. Hello, we have reached your booth. It's very nice to meet you. Could you please tell us a little bit about yourself? Who are you? What are you doing here? Can you hear me? Are we online, guys? No, we're not online. Okay, we're back online. Although, well, there was a tiny technical glitch, but we're going back to the virtual expo. Can everybody see my screen? No? Okay, let me bring it back. Oh, there you go. Now you can see it.
Okay. There are some technical troubles we're facing, and we need additional 5 minutes to fix everything.
So we are back online. We're going to start the second part of our plenary session in 15 minutes. And now we will attempt one more time to visit our virtual expo. So Alexei opened the page. He's going to share his computer screen with us. And we're going to announce one more time that the second part of the plenary session will start in 15 minutes. And we're online, aren't we? What do you think, Alexei? Oh, we're finally online. So good afternoon, all of you. Please join us for the second part of the plenary session, which will kick off in 15 minutes. So we have a lot of very interesting speeches for you. But while we had a break, Alexei and I had a chance to visit our virtual expo. So you can log in there using the link on the BCI Samara.com exhibition.bcisamara.com. So you can log into the virtual expo. And right now we're going to demonstrate how you can do that. So see, now we are at the virtual expo. So you can move from booth to booth when you press on the hexagon. And that is, this is the start of the expo. I click on the hexagon and I see a lot of booths around. Say we go to the 3A stand. So what do we have here? Well, first of all, you can click on the video. You can view the demo video by brand. Oh, by the way, yes, you can send them an email. You see this red rectangle. You can click on it to launch your email client. You can go to the company website. So you can look at the slides, the PowerPoint slides, which is the short presentation of the company. But the main thing is that you can click on this video camera icon. You will have to enter your name here. So let's join the meeting. Hi. Hi, everyone. Oh, hello, Yuri. See, he can hear us. Oh, tell us, what do you have here? What do you have at the booth? Yuri, we can't hear you. Well, I'm being told I have to relaunch the demo. I'm not sure what that means.
All right. So I don't know whether we the setting of the Zoom is ready for starting a webinar. I think the staff will manage something.
Looks good. So I share my presentation if it's okay.
Okay. So shall I start the
Я могу начать?
So thank you very much, everyone, are coming back.
Итак, я начинаю. Большое всем спасибо за то, что вы все вернулись на пленарное заседание, присоединились ко второй части пленарного заседания.
Actually, we have a long 3-hour plenary session, but I definitely promise that all the speech in this session will be very beneficial for all of us. So the first speaker, and actually all the 6 speakers, except the final last speaker, Dr. Walpole, the speaker will have 20 minutes more or less the presentation and 5 minutes, very short question and answer. And Dr. Walpole, in the last speaker, will have 40 minutes of a presentation. So the first presenter is Christoph Guger from GTech, Austria. The title of his presentation is Brain-Computer Interfaces for Rehabilitation, Brain Assessments, and Mapping. So Christoph, go ahead.
So thank you very much. So I'm coming from these companies, GTech Medical Engineering, and we are based, or the headquarters in Austria, but we have also offices in Spain and in Albany, USA, New York, and also in Hong Kong. And next year also in Australia. And we are active in about 15 international research projects at the moment. So in the first one, for example, in seizure AI, we use deep learning algorithms to identify epilepsy, or in another one, RecoverX-LAG, we work on brain-computer interface technology for lower limb rehabilitation. And this is also the first example that I would like to give you. So this is based on the event-related desynchronization from my supervisor, Gerd Purcell, at the University of Technology in Graz. And basically, it means if a patient or a human subject is imagining left-hand movement, you find the activation over the right hemisphere. So the red spot is the ERD. And if the person imagines a right-hand movement, you find the activation over the left hemisphere. And the nice thing is that these spots are at the same location for every human being. That's the reason why we know exactly where we should place the electrodes to capture left and right hand movement or foot movement. And this is something that we are using nowadays in our RecoverX system. That's our brain-computer interface for stroke rehabilitation. And here you can see the setup. The patient is equipped with an EEG system. Looking at the computer monitor, he sees an avatar, and the avatar gives him the instruction to imagine left or right hand movement. So at the moment the patient is imagining left hand movement, the brain-computer interface picks it up, and then we use a functional electrical stimulator to stimulate the muscle so that the hand is really moving. This is the big advantage because patients like it a lot if the hands move again as soon as they imagine the movement, especially if they were paralyzed for many years. So in this video here, you can see how this looks in real time. This is one patient who has a right hand that's affected by the stroke. And you can also see that we work with both hands. The left hand gets stimulated, also the right hand. So this is now the instruction to imagine a left hand movement. The patient does it. The brain-computer interface picks it up, and then we stimulate the left hand. This is more interesting because it's the affected hand. You can see the stimulation lasts for about 4 seconds, but the stimulation is only given if the brain-computer interface makes the correct decision. You can also see it's interleaved, so we want to activate both hemispheres. That's very important because then the task is always new for the cortex, and it also leads to a better coordination and speed of upper hands. Such a treatment normally lasts 45 minutes, and we are repeating it 25 times with every single patient. And here I can show you one example. This was a patient who was pretty young, only 38 years old, and the stroke affected her right hand. And she came into the brain-computer interface study 14 months after the stroke. And then we did 31 training sessions with her. Each one lasted 45 minutes. You can see the brain-computer interface classification accuracy in the first session was about 65%, but then she learned very nicely to increase accuracy. In session 26, she even reached 100% accuracy. So the BCI accuracy is a very nice marker to know if patients are engaged and are doing it correctly. And in the middle, we see, for example, the difference that we get for left and right hand movements in session 1 and session 31. So the red vertical line indicates the time point when the patient gets the instruction. You can see the sensory motor cortex needs about 3 seconds to switch it on, and then we find the difference between left and right. But in session 31, this is already much faster. So the sensory motor cortex is switched on within 200 milliseconds. And we find a bigger difference between left and right hand movement. And on the bottom, we can see the ERD maps. So on the left-hand side, we have the left hemisphere. On the right-hand side, we have the right hemisphere. So you can see on the right hemisphere, we already see some ERD marks indicated here in red, because it's the healthy side. And on the paretic side, it's very silent. There's not much ERD going on, but in session 31, you can see there's a much stronger ERD on both sides. The patient is able to switch on the ERD, the motor imagination, very, very rapidly. And this is the brain plasticity that we want to achieve with the brain-computer interface. And beside the BCI markers, we use a lot of functional tests like the upper extremity Vogel-Meyer assessment and 17 other tests to describe which functions are improving. And here you can see between the pre-assessment and the post-assessment, this is 1 day before the therapy and 1 day after the last therapy, we can pinpoint a 6-point improvement in this Vogel-Meyer assessment. Interesting for this patient is also the 9-hole peg test. In this case, the patient has to stick 9 little pins into certain positions. And you can see the left hand, the healthy hand, improves from 17 to about 14 seconds. That's an improvement of 16%. It's also something that we see pretty often, that the healthy side gets better. But of course, much more interesting is the right hand, the paretic side. And the patient needed 7 minutes and 26 seconds in the first session. So this is forever for doing this test. And at the end, she needed only a little bit more than 1 minute. That's an improvement of 600% in fine motoric skills. That's, of course, very important for the patient. Then we look at the Patel index. That's a questionnaire for daily activities, at tremor scales, at spasticity scales. And you can also see here that the spasticity in the hand and also in the wrist was reduced because of the treatment. And this patient was a hairdresser, which was actually unemployed after the stroke. So she was at home and couldn't work anymore. The social security system was paying her salary. And right after the treatment, she was able to open her hairdressing studio again, and she started to work again. This is, of course, exactly what we want to achieve with the treatment. And in this video, you can see the 9-hole peg test after the therapy. So this is for somebody who needs 1 minute and 14 seconds for completing the test. You can see it's pretty difficult to grasp the pegs. Then you have to rotate the little pegs and you have to put it into certain locations. So if the hand was paralyzed before, it's a really demanding task. And this is about double time of a healthy control or a healthy person. And this video shows the haircut that she was given to our physiotherapist right after the Recoverix therapy. Watch especially to the right hand, how she is using it. And this was also the reason why she could return to her job after 25 training sessions, which is only about 15 hours of training. And if you imagine yourself going to a fitness studio after 15 hours, you don't look much better. And here's a summary of a clinical study that we did. So in this study, we have 51 patients. And whenever there was an improvement in one of the 18 tests, then we added a few points. And if there was a decline in one of the tests, we subtracted a few points. You can see this patient, for example, 29, improved in most of the tests. Also, this patient here improved in a lot of tests. But there are other cases, for example, this patient, P11, improved only in a few tests and declined also in some. But in total, we got an improvement, an overall improvement in 49 out of 51 patients, which is very nice, and only 2 patients declined overall. So the first patient here had a second stroke during the treatment. This is something that we cannot compensate, of course. The other patient never paid attention during the treatment, so he was looking around, was always talking. That was the reason why he didn't achieve high classification accuracy. Then the treatment is also useless. At the moment, we are running another clinical study for lower limbs, locomotion. And in this case, we stimulate the muscle here on the leg. And we are showing the avatar in a mirror so that you get the impression, or that you can see your leg and also your hand movement, to activate also the mirror neurons when you can see the movement. This looks also very nice. And here you can see some locations where Recoverix is already used for regular treatment. And just in our own rehabilitation center in Austria, we completed already treatment 10,000 last month. So it's heavily used. Another application that we are doing pretty often is brain assessment. And if you're looking at this diagram, then you can see that normal persons have normal cognitive functions and normal motor responses. But coma patients, on the other hand side, cannot move and the brain is not working. But some patients are a little bit better. For example, in unresponsive wakefulness state or minimal consciousness state, or also locked in or completely locked in patients might not be able to move, or they cannot communicate with you. That's the reason why we developed the Mind Beagle system. So the beagle is the little dog that you might know from Australia on the airport. They have a very good nose, and in our case, they are sniffing inside the cortex if they are functional. This is done with auditory paradigms or vibrotactile paradigms. For the auditory paradigm, we put loudspeakers onto the ears, and then we play high and low tones like da-da-da-dee, da-da-da-dee, and we instruct the patient, please count only the high tones. And then we will find a nice P300 response indicated here in green for the high tones, and the ERP, the blue response for the low tones. And in this case, the difference is really nice and the shape is really good. The problem is very often for patients that the response is really ugly, and physicians just don't know how to interpret it. And that's the reason why we need also the brain-computer interface classification accuracy, which is shown on the bottom. So here we have 30 stimuli that we are giving, and the patient achieved already 100% accuracy after 4 high tones. And this means that we can perfectly discriminate high tones from low tones. And this tells us that the patient was understanding the task. And then we can go to the next experiment, which is a vibrotactile experiment, where we put vibrotactors onto the wrists. And then we instruct the patient, please count on the left or on the right-hand side. This is producing again a P300 response. This is now an example from an unresponsive wakefulness state patient from Stephen Lowry's group in Liège. And here for the auditory evoked potential experiment, you can see we get an EP. There's also a difference between the high and the low tones. It's a little bit significant. You can see it with the green shaded area. But the EP is not really nice, and physicians wouldn't mean how to interpret it. And if you look at the brain-computer interface classification accuracy, we can see it's around 20%. That's below the significance threshold, and this means there's no information inside the EEG data. For the VT2 experiment, we have one vibrotactile stimulator on the left hand, another one on the right hand. And the brain-computer interface instructs the patient, please count the left or the right stimuli. And you can see it's mainly noise, so there is no difference between left and right hand. And also the accuracy is 0%, so there is no information inside. And this means on this day of the assessment, the patient was not able to use the brain-computer interface. There's another example also from Stephen Lowry's group. It's a minimal consciousness state patient. And for the auditory testing, you can see now that we have a nice P300 response. It's significant. It's very different from the low tones. It's also visible on all the channels. And the accuracy goes up all the way to 100%. Also for the vibrotactile testing with one tactor on the left hand, another one on the right hand side, we see a very big P300 response, and the accuracy goes up to 100% even after a few stimuli already. The VT3 testing has one disc tract on the back, so one on the left hand, one on the right hand, and one on the back. And also here you can see a very nice P300 response, and also here the accuracy goes up to 100%. And if I would see this data, I would tell you that's a healthy person, but it was an MCS patient. This proved, for example, that the patient was able to follow the task that we were given. And in the next step, you can go for such patients to answering yes and no questions. So we are starting this screen here. And there's a little button, so you can ask him, do you like the BCI conference in Samara? And then you press the button and the patient can say yes when he's counting the vibrations on the left hand, and he can say no when he's counting the vibrations on the right hand. And then the little loop moves after about 30 seconds to a certain position, and this confirms the answer. And normally we are asking questions where we know the answer. Are you born in Russia? Did you study in Moscow? Something like that, so that we get an objective proof if the patient can follow us. So here's a patient, for example, an unresponsive wakefulness patient from Poland. And you can see in session number 1, we were asking him 10 questions. He answered 7 correctly, and 3 questions were undetermined. So the BCI system wasn't sure what the patient wanted to say. And in this case, the little loop stays in the middle. So on the second day, he answered 9 correctly, 1 was undetermined, and so on. And in total, we asked him 50 questions, 38 times the system was correct. Once he made a wrong decision, so 1 wrong answer, and 11 times the system wasn't sure. And this allowed us very objectively to prove that this patient is able to conversations. And this changes, of course, the life of these patients and also of the physicians, because suddenly they are more motivated and they are doing something for the patient. Together with Rossella Spataro, we worked also on a prediction of the outcome. In this case, we are using also these vibrotactile stimulators. We tested it in this case with 13 different unresponsive wakefulness patients. And basically, we found if the classification accuracy is above or equal to 45%, then this predicts a positive outcome of the patient. So if we look at the first patient, then we see that he started with a coma recovery scale of 6 points. And after 6 months, he had 15 points. So he got much better. So, or patient number 9 even woke up. But it's also the opposite. So in patient number 13, we didn't find a high classification accuracy, only 5 and 0%. This patient died, for example. So the BCI accuracy has a very nice prediction value for the outcome that you can expect. And the last example is actually brain mapping that you can do with BCI technology. And in this case, we are asking, in this case, Kai Miller to implant ECOG electrodes directly on the cortex. And then you can instruct the patient to be at rest. And Kai calculated the power spectrum, indicated here is the blue line. And then he was asking the patient to do a hand movement, indicated here with the red line. And interesting is, of course, to compare resting with hand movement. And in the low frequency band, you can see the resting has more energy than the hand movement. That's the event-related desynchronization that we already know from EEG recordings on the surface. But if you're doing ECOG recordings, then you find also differences in the high frequency band, around 100 Hertz. And here doing the hand movement, we have more energy than doing resting. This is called task-related high gamma activation. This is also something that we can use for mapping the eloquent cortex with the computer phase technology. So at the moment you can see that we have an epilepsy patient with about 100 electrodes implanted. On the left-hand side, the ECOG signal is coming in. And then we are instructing the patient to be relaxed and not to do anything. So he's just sitting there and we get a recording of the ECOG data. In this case, it's very clean, and then the instruction is to move the tongue. The patient is moving in. And then we find these red bubbles on the temporal base, for example, because he's seeing a face image. This is activating the high gamma activation there. And over the sensory motor cortex, we find the tongue. we are asking the patient again to relax, to have another baseline recording. And after 10 seconds, the next task is given. So in this case, he's just listening to a Japanese story. So first of all, he's seeing this loudspeaker symbol. This activates again the temporal base, the region responsible for symbols. And afterwards, the auditory cortex is activated because he's hearing it, and also Wernicke's area because he's understanding what he's hearing. The last task that I'm showing is to solve Rubik's Cube. So in this case, he needs the fingers, but again, first the temporal base is activated because he sees colors, and then the sensory motor cortex with the finger region is activated. And this is something that we developed together with Gerwin Schalter and Peter Brunner, who is also one of the next speakers. And this is interesting because it's purely passive. This means we are just measuring brain activity, and the alternative is electrical current stimulation, which is done at the moment in hospitals, but it's also dangerous because if you're turning up the current, then you can induce seizures, and if a patient gets a seizure, then you basically have to stop the mapping procedure. And here I can show you also a video of another application that you can do with this technology. In this case, Dr. Ogawa is showing different images to the patient, and the patient is just watching onto the images, and we are decoding in real time with the brain-computer interface what he is seeing. So this is, for example, a face, and in the monitor in the middle of the video, you can see what the brain-computer interface decodes. A face, that's a symbol, a face. This we are analyzing high gamma activation from the temporal base, from regions responsible for faces and also for symbols. This is now very interesting in a moment. So the patient sees himself, it's a face. Now he sees Christoph Capella. This is also interesting. He looks into Dr. Ogawa's face, and we don't find immediately that this is face because the cortex is already used to Dr. Ogawa's face. So it must be a new task to activate the high gamma activation. And at the moment, we can decode 18 different types of symbols when we look at the high resolution ECOG recording from the temporal base. So this was ECOG technology, and nowadays, if you're recording 256 channels, high density EEG, it looks like that image that I'm showing you here. But basically, the electrodes have a distance of 2 centimeters. So if you want to go further ahead, then we developed the Pangolin system. That's a ultra high density EEG system, which allows you to do 1000 channels. And here you can see an electrode grid. It's shaped like a polygon. The electrodes are made of gold, and that's a head stage amplifier because the amplifier must be as close as possible to the recording location. And here you can already see a head that is shaped, equipped with 1024 channels. So the polygons allow us to glue the electrodes pretty close together. You can see also the head stages, which are now connected to the main biosignal amplification system. And in this case, we have, for example, more than 300 channels over the sensory motor cortex. And this allows us even to decode single fingers from each other. And with this setup, you can basically replicate every single neuroscience experiment because you get just much more resolution than before. And on Saturday and Sunday, we are running again a Brain.io, brain-computer interface hackathon here in Samara, with a couple of host institutions in Moscow, Novosibirsk, Vladivostok, and so on. And everybody is invited to join the hackathon. So teams have to work together and come up with new brain-computer interface applications. At the end, you have to give a presentation, and we have also a very nice international jury looking at the results. We have also some rewards, and we have also very nice keynote talks. So if you're interested, just join on Zoom again, and please register yourself to be inside the hackathon. Thank you very much.
Thank you very much, Christoph. Really wonderful talk. Are there any questions from the floor? Please note if you have any questions into the question panel. We have one question from one floor. Is G pangolin in the last one application available for the purchase? How is the noise problem solved? And does it need special software?
It's available on the market, so you can already purchase it. The noise problem is solved that we have a biosignal amplifier inside the electrode grid. And that's also important because the electrodes are very small. They have just a few millimeters diameter. The distance between the electrodes is also very small. So without the amplification technology inside the grid, you would get a lot of power line interference or other interference. But with these active electrodes, the data quality is nice. And you need a high-amp system, and then you can record up to 1024 channels. And you need also software, the G-HiSys from G-Tech, for doing all the real-time processing.
Okay, thank you very much, Christoph. The time comes. So let's move on to the next speech. Next speaker is Dr. Mikhail Lebedev. Title of his presentation is Neural Dynamics, What Rotates and Why? So please, Dr. Lebedev.
Thank you very much. Hello, Samara. So I'm very glad to present here. So let me try to share my screen. One second. Okay. Okay, so what rotates and why? Today I will talk about how pictures changed in the neurophysiology articles. So I worked in this area for quite a lot, so I could observe how the figures in these articles changed from relatively simple ones like this to more complicated ones like this, then to more colorful ones like this. And nowadays, if you open a neurophysiology paper, then you see pictures like this, which look very beautiful, but sometimes are hard to understand. So I will cover briefly the evolution of this and then talk in more detail about this part. So traditional neurophysiology started with the work of Edward Everts, who had awake behaving monkeys perform motor tasks like pull or push a lever, and he would insert an electrode in the monkey brain and then record a single neuron in the motor cortex. And then he would plot pictures like this. For pull, firing rate would go up. For push, firing rate would go down. And then the paper, a typical neurophysiology paper would report that some cells go up, some cells go down, some cells stay the same. So this was a typical neurophysiology result in the beginning of neurophysiology. Then Georgopoulos made it a little bit more complicated. So he asked the monkey to move the lever in different directions. And then in this particular case, this neuron is active when the monkey moves to the left and less active when the monkey moves to the right. So Georgopoulos plotted the firing rate of this cell as a function of movement angle and called it a broad tuning curve. So and to the public, it was very appealing, the words broad, so that motor cortical cells were not very specifically tuned to the movement directions, but more or less represented many directions. Also notice that for the preferred direction, this firing rate increases, whereas for the other direction, the opposite direction, it decreases. So in one case, it goes up. and the other case it goes down. So later I will call this cell as a cell with heterogeneous response. So another addition came from the experiments with instructed delay tasks, where a monkey would be instructed to move, but it was not allowed to move. And then the monkey would wait, the monkey didn't move, but still you could see changes in neuronal activity and also measure directional tuning, like in Georgopoulos' work. Also, and this is from my own work, so this cell gradually increased its firing rate, but notice that in every single trial, there is a lot of variability in how this cell fires. So when you say, oh, this cell increases its firing rate, this is not the whole truth. There is more to this. Probably there is some information hidden in the fine temporal structure of these spikes. But unfortunately, nobody knows what kind of information is there in the spikes, and maybe this is something to be studied in the future. But to move on, one addition to the directional tuning is that you can measure directional tuning at different times. Say you look at the velocity of a monkey movement at time 0, and then you check how the neuron is active at different times before or after. And here you see that there is a rotation of preferred direction, an interesting fact that has some implications. The next development was the studies of neuronal populations. And again, Georgopoulos was a pioneer of this because he introduced a population vector. This is an attempt to predict movement from the activity of many cells. And Georgopoulos gave each cell a vector pointing in its preferred direction, and then multiplied this vector by the firing rate, then calculated the sum, and at the end he had this population vector that basically tracked the movement very well. And the more cells you put in the calculation, the better was the prediction. But the problem was that Georgopoulos did not record all these cells at the same time. He recorded one cell at a time, today, tomorrow, and so on, and it took him several months to record all these cells. So this is inconvenient, and it is more convenient to record many cells at the same time. And Humphrey and his colleagues did this in the 70s. So they didn't record too many cells, maybe like 5 or 10, but they showed that if you record 5 to 10 cells and put them in a linear equation, then you can predict movement parameters. Then the most important paper in this development was the work by Nicolelis and Chapin. They recorded close to 100 cells in a rat using multi-electrode arrays implanted in the brain, and then they made this rat controller robot. Also notice how the pictures changed with the development of the computers. They became colorful, and they could process many cells in the real time. So yeah, here is a typical, well, not like the best example of recordings. Here we recorded 394 neurons, and each wavy line here corresponds to a neuron, and with so many neurons you can really analyze what's going on in the brain in depth. And you can plot these colorful pictures if you have many neurons. This is a population peristimulus time histogram. So, and I sorted neurons by the time when they became active, and you can also see a wave of activity developing. So some cells start to fire earlier, then the others later, and so on. So I will mention the wave a little bit later. Also, when you deal with the ensembles, it's typically you describe their performance by a neuron dropping curve. So I will not go in all details of this, but basically, the more cells you have, the more accurate your predictions become. But this is not a linear relationship. You need, let's say, for good performance, you need 10 neurons. For better performance, you need 100. Then you go to 1,000, 10,000, and so on. And with ensembles, you can get more information with single cells, most definitely. So this picture looks complicated, but it describes the changes in preferred directions in an ensemble of a cell. And in the first three cases, the monkey was either controlling the robot with a joystick, or continuing to move the joystick, but controlling the robot through a brain-machine interface. But the last one is when we removed the joystick completely and the monkey tried to do it just with the brain. So typically, when you read about brain-machine interfaces, it is described that a monkey or a person is controlling something simply by thinking. But if you look close and you have ensemble recordings, then you see that simply by thinking is quite different from moving the head at the same time. And so some plasticity is needed to convert this picture into this picture. Curiously, this issue hasn't been explored sufficiently, so this is something to do in the future. Now, rotational dynamics, and it became popular after the paper of Mark Churchland and his colleagues, published in Nature, and the paper was very ambitious because they claimed to have invented some new explanation for everything. So according to them, whatever people did before them was very confusing, but now they discovered something in the population data which basically explains everything. So what did they discover? They converted their multi-neuronal data into 6 principal components, and then constructed a dynamical equation where the velocity of these principal, the first derivative of these principal components is a function of themselves, so multiplied by some metrics. And you can find in this matrix submetrics that makes this vector rotate. So what is rotation in this multidimensional space? Basically, this means that for some principal component becomes active first, then it is followed by the other, and so on. And then when you analyze many trials, you get a nice picture like this, which presumably means that there is some population rotational oscillatory dynamics hidden in this population activity. But notice that I said that different activities take turns, so there is probably some sequence in this activity. So I was curious at looking at the original data. So what is the basis for pictures like this? So luckily, their data is available online, and nowadays many people put their data online, so it's very easy for a person who wants to take somebody's data and then analyze and show how smart he is, basically. So I looked at the data, and then it was immediately clear that there was a sequence even in the responses of original neurons. So here, condition 1, 10, 37, 76 correspond to monkey moving in different directions. But still, although the monkey does different things, some neurons are activated early, the others late, and so on. So you can divide this population into the early activated neurons, intermediate, late, and then you can continue playing with this. Say you take the average response of the early population, intermediate, late, and so on, or you can even shuffle conditions. Even if you shuffle conditions, you get basically the same response. And if you plot this in 3 dimensions, early neurons, late, intermediate, you get this rotations already. So no need to perform complicated analysis, neuronal dynamics or whatever. So you can construct principal components from these neurons, and then they already sort of rotate, and even for shuffled conditions, they rotate. If you apply Churchland analysis called JPCA, then you get nice rotations. But then if you apply JPCA to shuffled conditions, you do not get rotation. So I was very puzzled by this. So it looked like that their analysis really has some sophistication that maybe I didn't understand. So why do you have a clear rotation in the data and then it is gone when you perform JPCA? So to get a better understanding of this, I conducted a simple simulation. So each neuron was simulated as responding like this in a very arbitrary way. So the amplitude was chosen on random. The only thing that I required was that the neurons were activated in sequence. And if I used a sequence like this for all conditions, basically, any condition, there is a sequence like this, and then apply JPCA analysis, then I didn't get rotations. Then I thought, oh, well, maybe this makes the data badly conditioned or something. So for half of the conditions, I shifted this response a little bit, which would correspond to the monkey responding a little later. And then these rotations magically appeared in the JPCA plot. As a sanity check, if you do not do any sequence, nothing appears in the JPCA plot. Next, remember I mentioned that when I shuffled the conditions in Churchland's data, I was getting this picture like this. But when I shifted for half of the conditions, the response by 100 milliseconds, then I was getting these rotations. Then probably I should have done this in the very first place, but I read their paper more carefully, and then I discovered a trick that they were doing. And the trick was they calculated average response for each cell, and then they subtracted from each response. So to me, it looks like a questionable procedure, but what it does, it basically kills this rotational structure for very nice cells that just form a sequence and response very similar on each trial. So if you do not do this subtraction, then you get these rotations very easily, even from shuffled conditions and for simulated data with temporal sequence. Only for simulated data with no temporal sequence, you do not get these rotations. Furthermore, if the goal is to obtain rotations, you can obtain them with a multiple linear regression, and you can even fit their data to an infinity sign. So you can fit, or you can even predict, and you can even do this for the shuffled data. So that was it. We published it, and so you can read this paper for more details. But curiously, just recently they published a review in Annual Reviews of Neuroscience, and they responded to our paper, and they said basically that this sequence like responses are very artificial and they do not exist in real data, although we found them in their own data. So this prompted me to do some additional analysis. And by the way, they emphasize that real cells, they are not as nice as the one that form a sequence, and the real cells just do whatever they do on different conditions. They are very heterogeneous, and they do not fit this nice sequence-like pattern. So I looked at their data once again, and first I looked at the neurons with very consistent responses. It was very easy to find them. So in this case, these are the best 20 cells with very consistent responses, and as in our previous publication, they form a nice sequence of responses. If you run this JPCA, you get a nice rotation, and even if you subtract the mean response, you get these rotations. Also, if you look at the principal components, then the first two principal components are just basically the same response for all conditions, and there are two types of them shifted in time. So because these sinusoids are shifted in time, then you get these rotations. So next I looked at the cells with really bad responses, I don't know, with really good heterogeneous responses. Remember in the beginning I mentioned this Georgopoulos cell that fires for one direction and doesn't fire for the other direction. So these cells are like this. They are easy to find, but the analysis when you sort the activity by peak firing rate, that doesn't work. So I had to invent another method for sorting them, and I used variance or standard deviation. Basically, for each cell, I analyzed how their variance changes as a function of time, and then I sorted them, and then they form a pretty clear sequence. So, and also you can do this JPCA analysis, they rotate, but I think they rotate because the sequence exists even for these cells. You can look at principal components for these cells. They are, again, heterogeneous, different on different trials. In 3 dimensions, this doesn't look very nice, but you can see sort of rotations which resemble JPCA result. So sorting by this variance or standard deviation is not very different from sorting by peak activity. So because if you sort by standard deviation and look at average PATH, then you get pretty much the same sequence. So if you sort by average PATH and go back to standard deviation, the sequence is worse, but it is still partially preserved. So these are related methods. And finally, I just simulated this Georgopoulos cell or heterogeneous cell. So the cell would fire, would be activated for the preferred direction and would give a negative response for the opposite direction. Then if you take a bunch of these cells with randomly pointing preferred directions and do not require them fire in sequence, then in the principal components or in JPCA, you get no rotations. But once you form a sequence of these cells, then you easily get these rotations. So the new message here is that even if you have these cells with heterogeneous responses, which are very dependent on what the monkey actually does, still, if they form a sequence, then in this analysis you get rotations. If they do not form a sequence, no rotation. So I think this rotation is pretty much equivalent to the existence of the sequence in these responses. I would advise that people who do advanced analysis like this still look at their original data and see what they have in their original data. So that's it. Thank you very much. And if there are any questions, I will be glad to answer.
Thank you very much, Dr. Lebedev. Wonderful talk. Any questions from the floor? Please put the questions on the Q&A panel. Yes, we have one question. Okay. What is the practical application of this analysis?
So the practical application, you probably have to ask the inventors of these methods. But for example, the original paper of Churchland and his colleagues was published more than 1,000 times, and it's very popular. Also, if you look at this literature, you find many papers. And some of them are actually interesting. For example, they talk about neurons forming subspaces in the multi-neuronal response space. So, for this, you could use to trick the BMI either to perform well or not to perform well. For example, you can require the neurons develop some sort of an unusual activity that they normally do not develop, and this is harder. So there are some implications both for basic science, for our understanding what populations of neurons do, but also for brain-computer interfaces.
Thank you very much. So time comes.
Okay.
Thank you very much, Dr. Lebedev.
Thank you.
So let's move to the next speaker. Our next speaker is Peter Brunner from Washington University School of Medicine in St. Louis, United States. Title of his presentation is Adaptive Neurotechnologies that Interact with the Nervous System. So if you are ready, please start.
Thank you. Can you see my screen?
Yes, perfect.
Okay. So yeah, thank you for having me. So I'm an associate professor at Washington University in St. Louis. I'm also serving as the deputy director at the National Center for Adaptive Neurotechnologies. And one of the research lines that we're interested there is technologies that can really interact with the nervous system. And what I mean with that is that they can actually use perception or other sensation into the nervous system. But before I start my presentation, I have to disclose my conflict of interest. I hold some intellectual property for brain mapping technologies and may derive licensing income from the same. So let me just introduce the general idea that I want to discuss today. So over the last 20-something years, we've learned a lot about the functional organization of the cortex. Specifically, fMRI studies have discovered a lot of areas throughout the brain that are responsible or are involved in various low-level and high-level function. For example, we know about visual perception, face recognition, we know about motor cortex, and all of this evidence is mostly correlational. Because it was basically observed through indirect means, for example, for an increase of blood flow while they perform a particular task in an fMRI scanner. Recently, we have more and more the opportunity to actually observe these changes on the cortex with even more detail and also more directly. The recent advent of electrocorticography allows us to place sensors directly on the surface of the brain or within the brain. These sensors are basically electrodes embedded in a elastic sheet, and they're embedded and placed for clinical reasons. For example, for people that suffer from intractable epilepsy. In these people, we implant these electrodes to localize their seizure onset zone and also to deliver cortical stimulation through these electrodes to map out the brain. And I will talk about that in more detail later. Another interesting aspect about this kind of technology is that it is constantly evolving, that the technology, in this case the resolution of the ECOG grids, is constantly increasing, and we're getting a better understanding of how to actually process these signals. And that's also reflected in the number of applications that is coming out of this field that has been starting off to take off in the last 10 years and has reached over 500 publications per year. But also the quality of this field is increasing, with most of those publications ending up in peer-reviewed journals. So the most seminal discoveries in ECOG is that there are two frequency bands. The low frequency band that is very indicative of basically the readiness to execute a particular movement, basically cortical excitation, and the high frequency band that's really indicative of the functional organization underneath. For example, in this case, you see somebody who's performing a motor movement with his right hand, and you see in the left hemisphere hand motor cortex showing power augmentation in the high frequency band, and an attenuation basically in the low frequency band that's not so specific and basically makes the entire motor cortex more excitable. We have seen these kind of like patterns, not just for particular single movements. We can do this for various different movements, and you have seen some of that work actually in Christoph Guger's talk just half an hour ago. What I want to get into is that these kind of like power augmentations that we can observe in ECOG have a very strong correlation with the function that you elicit or inhibit through electrical cortical stimulation. And I will expand a little bit on how to do that actually. So interim summary is basically if you place electrodes on the surface of the brain, we can observe functional changes directly, and we can deliver electrical cortical stimulation and also perturb the nervous system directly, therefore interact with the central nervous system using electrical stimulation. So how do we do that? I want to start out with describing a little bit of the methodology behind that. What we use to stimulate the brain is biphasic stimulation. And these are basically very short pulses. They are 300 microseconds in duration. And the amplitude of these pulses ranges from single milliamps to up to like 15 milliamps. And these pulses are delivered in trains at stimulation rates of 50 hertz or above. And when this stimulation is delivered, what you actually will observe, and I will show this later in examples, is either an excitatory response. For example, if you stimulate motor cortex, you will see the hand move, or if you stimulate areas involved in processing, you will see an interruption of this language processing. There are a couple considerations when we perform this. Obviously, we do this in human subjects, so we don't want to cause any damage or other injury to the cortex. So the safety considerations that we're mostly concerned is that we have to keep the charge density below a certain threshold, in this case 50 microcoulombs per centimeter squared per phase. So you can already see this is charge density, so this has something to do with the surface area of these electrodes. We can only stimulate electrodes because of that reason that have a certain range of impedance, because otherwise we're not just going to increase the voltage unnecessarily. We have to select what kind of stimulation we perform. There are options that are monopolar or bipolar. These kinds of stimuli, unfortunately, can cause seizures. You've seen this also in Christoph Guger's talk just half an hour ago. If you stimulate near the epileptogenic onset zone, you may actually start after discharges that can develop into a full-blown seizure. So sometimes you need to either have the anti-epileptic drugs already administered, or you have to have benzodiazepines ready, for example, Ativan for injection if these after discharges develop into a seizure. When we observe the effect on the behavior or the cognitive performance, we typically have to make sure that the stimulation frequency is high enough so that we deliver enough charge to the cortex. So stimulation underneath 20 hertz typically is not very reliable in eliciting a functional response or a change of cognition. The stimulation current has to be within a certain range of safety, and I will illustrate that later. For example, motor cortex can be kindled with 2 to 6 milliamps, so it doesn't take much current intensity to create either a cessation or an actual motor movement. However, language requires much higher intensities and longer trains to be disruptive. Also, the stimulation artifact needs to be visible. You need to make sure that these stimulation trains don't result in interstimulus after discharges, and that they produce a consistent effect. So what that means is that when we perform such a stimulation and we're looking for eliciting a particular effect, we have to perform multiple stimulation trains, and those have to be interleaved with sham trains. And the subject typically is not aware whether you're actually stimulating or whether you're actually performing a sham train. Just to summarize a couple of the safety concerns that we have, obviously the charge transfer. So we have to make sure to stay with below 50 microcoulombs per centimeter square. We have to also make sure that when we stimulate chronically, that the voltage below the threshold for electrolysis, that for chronic stimulation, the thermal deposition doesn't exceed a St. Miller threshold, and also that for longer stimulation, that this doesn't cause any other tissue damage. So, as I said, one of the considerations is how big are those electrodes? You've seen in the very introduction that you can have standard density electrodes. These are the ones that have been used for the last 40 years. They're typically 2.4 millimeters in diameter, and we can have high density electrodes. If we look at the relative surface of these, we can quickly see that high density electrodes are much, much smaller, and therefore the current density will be much higher. So we have issues of how high we can stimulate. The same holds true for depth electrodes, and there another compounding factor is that the fields that we generate are getting much more complicated. So in terms of the safety considerations, as I said, for motor, we just need a few milliamps, but if we need to go into language territory, we need up to like 50 milliamps. So if we look at our 300 microsecond pulse duration and the safe area in which we can operate, we can see that at least for brief stimulation with standard electrodes, we can go all the way up and can elicit disruption of language function. But if we go into high density electrodes, we very quickly go into a territory where the stimulus intensity has to be limited. Also want to touch a little bit on the device evolution, because if we actually want to perform this, we have to have devices that are FDA approved and allow us to stimulate or deliver the stimulation safely in humans. So the evolution is kind of interesting because the first standalone cortical stimulators were built and released in the 1970s. This was actually pre-FDA, and they have been around for a very long time, mainly because the market for this kind of stimulation was not very large, and it took until the 1990s until the first company pursued FDA approval. And basically the device pushed out was pretty similar to the device that was in the market before, since the 1970s. And the evolution has been very slow in delivering capable devices. However, recently, electrical stimulation, specifically for the purpose of clinical mapping, has been evolving. For example, this is a system from Neon Coden. Neon Coden provides epilepsy monitoring system. These systems typically consist out of an amplifier system, video system, and it basically allows you to synchronize the signals recorded from the brain with video stream and review them after the fact. They basically provide now a system in which you can click at particular electrodes and deliver these stimuli. This is mainly geared towards clinicians that want to perform stimulation mapping or want to explore the clinic onset zone in more detail. For scientific investigations, the advent of programmable stimulators has been very significant. This is a stimulator that is now being FDA approved and provided by GTEC. This stimulator can be controlled and is programmable, and what that allows us is to do more systematic exploration of the effect of electrical cortical stimulation, in which we augment the clinician with a program that delivers this stimuli in a more controlled fashion, sometimes in a closed loop fashion. For example, if we want to deliver stimuli at particular phases of an underlying oscillation, with these devices, with these programmable stimulators, we can do that. So I want to show a couple of demonstrations of the effect of electrical cortical stimulation. These are videos that have been generated in the course of being people undergoing temporary placement of these ECOG electrodes and subsequent functional mapping of their cortex. So this first example is now stimulating a human subject with 2 to 3 milliamps in motor cortex.
Oh, whoa, jeez.
And you can see the effect is very strong. It's very difficult for the subject not to notice that its hand is controlled. So again, the subject did not want to control or move his hand. This is involuntarily induced by stimulating hand motor cortex with 3 milliamps at 50 hertz. You can not only, or in addition to making these crude movements, if you have more high density electrodes, you can control the motor function in a more fine detail. So this is an example from Nick Ramsey, University Medical Center in Utrecht, where he basically has implanted a high density grid over motor cortex, or motor cortex in this case, and he stimulates different pairs of electrodes, okay, that are adjacent, and elicits different directions of tongue movement. So as you can see here in the first example, he is stimulating this pair, which elicits a movement of the tongue to the left. Now he stimulates a pair adjacent to that, which makes the tongue move up. And another example, another pair adjacent to that, now basically the tongue is moving to the right. And these are very reproducible results. And here's basically now all of them superimposed. So we not only are able to induce motor movements, we can also induce perception or disrupt perception. So this is now results presented from a subject implanted at Albany Medical College. This subject had electrodes implanted over fusiform gyrus. This is an area that is involved in recognizing faces. And when stimulating nearby electrodes there, we could observe that color perception was induced and face perception was disrupted. So now I'm going to show you the example for color perception. So the subject is stimulated at these electrodes that I annotated here.
Yeah. Spots.
Where?
Peripheral vision. What just happened? There's something blinking.
Where are your peripheral vision?
Top corner. Right.
So you get a very, very specific perceptual effect from the stimulation. More interestingly, now a very adjacent electrodes that's now right on fusiform gyrus. When this is stimulated, the subject is unable to recognize faces.
No longer have any kind of eyeball. No, come on. On your right side. Right side, I'm not really seeing much. Now I have the face again? Yes.
So if you stop the stimulation, the effect immediately stops to persist, and the subject is again able to recognize the face. So interim summary, so what we have learned from these clinical stimulation studies is that you can induce motor movements, motor sensation, perception, and you can disrupt all of these functions as well. Another thing that we've learned is that the effect that we can observe can be distributed throughout the cortex. So you can have the same observation by stimulating a wide range of areas throughout the cortex. Even more troublesome, you can actually, on the same side, depending on stimulation parameters, observe various different effects of your stimulation. For example, you can have numbness and a sensation at the same location depending on the stimulation parameters, or deafness and sounds. So next I want to touch upon a couple of the clinical utilities that this closed loop stimulation that you can now perform has. So as I said before, these electrodes allow us to record and stimulate at the same time. So one of the clinical applications is to disrupt epileptic activity that could potentially develop into a full-blown seizure. So what you see here is basically a trace of around 10 seconds where the subject is actually undergoing functional mapping. So the red area on the left shows basically this mapping burst where the cortex is stimulated. Unfortunately for the subject, this mapping develops into what's called after discharges. You can see this activity here on the blue underlaid traces. And Obviously, the clinician then attempts to disrupt this ongoing after discharge. So he delivers brief disruptive bursts to the cortex. And he repeats this several times. And on the third disruptive burst, he actually clears these after discharges. So while this is at the bedside, is pretty simple. You observe, you detect that there's something outside of the range of normal activity, you deliver a disruptive burst, you observe. If it's cleared, you're good. If it's not cleared, you repeat. So this principle that has been observed in the clinic for the last 30 years has been recently translated into a device that can be implanted into patients, the so-called responsive neurostimulator. So in this case, you have to first identify the area from where the seizures start. You implant these electrode strips right in clear proximity or above this area. This is fully implantable. It contains a battery that lasts several years, and it operates 24/7. Once it's appropriately programmed, it can detect that the seizure may develop and can try to disrupt it. And this is going to be fairly effective in a variety of different epilepsy conditions. So finally, I want to transition a little bit into some of the ongoing research in our laboratory in which we want to further investigate the scientific utility of electrical stimulation. So in this case, the area of the area in which we are most interested in is single pulse electrical stimulation. So far, I've shown you bursts of 50 hertz. Leave us very little time to observe the effect of the stimulation. However, you can reduce the stimulation frequency to 2 hertz while keeping the same intensity. And this allows us to now observe the functional response to stimulation. However, this is not a trivial endeavor, as the stimulation that we deliver results in stimulation artifacts that are a million times larger than the signals that we observe. For example, we observe signals in the microvolt range. Stimulation is in the volt range. So the requirement to do this is to have an amplifier system that can tolerate these high inputs, and also a technique that allows you to remove these stimulation artifacts and properly perform statistical analysis on the resulting effects. So what you see here in this pipeline is what you need to perform. So you have the stimulation, then you record data from these electrodes, and you can see these huge recorded stimulation artifacts. You have to remove these artifacts carefully without inducing any filter artifacts or artifacts that can result in filter artifacts. Then you can, from that, extract features, in this case, the broadband gamma power after the stimulation in the following 100 milliseconds. You can then visualize the effect of the stimulation, and you can perform statistical analysis across these hundreds of stimulation pulses that you have delivered and determine whether this stimulation results in a functional activation at distant sites. So this is basically our demonstration of this. So in this case, on this subject, we stimulate the tip of the temporal lobe, indicated here by those red dots. And as you can see, this is the functional activation as it traverses throughout the brain. So this is really a short, brief period of time. It goes from the following 20 milliseconds after to less than 200 milliseconds after that. So this is not volume conduction. This is evoked cortical activity in response to this single pulse stimulation. When you do appropriate stimulation analysis, you will see that identify a particular location in the sequence in which they are activated. So thereby, we can do a functional connectivity analysis, allowing us to determine, using single pulse electrical stimulation, how the brain is connected. Here's another study in which we were interested in the effect of areas within the cortical network. So this is stimulating now a subject on the right temporal lobe. So this rectangular feature here is the right superior temporal gyrus. This is the Sylvan fissure. This is kind of like the central sulcus. So we'll stimulate electrodes on the superior temporal gyrus. And as you can see, the entire network within the superior temporal gyrus gets then activated, but not electrodes outside of that. We further investigated that to see whether there's a correlation between the activation that we find in response to single pulse electrical stimulation and that's to natural auditory stimuli. So we have a battery of different auditory stimuli, nature sounds, environmental sounds, and so forth. And we also stimulate the same subject with single pulse electrical stimulation at various sites. So when we perform an analysis of that, this is kind of like the correlation we see. So we see sites that elicit a response to the auditory stimulus, and we see sites that elicit a response to the single vector stimulation. And if we do this across subjects and across various different stimulation pairs, what we find is a very strong correlation between the responses of these electrodes and the locations. So this tells us that basically we can determine functionally connected areas by stimulating one of these electrodes of this area. Another application that we were interested in is now median nerve stimulation. So this is now not stimulating the brain directly, but the median nerve. In this case, the median nerve innervates a big portion of the hand. And what we were interested in is the somatosensory evoked potentials that are elicited through the median nerve stimulation, or evoked through the median nerve stimulation. And we were interested in two aspects of that. The polarity of these potential, because it has been known for a very long time that they can delineate basically the central sulcus. Basically, whether there's a positive or negative peak indicates whether this is pre or post central sulcus. But also, we speculated that they also induced a functional response, pretty much similar to what I've shown you before. So we looked at the broadband gamma response to this median nerve stimulation. And so what you see here is now a result from one of the subjects that was stimulated that way. So you can see here the central sulcus as determined automatically by the polarity reversal in the evoked potentials. But also, when we do further analysis here, and again, this is like really above, right onto the motor cortex. Okay, when we perform another analysis, just looking at the time frequency analysis of the broadband gamma activity. So you see here from 70 to 240 hertz, the 0 to 20 milliseconds after the median nerve stimulation, we see a not very specific stimulation artifact, but following that, a very specific functional activity of the cortex. And when we perform control analysis in which we perform vibrotactile stimulation, kind of like induce sensation and movement into the innervated area, we can see a very strong correlation between the two, indicating that median nerve stimulation can be used not only to delineate the central sulcus, but also to determine the functionally activated area. So a couple of conclusions from my talk. So electrical cortical stimulation to directly interact with the nervous system can be delivered through short bursts of electrical stimulation. You can either elicit an effect or inhibit function. You can also perform single pulse electrical stimulation for more scientific endeavors. This has clinical utilities using nerve stimulation or scientific utility for human brain mapping. So with that, I would like to give credit to the people in my laboratory and my collaborators, both at my old institution at Auburn Medical College and my I've recently joined the Department of Neurosurgery at Washington University, and also to all these sponsors that provide funding for these endeavors from NIH and the U.S. Army Research Office and Fondazione Rome. With that, I have concluded my talk, and I'm open for questions. Thank you.
Thank you very much. Very wonderful talk. Any questions from the floor? Yes, we got one question. Are behavioral outputs consistent across patients if you stimulate the same brain area?
So on the growth scale, yes. So if you basically say this is hand motor cortex, and if you basically say, okay, this is the expected behavior, yes. But once you go into a more fine-grained analysis, once you look at the anatomy underlying, even if you account for variances in the anatomy, you will find quite a variance in the response. We noticed already from the passive recordings using ECOG that our cortex has a very fine-grained organization.
Thank you very much, Peter. The time comes. So let's move on to the next presentation. Thank you.
Thank you.
Our next speaker is Sulaiman Ben-Smaia from the University of Chicago, United States. Title of his presentation is a biomimetic approach to artificial touch. So Sulaiman, go ahead, please.
Yeah, hi. This is probably the earliest talk I've ever given, so keep that in mind while judging my performance. So before I get started on the topic, I just want to introduce myself and to kind of frame what the rest of what I'm going to say. And what we do in my lab, most of the people in my lab work on is it falls under the coding. And the idea here, I'm going to give you, we're interested in the senses of touch and proprioception. And I'm just going to give use touch as an example. The idea is when you grasp an object or you manipulate an object, there's a pattern of deformation of the skin that produces a pattern of activation in the nerve, here denoted by these these colored rasters, and different colors correspond to different types of nerve fibers that respond to different aspects of these skin different deformations. And then this neural activity in the nerve then propagates down the neuroaxis, ultimately giving rise to a percept of this object. And when we hold an object in our hand, we have information about its shape, its size, its texture. If it's moving, we have information about that, and that's all coming from these signals from our hands. And so, what we're interested in my lab is to try to understand how is this information multiplexed in the nerve. So, all this information about the texture and the shape and all that stuff, it's the same neurons that are carrying it, and somehow we can disentangle these kinds of information stemming from the nerve, and as it propagates along the neuroaxis. And what we're interested in is coming up with quantitative models that relate not just the stimulus and the pattern of neural activation it evokes, but also how patterns of activation along the neuroaxis give rise to perception. So that's what we spend most of our time doing. And so our neuroprosthetics effort relevant to this conference consists of taking what we've learned from this, the code, touch and tactile and proprioceptive coding along the neuroaxis, and try to leverage that to develop ways to restore the senses of touch and proprioception, where we focus on touch. My colleague coming up next works on proprioception. But we try to leverage what we've learned about how touch is encoded in the intact nervous system to try to restore it to patient populations who have lost it. So for instance, amputees who have lost their hand, and so they're equipped with bionic hands, and we want to restore the sense of touch through these bionic hands via nerve interfaces, or tetraplegic patients, typically with a spinal cord injury, for whom peripheral nerve interfaces are not an option because they're no longer connected to the central nervous system. And for those subjects, we work on cortical interfaces. And I'll be talking mostly about peripheral nerve interfaces today, but just to kind of show you to show you the bridge to the upcoming cortical interfaces. Okay, so first, before we get into the neural engineering, you might ask yourself, why are we going to spend so much time and effort trying to restore the sense of touch? And this is a movie I made of me doing stuff with my hands, and most of it is very mundane stuff like picking things up, writing with the utensil. And the idea is that anytime we're doing anything with our hands, we have this barrage of sensory signals coming back from our hands that tell us about the hand state and about our interactions with objects. And without these sensory signals, we would struggle to do anything with our hands. And let me just show you, let me prove that to you. This is a movie made by my colleague Roland Johansson at Umeå University in Sweden, of a lady lighting a match, no problem. Moments later, the same lady is going to try to light this match, but her fingertips have been numbed with a local anesthetic, and you can see that suddenly she struggles mightily to do this task. She drops one, she realizes she's not going to be able to pick it up, and then after a long struggle, she manages to light it. But what's remarkable is that she's going to continue doing this for a while, and she's going to continue to be really bad at it. And that's because you just cannot restore, or you cannot compensate for the loss of these tactile signals with vision. And here's another case. This is an individual who suffers from a neuropathy that has destroyed his somatosensory system, or at least his somatosensory nerves. So he has an intact motor system, but he can't feel his body. He lacks the senses of touch and proprioception. And you can see he's doing something even easier than lighting a match. He's trying to grab this coffee cup and bring it to his mouth, and he struggles mightily to do even that. And that sort of, and if I showed you this movie and I asked you, what do you think is wrong with this person? You would think he has a severe motor impairment, and it really highlights the yin and the yang between the motor and the sensory systems, where really one does not work without the other. And therefore, in the context of prosthetics, if you want to create a prosthetic limb that is endowed with the dexterity that our limbs confer to us, you need not only to have a sweet robot and an awesome way to control this robot, but you also need to restore the sensory signal. So this is, just to kind of orient you, I'm sure most of you have seen stuff like this, but this is my colleagues at the University of Pittsburgh. So you can see there is a tetraplegic patient, Jan, who's controlling this robot by thought. And the idea is you read out signals using chronically implanted arrays from primary motor cortex, the part of the brain that sends signals to the muscles. And you can, from these signals, infer what the intended movement was, and then you can make the robot do whatever that intended movement was. And so to Jan, the way she experiences this is that she is trying to move her own arm, which is paralyzed, and she can get this robot to do whatever it is she wants. And if you're watching this, you're like, well, this is pretty cool. If you're watching this for the first time, it's a pretty great achievement. But now, if you're watching this for the 1,000th time, you'll probably think to yourself, well, you know what? I would be way better at this task than she is. But she's about as good as this gentleman I just showed you a minute ago would be doing this task, right? He struggles to do the coffee cup. He would struggle doing this grasp and transport task. So this highlights the fact that if you want to, it demonstrates that there's something missing without the senses of touch because she can't feel anything. Now, a subsequent subject, Nathan Copeland. First, let me describe briefly how you would restore the sense of touch. So the idea is when you grasp or when you're contacting an object, the skin deforms. It activates nerve fibers in the skin that innervate the skin, and these signals travel up the arm, short distance up the spinal cord, ultimately culminate in a pattern of activation in somatosensory cortex. So this is the part of the brain that receives touch input from the body. And that pattern depends on what you touch and how you touch it. So these prosthetic arms or hands have sensors on them. And what we work on is to convert the output of these sensors into patterns of electrical stimulation of the brain to reproduce, to the extent possible, these natural patterns of activation, right? Or at least produce patterns of electrical stimulation that produce patterns of neural activation that are intuitive, that the subject can use to guide its manipulation with objects. So this idea now has been, and usually I spend a lot of time describing what happens up to this point, but I'm just going to tell you what the future holds instead. So this here is on the left side is the video that I showed you earlier, which is Jan moving these objects, and on the right side is a more recent subject at Pitt, Nathan Copeland, who's doing the same task, but the sensor output on the hand is converted in real time into electrical stimulation of somatosensory cortex, so that when he reaches to grasp an object and make contacts with the object, he actually can feel the object through the bionic hand. And I don't have the data here, but this stuff is published. So if you don't believe me, you can check it out. But Nathan does significantly better with the sensory feedback than without. So there's another condition comparing his performance when you just turn off the sensory feedback, and he's much slower at doing this task. And of course, as you would expect, when you're grasping an object and you can actually feel the object, like I showed you earlier, this confers a lot greater dexterity. But this is the Gen 1. And in these Generation 1 sensory encoding algorithms, and this is all of the sensory encoding algorithms that have ever been used in a cortical interface, consisted of taking the output of the sensors and then modulating the amplitude or frequency of stimulation of the brain, right? So you're just basically tracking the pressure on the sensor with your electrical stimulus. And what I want to spend the rest of the time talking about is, how we can do better than that, and how and what we expect to happen when we do. So I opened this talking about cortical interfaces, but what I'm, and the idea there is to have, to take the output of the sensor and produce patterns of electrical stimulation of the brain. But I'm going to talk now a bit about how to restore touch in amputees, and the reason why is because that work is sort of more advanced than its cortical counterpart, and therefore can serve as this roadmap of what we expect to find in the brain-machine interface, on the brain-machine interface side. So the idea here is, with amputees, the nerve that used to innervate the hand is still intact. So what you can do is interface with that nerve. And when you electrically stimulate that nerve, you can produce this has been shown now many times, you can produce very vivid tactile sensations that are projected to the hand. So subjects feel something coming from the hand that they know is no longer there, and it's very vivid. And so you can use that phenomenon to restore touch. So this is my colleague Dustin Tyler at Case Western University, just to show you kind of the Gen 1 algorithms here, where again, there are sensors on this hand that convey to him a sensation of touch that is modulated by how much pressure he's exerting on these very fragile objects. And you can see how remarkably well and accurately and precisely he can modulate his force, which he could not do without this tactile feedback. But so that was Gen 1, but I think a lot of progress has been made on the sensory encoding algorithms, and I'm going to try to tell you a little bit about that. So first, before I do, let's think about what are the neural correlates of natural touch. What happens when you're actually interacting with objects? Well, you have something like 12,000 nerve fibers that innervate the surface of the hand. And anytime you touch anything, all 12,000 of these nerve fibers are going to respond differently to that touch, depending on what type they are, where they are relative to the contact events, etc. And so you have 12,000 independent channels of information telling you what's going on when you interact with an object. And that's why the sense of touch is so rich and so useful when you're interacting with objects. Now, if you wanted to restore the sense of touch perfectly through a nerve interface, how would you do it, right? Well, what you would need is 12,000 stimulating channels, each selectively stimulating or activating a single nerve fiber. And then if you knew exactly how that nerve fiber would respond during an interaction with an object, you could just kind of electrically activate it to reproduce that natural pattern, right? And if you did that, you would restore touch perfectly. People would feel like, wow, this is natural touch. The unamputated hand and the amputated hand would basically feel the same. Of course, this is predicated upon technologies that don't exist and probably never will, upon sensor technologies that don't exist and probably never will. But this is kind of ideally, this is what you're shooting for. So while the technological component of that is just nowhere near there, the scientific bit, understanding the relationship between patterns of skin deformation and patterns of activation is. And so why are these slides here? Okay. And this is a model that we've been developed, that we published now in 2017, but this is the culmination of something like 20 plus years of work. And it's a model that what it does, in brief, again, this is published if you want to check out the details, but what it does is you specify a stimulus and it describes how the skin would deform given that stimulus. And it tiles the skin with mechanoreceptors at their known densities. So there are, multiple kinds. There's three main kinds of mechanoreceptors and mechanoreceptive afferents that innervate the palmar surface of the hand. So we innervate this virtual hand with all these nerve fibers at their known densities. And then we can predict, using a pretty simple model, it's an integrated fiber model, a pretty simple model, how each of these 12,000 nerve fibers would respond given this stimulus, given this pattern of stimulation of the skin, right? So what you on the input side, what you have is the stimulus. You just tell it what is the stimulus, and on the output side, it would say how all 12,000 of these nerve fibers would respond to that stimulus. And when you do that, again, this is just to show you that this model works. And so this is the rate predicted by the model versus the rate measured in real nerve fibers. And you can see that the model can predict very precisely how natural nerve fibers would respond, not just in their strength. So you can see these are really hug the unity line, but also in their timing. So if you know anything about mechanoreceptive afferents, you know that they respond in very precise ways. If you present the same stimulus over and over again, they will give you a very precisely identical response in time, right? And so what we show is that this model can reproduce with essentially millisecond precision the response of each of these nerve fibers. So now you have 12,000 nerve fibers, and you can reproduce with millisecond precision their responses to any stimulus that you can come up with. So let me just illustrate the sort of the model, show it to you in action. So here, for instance, you specify an indented edge into the skin. The blue, or this surface here, shows you how the skin would deform. There's a model of skin mechanics that shows how the skin would deform given the stimulus. And then on the right, it shows you how all 12,000 of these, the nerve fibers that innervate the fingertip would respond to this. So I don't show you the entire hand here, I just show you the fingertip. So for instance, you can see that RA and PC afferents only responded during the indentation and retraction phases, whereas the SAs respond throughout, et cetera. So it really gives you a detailed representation of how all the nerve fibers would respond. Here's now an example of textures. When you scan textures across the skin in different directions, you can simulate how each of these nerve fibers respond to that. And I'll just mention in passing, before I go back to the neuroprosthetics, that this is a potentially very useful scientific tool, because now, instead of having to painstakingly respond or record from individual nerve fibers and create populations and then try to understand how information is encoded in these populations, you can just simulate. You just give it a stimulus, you simulate the response to that stimulus, and then you can see how the information about that stimulus is encoded. So I'll give you an example of a paper we published last year of how that can be really useful and save a lot of time. There was this idea, actually by Roland Johansson, whose movie I showed you earlier, that, so first, in touch, there was this long-standing idea that, when you grasp an object, the geometry of this object, the local geometry of this object is encoded in space, in the spatial pattern of activation, kind of like in the retina. When you look at an A, you get an A-shaped pattern of activation in your photoreceptors. Well, if you press your finger across an embossed A, you get an A-shaped pattern of activation in these mechanoreceptive afferents. And the idea is that's how information about local geometry is encoded in the nerve. So this was the old idea, right? Now Roland made a great point that when you're interacting with objects, you need to really have this tactile information rapidly. You can't just wait 200 milliseconds to figure out what the shape of something is. And he suggested that this spatial idea did not work because it's too slow. You have to kind of integrate over time. But what we were able to show, but this was basically a theoretical idea, right? Because no one has ever recorded from every single nerve fiber in the nerve. But what we did is simulate the responses of every nerve fiber in the nerve. And what we found is that in fact, the spatial information evolves very quickly. So for instance, this is showing how quickly can you figure out what the orientation of an edge indented in the skin from these patterns of neural activation. And we showed that you can do that within like 30 or 40 milliseconds. So very, very quickly, and much quicker than you might have thought if you were, if you listened to Roland, who suggested that you had to integrate this information over time. And the reason why is because you integrate over space. When you have so many densely packed receptors, actually that information evolves much faster than you would have thought. And this is something that we were able to discover and show with this simulation. Okay, now back to the prosthetics. So again, in a perfect world, we would have the model that takes the output of sensors and converts them into pattern of activation of the nerve to really reproduce touch in all its glory. But the reality is, we have a few sensors on the hand, and we have only a handful of stimulating channels, maybe up to 100 if you're really generous, but that's still orders of magnitude fewer than there are nerve fibers in the nerves innervating the palmar surface of the hand. So my student Lisa Okorokova and Shinpu He and I developed a way to sort of create a simplified model of how the nerve responds. Rather than trying to reproduce each nerve fiber's activity individually, what we wanted to see is how do populations of nerve fibers respond to stimulation of the skin. And that, when you're stimulating, you're not stimulating a nerve fiber at a time. You're stimulating a population of, let's say, hundreds of nerve fibers. And so what we want to do is simulate how these hundreds of nerve fibers respond so that we can control, or we can know how to stimulate these populations, at the level of fascicle. So first, what we showed is that we developed a very simple model that has that it's a linear model with a handful of parameters, and it can reproduce the aggregate activity that is simulated using the full model very accurately. So here, the black. So this is just during activities of daily living with a sensorized glove. You can see the force traces in these color traces up here, and then the black is the full model. How well can you predict the responses, the nerve responses using the full model, and the color traces are how well can you estimate or approximate that full response at the population level using the simple model, and you can see it's very, very well. It's well enough, right? And so then this approach has now been deployed with actual subjects, where again you use this model that I just showed you to take the output of the sensors and convert them into patterns of electrical stimulation of the nerve. And when you do that, a bunch of cool stuff happens. One, the stimuli the stimulation feels more natural, right? So you compare a flat train that is typically used to these biomimetic trains, and they feel more natural. That's shown here. This was published in Sylvester Macher's lab in 2018. But they also confer greater dexterity on you, and I'm showing you one example, and this is the fragile object transport task, where you're just trying to transport a bunch of fragile objects without breaking them, and you can do better with these biomimetic trains than you can with just the standard trains. So it's not just that you're better with the touch than without, you're better with this biomimetic touch than with the standard touch, which just tracks the pressure. So that's promising, because what that means is when you're speaking the nervous system's natural language, when you're given the central nervous system the signals that it expects given interactions with objects, things feel better, feel more natural, and the resulting sensory feedback confers greater dexterity, right? Another thing so the second image here, although Sylvester also showed that you're better at the fragile object task, but in this case you can also, for instance, perceive the compliance of objects better with this biomimetic feedback than without. So it just gives you more information about the objects, more information about the contact events, and it feels more natural. So the reason I went through all this kind of side story about peripheral nerve interfaces at a BCI meeting is because we published another paper this year or last, I forget, where we looked at contact events during in the nerve and in the brain, and we found that at the aggregate level, at the population level, the nerve activity mimics the brain activity. So the same exact model can be used for sensory feedback in the nerve than in the brain. Looks like I'm out of time, so I'll just mention one last thing. I was going to say some cautionary notes. Just to kind of link it more to the general tenor of this meeting. So here we're talking about restoration of touch, and maybe a lot of you don't care about restoration of touch, but the sorts of approaches that we're using to stimulate the brain to try to reproduce natural patterns of activation, basically what we're doing is writing information into the brain through electrical stimulation that is interpretable, right? And so once as we improve our ability to do that, you can start expanding the scope of that. So you can, maybe write in different kinds of sensory information, or writing memories, or writing any kind of thought. So the long horizon, sort of the Neuralink, Elon Musk's sort of horizon of this kind of work is to learn how to better directly write information to the brain. This is my lab, and sorry I went a little over.
Thank you very much. A very impressive talk. I know we have a bunch of questions in the Q&A box, but the time is limited. Please answer to the first question only, and then please answer the rest of them afterwards by the text messaging manner. So the question is from Dr. Mark Ratash. Are there attempts to incorporate efferent contribution to perception, efference copy, into haptic perception and the BCI?
So no. And the reason why I think the idea is, and of course, this is sort of a first order answer to this question, but the idea is that you are, trying to control this limb using the natural language of the motor system, right? You're imagining moving your arm in the way, and that's what moves the arm. So, in principle, then, to the extent that there's efference copy, is involved on the perceptual side, that efference copy should be essentially preserved, right? Now, as somebody who's been studying the somatosensory cortex for a very long time, and this is the structure that we're interfacing with, I have never seen any evidence of efference copy there. And we're actually right now looking in primates, right? So now we're looking in detail to answer that question. But there's a lot of questions about how, and if you were to, what is an efference copy? How is it represented on the sensory side? Obviously, it does play a role in perception in intact individuals. I guess my first order answer is we expect that to be given for free, given that we have sort of biomimetic control algorithms implemented.
Thank you very much, Sulaiman. Please answer to the another question by typing manner later on. So thank you very much. So let's move on to the next speaker. The next presenter is Dr. Lee Miller from Northwestern University, United States of America. And the title of his presentation is Adapting Brain-Computer Interfaces to Real-World Behaviors. So please, Lee.
Okay, can you see my shared screen properly?
Yes, but could you share your slide? Actually, it's
hasn't started.
No, it hasn't started yet.
I thought I did.
The video and the voices are nice, but yeah.
Here we go.
Oh, here it comes.
Is that better?
Good.
Okay.
No, good. it's a presenter screen, and it's yes. Please click there. Yes, okay. Perfect. Good.
So appreciate the invitation. Good morning from Chicago, and good evening, I guess, to any of you who are in Russia. I often like to start my presentations with a picture that's local, and in fact, this one comes from the last year meeting when Ilya arranged an outing for several of us to the Caucasus Mountains in the south of Russia, which was great fun. And this is a picture of several of us standing at the top of a peak of some sort. They're a little too small to see, but if you look closely here, you can see that there's our driver here on the left, and Ilya and Fabian and Morgan and me. Misha doesn't show up anywhere. He thought we were nuts, and so he stayed behind and he took this picture, fortunately. So I want to tell you about our efforts to adapt brain-computer interfaces, in this case motor interfaces, not the somatosensory ones that Sleeman was just talking about, to activities in the real world. Now, obviously, I don't mean mountain climbing, but what I do mean is using your hands for the kinds of activities that we might do, or that a spinal cord injured patient might do throughout the day in trying to do the sorts of activities that you and I do naturally. This is a clip showing the basic approach that we are taking to effect movement. This is using what's called functional electrical stimulation, and this particular clip comes to me by a colleague at the Cleveland FES Center, which is one of the world leading institutions doing this kind of work. This patient has an injury at about C5, so that means that his hand is paralyzed, and it's insensate and he cannot move it, but he still is able to move the proximal part of his limb. In this case, there are sensors, both implanted EMG sensors on the shoulder muscles and a mechanical joystick sort of thing at the shoulder that sense the movements of his shoulder, so that as he lifts his shoulder, it causes a pre-patterned
pre-programmed pattern of electrical stimulation of electrodes implanted in the muscles of his forearm and hand that cause his hand to close, essentially like this. You'll see here he lifts his shoulder, and this causes his hand to close. The moment he drops his shoulder, this causes his hand to open. So this provides significantly improved function for patients like this. It's been implanted in about 300 patients, but it requires significant cognitive burden to literally use the same muscles to control the position of the hand in space as to open and close the hand. It's a single degree of freedom control, and it's entirely pre-programmed, so the patient can basically just turn it on and off. What we have worked on over the last number of years is a similar kind of system that's controlled not by physical movements of the shoulder, but by recordings from the brain, using the typical kinds of brain-machine interface approaches that many speakers have talked about so far. But instead of controlling the kinematics of a robot or the kinematics of a cursor on a computer screen, we actually control the contraction of individual muscles. And this is the way that experiment works. This diagram was made in a Nature publication a number of years ago, but it describes the essence of what we are doing, and I'll tell you then how we're extending that. We record from the monkey's brain, and then in this case, the hand area of the motor cortex. We use those recordings to make predictions of muscle activity, much like anyone else makes kinematic predictions. Then we use those time-varying predictions of multi-muscle activity to drive a multi-channel stimulator, which stimulates the muscles and causes them to contract. We do this in the presence of a peripheral nerve block, so this allows us to temporarily paralyze the monkey's hand, and during this period, we do these experiments. And this is a clip showing this sequence. The initial couple of reaches that the monkey makes are during this nerve block, at which point his hand is paralyzed. Although, as in the patient that I showed you, he can still move his shoulder and his elbow completely normally because the location of the peripheral nerve block is at the elbow. And this is what it looks like. So these first couple of attempts are when his hand is paralyzed. You can see he can't grasp the ball, although he can reach toward it. And presumably, the neurons active in the hand area of the cortex are active as they normally are, as he's trying to grasp. Now we've turned the prosthesis on, and you can see he can use his hand, not by activating those muscles through the spinal cord, but in fact, through the computer and the electrical stimulator. So this was a basic proof of principle that we did a number of years ago. It used a relatively small number of electrodes on muscles, and it was limited to a very small range of motor activities. This particular one we chose because it does represent a natural kind of grasping behavior that might well be useful to a patient, but it's rather limited in scope. So what I want to talk to you about for the rest of this lecture is not the details of this brain-controlled FES, but it's our subsequent experiments to look at how different kinds of motor behaviors are represented within the brain. And we're doing this now wirelessly within a large cage that the monkey can move about and perform a variety of unconstrained motor behaviors. This is a picture of the cage, and on the right are the number of people who have been involved in these experiments over the years and currently. And you see this cage here, which contains apparatuses on the left that allow the monkey to do the lab kinds of tasks that we're used to doing, power grasp, button pressing, and so forth. And this panel here allows the monkey to push a button and get a water reward, as in the cage. On this side of the cage, we have a proximity sensor, so we can tell where the monkey is within the cage. And one of the things we ask him to do is simply walk back and forth in the cage. And that's what's demonstrated here. What makes this particular behavior more interesting, in addition to the button pressing at the one end, is the power grasp that the monkey makes as he walks across those bars. We can also give the monkey treats to play with. Here he's foraging for food inside this paper bag, also filled with paper. And here we're simply handing the monkey treats that he can grasp using precision grasp. So you get a sense of the broad range of activities that the monkey does in this cage that we can record from wirelessly with an implant you can no longer see on his head, which is the BlackRock wireless transmitter. and also a separate transmitter that's housed in this backpack that streams the EMG recordings. This is simply a diagram of the whole system, the wireless recordings of Cortex and EMG that I've talked about already, and we can substitute within that backpack a wireless stimulator to do our FES experiments. Although the experiments that I'm talking about today use a system to record EMG rather than stimulate muscles, but the basic design here is very similar. This figure shows the three kinds of behaviors that I want to talk about for the rest of the talk. Power grasp, as we would do in the lab, the crawling task, which I described, including the grasps that the monkey makes on these poles, and a precision grasp, which requires a different shape and a more complex control of muscle activity than does the power grasp. Below these pictures are shown the rasters recorded from electrode arrays implanted in the hand area, and also EMG signals coming from mostly forearm and intrinsic hand muscles. And this is a limited set of the muscles that we are able to record at any given time. What I want you to notice is each of these tasks causes activity in the brain and in the muscles, and it allows us to look at the relationship between the brain activity and the muscle activity and ask whether or not the mapping or the relationship between brain activity and muscle activity remains the same across these different motor behaviors in different contexts. This work that I'll be talking about subsequently is largely done by a postdoc currently in my lab, Xuan Ma. So I need to take just a little bit of a divergence here from the main theme to talk about something that's actually rather close to the talk that Misha gave, although I promise I will not be talking about any twirly kinds of things here. But I do want to talk about the concept of a high-dimensional neural state space, which is indicated here. In this case, these are recordings that are made as the monkey's doing what we refer to as a center-out task. He grabs the handle of that robot and simply makes movements in one of these 8 directions. These peri-event histograms show the modulation of 9 different neurons that I've chosen because they're representative from the larger set of roughly 100 neurons. These traces here show the trajectory. In this case, the monkey was moving up or away from him and to the right. What I want you to notice is a number of neurons do largely the same thing. And if you look at these 2 here in particular, these are the prototypical Georgopoulos-like neurons that Misha also showed us. They become active about 100 milliseconds before the onset of the movement, which is shown by this green dashed line. And the firing activity persists throughout the movement. And at the end of the movement, as the hand is in a different position, it has a slightly different firing rate than it did at the beginning. And these 2 are doing almost exactly the same thing. Here's a neuron that's doing almost exactly the opposite thing. So again, Misha showed us this. There are neurons with preferred directions pointing in different directions. And in this case, the movement was in the anti-preferred direction. Here's a neuron that came on a bit later. Here's a neuron that came on and stayed on for quite a long period of time. And here's a neuron that shut off, but then became more active. So what I'd like you to take from this set of images is, 1, a bunch of neurons do essentially the same thing, and this gets at the idea of a low-dimensional representation of movement by redundant neurons. But then there are also groups of these neurons doing different things. So how can we think about that more effectively? This is a diagram that I borrowed from Mark Churchland, in which we describe this neural state space. In this case, it's simply a 3-dimensional coordinate system, and each of the 3 axes represents the firing rate of one of 3 hypothetical neurons. So think of them as any 3 that you might pick from this group over here. Depending on the firing rate of these different neurons, the overall activity can be represented at some location within this 3-dimensional space. So a rightward reach might be located here, while a leftward reach that's accompanied by different firing rates in these 3 neurons would be located in a different space over here. This is 3 dimensions. You can imagine, although I can't draw for you, a 9-dimensional space like this in which the location of the neural activity is determined by the firing of 9 neurons. But You don't need to stop there. You can think about the 100 neurons that we can record, making a 100-dimensional space. And of course, we can also think about the million-dimensional space that is represented by the full number of neurons in this part of the brain. This gives us some mathematical tools to look to see how the firing rate is represented at any given point in time, and also how it evolves over time. And I'll show you another example here that comes from real data, not cartoons. At the top here, and this actually is a recording from somatosensory cortex, although it doesn't actually matter. Here we're recording 40 neurons, 41, and we would periodically bump the monkey's hand in one of these 4 directions, shown here by this key at the bottom. As the arm was bumped, we would count the number of action potentials, or the firing rate of action potentials, from each of these 40 neurons. So you can think about this as a location within this 40-dimensional space that I just described to you in the previous slide. And then we can ask, where does the activity move within this neural state space for these different bumps? Now, again, I can't plot that 40-dimensional space for you other than with these rasters, but I can use principal component analysis, which again, Misha described for us in the second talk of this session, to reduce the dimensionality of this 40-dimensional space. And I'm going to do that down to 2 dimensions. And when I do this, I get a plot like this. So this is analogous to that 3-dimensional cartoon that I showed you, but these are real data. These are the locations within this 40-dimensional space projected onto 2 primary axes. And you can see that the brain evolves or moves 2 clusters of points in these 4 different locations as the hand is bumped. This is just a static snapshot of the brain activity at the peak of the response to this perturbation. But as I said, we can also look at the time evolution of these signals. This is a movie clip, which is done exactly as this static picture is done here. Each of these dots, which I didn't say previously, represents the result of 1 perturbation. Here it's a static snapshot. Here I'm going to show you a clip of the evolution of this. So essentially I'm showing you about 100 perturbations at the same time. You'll get the idea looking here. Here, the brain state is just kind of randomly changing, leading up to the bump. Here comes the bump, and you see the brain state flying apart in these 4 different directions. But you can see the evolution of that brain state forming. So these are what I'm going to refer to now as latent signals. They're signals that we can extract from the firing rate of neurons, but in fact, we think that the latent signals are the fundamental component and that they ultimately cause the firing rate of these neurons that we record. And we can look at those and learn some interesting things about how different behaviors are represented in the brain. Now, this is another way of looking at the correlation between, in this case, different muscles, and I'll show you different neurons in just a moment. In fact, this is literally the pairwise correlations between a bunch of different muscles that we recorded during these different behaviors. If you look closely here, you see there's a cluster of rather well correlated neurons here, also here, and down here. This matrix and all of the other matrices were sorted according to a clustering algorithm that clustered these similar neurons together. And what I'd like you to notice is, if we compare power grasp, and that's power grasp in the lab, and the power grasp the monkey does by grasping the rods, the patterns of muscle activity in this spatial sense look quite similar to one another. But if we compare either of these 2 power grasps to the precision grasp, the patterns of muscle activity are rather different, because as I told you, the precision grasp requires a different set of muscles to be active than does the power grasp. I can do the same thing for neurons, and now we see something rather interesting. This is exactly the same analysis, but now the power grasp in the brain is represented in very much the same way as the precision grasp in the brain. You see the repeated elements here and here in both matrices. There are some additional elements here that are present here not as strongly, but basically these two matrices look rather similar, and they both look completely different from the brain representation of the power grasp during crawling. So this tells us that the context in which this power grasp is produced appears to be quite important. Now we can quantify this. Instead of just looking at the similarity of these matrices, I can do a scatter plot of each of the elements of these two matrices, which is shown here. So this is a scatter plot of the similarity between the power grasp and the crawling in the brain. And you can see it's basically just a random relationship between these two. If you calculate an R, it's just 0.23. If we do the same thing for the representation of power grasp and precision grasp in the brain, in fact, there's a pretty strong correlation. So this is consistent with what we thought we saw just by looking at the matrices. The two kinds of grasps, despite their different EMG patterns, are represented rather similarly in the brain. And the power grasp, when it's done in two different contexts, is represented quite differently. We can just provide numbers for all the combinations of comparisons between these tasks. And just to reiterate what I just said, in the brain, the two types of grasps, power and precision, are quite similar. In muscles, on the other hand, the power grasp and the crawling grasp are quite similar. So this suggests that there are important differences in the representation of these activities in the brain. And this is another way of looking at what I just said. I claimed there weren't going to be any twirlies, but this is something similar. These are the trajectories that are traced out, just like that bump movie I showed you, when the monkey executes these 5 different kinds of behaviors. 3 of them I've already described, but we also had the monkey picking these treats, and I showed you a video of that, and also executing a wrist movement task. So that you can see the brain state evolves in completely different parts of this state space for these different behaviors. So what implications do this have for our ability to do a brain-controlled FES prosthesis? Here are predictions of EMG activity based on our recordings from the brain for the 3 different behaviors that I've talked to you about. Each of these predictions was made by training and testing on the same behavior. They were cross-validated, which means we used held-out data for these test examples, but they were trained and tested on the same type of behavior. And you can see these predictions are quite good. If we calculated R-squared between them, they'd be in the range of 0.7 or 0.8. On the other hand, if we train on the power grasp and then test on either crawling or precision grasp, our predictions are much worse. The crawling behavior, which includes power grasping, can't be predicted at all. The predictions are terrible. The precision grasp, which I told you was closer to that of the power grasp, we can predict okay, but really not terribly well. This matrix on the right shows us a summary of these within and across EMG predictions. Along the diagonal shows the quality in variance accounted for, which I told you before were in the 0.7 to 0.8 range, for training and testing on the same behavior. The off-diagonal terms represent training and testing on different behaviors, which I showed you work, in fact, I'm showing you right now, work rather poorly. So this has really kind of dire implications, at least for the use of these linear types of decoders, in terms of decoders that will generalize across a broad range of different behaviors, unconstrained behaviors. So we're in the middle of developing much more complicated nonlinear decoders, which I'm not going to tell you about because we're in the midst of that. The take-home message is that, in fact, they work significantly better than linear decoders, but we have a significant distance to go in making them work perfectly well. So this is the summary of what I've told you. We can use cortical activity to predict EMG and to control FES intensity across a range of different behaviors, and it works quite well if we train and test within the same behavior. However, the latent spaces in the brain in which these behaviors are represented are quite different, causing our linear decoders to fail across those behaviors. And we're working now, as I just said, to develop decoders that are more robust across this range of behaviors. And these are funding sources and colleagues that helped with this research. Thanks.
Thank you very much, Dr. Miller. Very wonderful talk. Are there questions from the floor? Yes, we have a question from Dr. Mark Latesh. What do you think about the Feldman's idea that neural population represents not peripheral variables, but the spatial referent coordinates?
Well, with apologies to Feldman and Latesh, I think the neurons in primary motor cortex are very closely related to the dynamics, to the force components of movement. As I've shown you, we get very good correlations with muscle activity, despite the fact that muscle activity itself is a fairly noisy and dynamically complex signal compared to the position signal. If we predict position, actually we can't predict, we can't even measure the position in these complex tasks at the moment, although we're working at it. But even in the lab, when we do rather simple tasks, we can often predict EMG better than the simpler position signal. So for a variety of reasons, I think that these neurons in primary motor cortex, possibly unlike neurons in higher cortical areas, are more closely related to forces and muscle activity than they are to position or to the reference position.
Okay, thank you very much. Our time comes. So thank you very much, Dr. Miller.
Thank you.
So let's move on to the last speech. The last speaker is Dr. Jonathan Walpole from National Center for Adaptive Neurotechnologies, Administration, Veterans Affairs Medical Centers, United States. Title of his presentation is The Substrates of BCI-Based Behaviors.
So thank you very much. I'm really very happy and honored to be here, to be able to join in this meeting. I want to thank Ilya and the other organizers for this opportunity. It's very exciting. I've been really very glad to be able to see the previous presentations. They really relate to a lot of what I want to say here, and I was happy to see that these very distinguished previous presenters agree with me in many of the things I'm going to say. So I want to talk about the substrates of BCI-based behaviors, the substrates in the nervous system that are responsible for these behaviors. So what is a BCI? What is a brain-computer interface? I want to start out with a very specific definition that the central nervous system produces behaviors that serves the needs of the person. This, as far as we understand, is what the nervous system was evolved to do. Over millions of years, that's what it's adapted to do in each of us. All its natural behaviors are produced by muscles. A BCI, instead of using muscles, a BCI measures central nervous system activity and converts it into non-muscular behaviors that replace, restore, enhance, supplement, or improve natural behaviors. This is the basic picture of a BCI. Signals are acquired from the surface of the scalp or from the surface of the brain or from within the brain. They're acquired, they're assessed to measure specific features, and these features are translated into a variety of kinds of applications. They can replace normal function. They could restore normal function with FES, as you were seeing in a number of the presentations. They could, in theory, enhance normal function by basically supplementing what occurs during normal behaviors to make these behaviors better, to enhance them. They can supplement by adding additional behaviors, such as the control of a third arm. And most finally, and I'll emphasize this increasingly as I go along, they can be used to improve behaviors, to aid in rehabilitation after strokes, for example. So it's important to realize, and Dr. Lebedev brought this out also earlier, that BCI uses a new kind of behavior. People like to think about BCIs as mind reading, but they're not. What they do is they offer the CNS the opportunity to develop a new kind of behavior, a behavior that's not based on muscles. Like natural muscle-based behaviors, BCI-based behaviors are learned. They're acquired through practice. This is illustrated here in a study now almost 20 years ago from Dawn Taylor and Andy Schwartz's lab, showing a monkey who over a period of days is using cortical neurons to control movement of a cursor on a screen to targets. And you just see here that the targets get smaller. The targets that the monkey's able to hit get progressively smaller as the animal learns better control, as he acquires control of this BCI-based behavior. This is a more recent study from Perdicus and Jose Millán's group of two paralyzed patients who were learning a BCI-controlled video game over a period of months. And this shows for each of the patients how the control improves. You see more and more yellow over the months as their brain control of this task, of this simple video game, improves. Again, this is a behavior, a BCI-based non-muscular behavior that they're acquiring. So how does the central nervous system acquire and maintain this new kind of behavior? I want to start with a related question. If we want to understand how the central nervous system acquires and maintains this new kind of behavior, it would be good if we understood how the central nervous system acquires and maintains natural muscle-based behaviors. Now, over the past 40 to 50 years, our concept of how the central nervous system functions has changed enormously, primarily because we become aware of the fact that the central nervous system is changing continually throughout life, that all parts of it are continually changing. This is a huge change from the view, say, 50 years ago in 1970, which was around the time that I became involved in science, in which point it was thought that the central nervous system was really very hardwired. It could change very little and only in very limited ways. We now know that this is not true. The CNS changes throughout life through many different mechanisms: neurogenesis, gene activation, neuronal properties change, there's synaptic changes, long-term potentiation and depression, glia change, dendrites change, there is excretion of hormones that changes, there's axons sprout, all vascular changes occur as well. All these things combine to allow the CNS to acquire and maintain behaviors. And the other thing that's become clear in recent decades is that the CNS substrate of a behavior is distributed. It can extend from the brain to the spinal cord. This is a recent study of an fMRI study of the brain activity that develops when a person learns a simple motor sequence task. So there are changes that occur at multiple levels in the cortex, subcortically, and even in the spinal cord. So that this very relatively simple motor control task depends on plasticity occurring at multiple locations. It's a distributed pattern of plasticity that produces this new behavior, this skill. Now, in my group, we've spent now close to 40 years looking at the distributed pattern of plasticity underlying really a very simple kind of behavior. What we've shown is that animals and people can learn to change the size of the stretch reflex. This is the knee-jerk reflex produced by the very simple reflex arc of incoming spindle afferent input, exciting the motor neuron and producing a contraction. So this is the knee-jerk reflex, and we've shown that people and animals can change the size of this reflex. Here it is, the stretch reflex can change the size of it through an operant conditioning procedure. And this is our understanding at this point, relatively limited, but we do have some understanding of what occurs. And this pattern has been developed again over a number of decades. It's primarily the work of Shenyun Chen, Jonathan Karp, and a number of other people over many years now. As we understand it, the operant conditioning reward reaches the inferior olive. It gradually, over days and weeks, produces initial days produces plasticity, this pink, in the cerebellum, which leads to plasticity in sensory motor cortex, which changes descending corticospinal tract output, which produces a small, this is when we're trying to make the reflex smaller, a small decrease in the reflex. And this change stays in effect over days, and it gradually changes many sites in the spinal cord. So the spinal cord itself is changing here, and this leads to much greater change in the reflex. So here's the final change in the reflex, and it's being produced by this really this distributed pattern of plasticity that operates as a hierarchy. The plasticity in the brain guides and maintains the plasticity in the spinal cord. So we recently realized that we need a name for the CNS substrate of a behavior. And at that point, I thought it would be a good idea to follow the model that was first used by Sherrington in the 1890s, and when they needed a word for the newly recognized connection between neurons. And they came up with the word synapse. He acquired that primarily from consulting a Greek scholar at Cambridge, who based this on Greek term for a grasp, for something that holding and grasping. It was developed it was quite a complex process how that was developed. And so I wanted to follow the same model. I contacted Adam Camisar, who's a classical scholar, and with the problem, and he was very willing and very welcoming in terms of addressing it. After some work, he decided that there was a very logical classical origin for what we wanted, that Aristotle and his followers among the Stoic philosophers came up with a term for the physical substrate of a behavior, and they called it a hexis. So we started with this term, and we really were kind of continuing their work because they gave this term to the physical substrate of a behavior. They had no idea 20 centuries ago what that physical substrate was. Now we're beginning 2,000 years later to have something of an idea of what that substrate is. So we really need the word that they developed. So we started with hexis. We wanted to develop from that a word that would not be confused with other things like hexane or hexagon. We wanted a word that would be relatively simple to use and very clear. And what we arrived at after considerable work and discussions with other people was the term hexer. So these are hexers. This is the hexer responsible for motor sequence learning. This is the hexer underlying a operantly conditioned change in a reflex. So hexers share neurons and synapses. They overlap, particularly in the spinal cord and elsewhere as well. They use the same neurons and synapses. Thus, they affect each other. And all these structures from the cortex to the spinal cord are plastic. They're able to change. So this is an example from a study done now about 10 years ago, in which people were trained on a simple foot flexion extension task. MRI was recorded while they performed the task. They then spent several weeks learning a new dance step. They had dance training over several weeks. They then again did the foot flexion extension task, and MRI was recorded during that. So the task looked the same. They were doing the same task, but the MRI, what they looked at was the difference between the fMRI here and the fMRI here. And what they found was that there were differences in the CNS activity underlying the same task. Differences in cortex, a number of places, and also subcortically. So the CNS is producing the same behavior, but it's producing it differently because of this new hexer. So the old hexer is producing its same behavior, but it's producing it differently because of it's accommodated to this new hexer produced by dance training. So a new hexer, here's another example of a new hexer. In this case, reflex operant conditioning. We're changing the size of a leg reflex, affects an old one, locomotion. So here you see a rat walking along on a treadmill. You see the soleus activity. This is in the posterior calf of the right and left as it walks along. You see the muscle activity that's producing the stance as it walks along, right, left, right, left, right, left. A lot of this excitation is being produced by that pathway that we've changed with operant conditioning. So here you have the soleus burst prior to conditioning. Here's down conditioning. The burst is smaller. And here's another animal in which the reflex has been made larger. The soleus burst here during walking is bigger on the side that we've trained. However, walking is not impaired. The animal doesn't start limping. Its step length doesn't change on the two sides. It still walks along just fine. EMG and kinematic changes preserve the key features of walking, the key features of equal of right-left symmetry, the key features of appropriate step length, the key features of stable and equal hip heights on the two sides. So, and this shows how this a part of how this compensation occurs. Here's the rat. You see this is its back right leg. The rat's over here. It's walking on the treadmill. These are the joint angles as it walks along, hip and knee and ankle. So this is what happens. This is before the reflex is made smaller. Now, when the reflex is made smaller, this ankle angle gets smaller as well because there's less soleus activity back here. This in itself would lower the hip. So the animal would be walking along tilted. This new hexer of the operantly conditioned reflex would have impaired the behavior produced by the old hexer of locomotion. That doesn't happen because the hip angle gets bigger. There's a compensatory change. As a result, the hip height stays the same. So the angles are different, but the hip height, which is a key feature, so the animal isn't tilted as it walks along, it's still stable, but that old behavior of locomotion is being produced differently. And you can see that also for up training. If we simply made the reflex bigger, the ankle angle gets bigger, the hip height would go up. But that doesn't happen because this angle gets smaller. The hip angle here gets smaller. That compensates and the hip height stays the same. So the old hexer has adjusted itself. It's changed because of the new hexer. It shares neurons and synapses with this new hexer, and it has to change to accommodate the changes produced by the new hexer. So in summary, then, a hexer is a distributed pattern of plasticity that changes continually to maintain the key features of its behavior, things like hip height and things like right to other factors of right to left symmetry. This was presaged by Nikolai Bernstein in the 20th century, who referred to behaviors as biodynamic structures that live and develop. And this, my friend Mark Latache at Penn State University, who's now the principal translator of Bernstein now into English, translated this kindly for me for this presentation into Russian. So this is Bernstein's concept. It's really very similar to the concept of the hexer. Behavior, the basis of a behavior that really changes to maintain the behavior. So the EMG and kinematic details may change. The key features of the behavior, the essential features that identify it as that kind of behavior, it identifies it as locomotion and as normal locomotion, those are preserved. A hexer is like a person with a single purpose in life, the preservation of a specific behavior. The hexers are all doing this concurrently. They're changing overlapping neuronal and synaptic populations. Thus, each hexer is continually responding to what others have done. Hexers produce a negotiated equilibrium. All the hexers are changing concurrently. Each is maintaining the key features of its own behavior. Because they share the CNS, the aggregate process is a negotiation. Hexers negotiate the properties of the neurons and synapses they all use. They keep the CNS in a negotiated equilibrium that maintains the key features of all their behaviors. A new hexer expands the negotiation. Old hexers change in response. The details of old behaviors may change, but their key features don't. So here's a cartoon indicating that. This is a central nervous system. It has many deltas, many places it can change. Here, during actually in utero, we acquire flexion withdrawal responses that are appropriate. They change a certain set of properties. A little later, early in life, we learn to walk. This changes a set of properties, and it also affects these guys that contribute to flexion withdrawal. So flexion withdrawal has to adjust. So this is adjusted to the new hexer. And later on, if additional skills are required, additional changes occur. And you get a negotiated equilibrium among these properties that keeps all these hexers happy. So this is an illustration of two hexers negotiating. Here's given a specific neuronal or synaptic property along this axis. This is its normal range. This is a behavior that depends on that property. And when it's low, when the property is within this range, the behavior is good. So this behavior, the hexer underlying this behavior, adjusts this property to keep it in a good range. So the behavior is properly performed. An additional hexer wants it a little differently. An additional hexer would be happiest with it a little over here. Between the two of them, they negotiate an equilibrium that keeps them both relatively happy. So that's the result of a normal negotiation among hexers. So taking this back to the central nervous system and what it does, which is to produce behaviors, here we have all the major areas of the central nervous system. They collaborate to control muscles to produce behaviors. They do this by all the areas are continually plastic in order to optimize this output to control the behaviors. This plasticity is being controlled by the various behaviors, the hexers of all the multiple behaviors that the person has acquired and is maintaining throughout life. So this is the normal nervous system. Okay, so that's the operation of the normal nervous system by our new understanding of how the basis of behaviors is distributed throughout the nervous system, and all the parts are continually changing to maintain these behaviors. The hexers representing the individual behaviors are continually changing to preserve the key features of their own behaviors. So what does this say? Let's assume that the BCI-based behaviors work the same way. How does the CNS acquire and maintain BCI-based behaviors? So here's a CNS BCI system. Now you have all the areas of the central nervous system, and you're taking signals from somewhere, maybe from the cortex, maybe from elsewhere, but you're taking signals here that you record. They're going to a BCI, which is producing the behaviors. You're now asking all these areas to adjust appropriately, not to control through muscles, but to control the BCI. And the BCI also has the ability to change. So this plasticity is occurring, the BCI's plasticity is occurring to produce BCI-based behaviors. This is what could be called a synthetic hexer. This is a term suggested by a collaborator, Sumner Norman, because it's a hexer that's made up of the natural central nervous system plus the technology that we add. This technology with the ability to adjust on its own. So you really have two adaptive controllers here. And this brings up the issue that Dr. Lebedev and others were alluding to earlier, that this is a very complicated problem. The BCI operation is not a problem we're not reading the mind. It's not a signal to noise problem. That's not the essential problem of BCI, of developing BCIs. The essential problem is getting this to work properly, understanding how we can use this, we can reorient this plasticity to a new purpose, how we can control we should manage the interaction between these two adaptive controllers, the normal nervous system and the brain-computer interface. What parts of this output do we delegate to this part, to that part? How do they interact to optimize their product? How are the results used to adjust the BCIs? The issue of how you use sensory input and vision, and you've heard about that from Dr. Benzmaya and Dr. Miller earlier. The various issues that come up, the kind of science that they're doing is what's essential if we're really going to understand these interactions and be able to produce very effective brain-computer interfaces. So these are scientific problems that remain largely unsolved at this point, and there are very initial promising efforts underway to resolve them. Those problems need to be resolved for us to get the most effective brain-computer interfaces, and that presumably will happen. But it's something that really needs to engage people and continuing to do that to get these results. So the implications of this situation I want to talk about for the three major BCI categories. So the first kind, the ones that certainly gets the most attention, are BCIs for people with severe disabilities. BCIs, for example, for people who are locked in, which Christoph Guber was talking about earlier. These are people who've lost these normal outputs. They don't control muscles anymore. So in theory, we want them to operate this way. We want to be able to reorient the plasticity. We want to be able to optimize the interaction here to produce optimal behaviors. So at this point, these applications are relatively limited. For most people, given current BCIs, conventional technologies, muscle-based assistive technologies are much better for all but a very few of the people with severe disabilities. Current BCIs require too much ongoing support to be widely used by people, to be used by many people. They're expensive, they require personnel ongoing for use. And most of all, probably, they have what I refer to as the Grand Canyon problem. This is something that actually Lee Miller talked about, that sort of kind of alluded to at the beginning of his talk, sort of, that here's a person standing at the edge of the Grand Canyon. Now, there is no way anyone who, without a suicide wish, would use any sort of a BCI to control his body while he was doing this. They're too unreliable, they're too inconsistent to trust in such a critical situation. And until we solve the scientific problems which people are now beginning to work on, we won't be able to change that. This problem will exist. We won't be able to use BCIs for really complex, critical things where failure is not acceptable. You don't need 99% control here. You need basically 100% control all the time. And BCIs are, at this point, are very far from doing that for complex sorts of behaviors. So BCIs for people with severe disabilities, while they require a lot of attention and for some people can be useful in limited ways, are at the moment a relatively minor use of BCIs. They hopefully will become a great deal better in the future, but at the moment, they're relatively limited. So moving on to the second major category, which also gets considerable and increasing attention, BCIs for people without disabilities. These are people who have normally functioning nervous systems and are going to use a BCI for various other purposes. So basically, this is the situation. This is what we're trying to do. And it was very interesting for me putting together this slide, because I put together this slide and it looked like this. And I thought, boy, this is a real mess. I can't show this to people. This is ridiculous. I have to simplify this. And then I realized that no, this is realistic. This is what the situation really is. It is very much a mess. It is very complicated. Here we have this normal nervous system that's doing what it normally does, and all these normal hexers are adjusting to produce normal muscle activity. And then we're asking all these areas to readjust, to change also, to acquire this new kind of hexer, this synthetic hexer, to reorient to some extent the plasticity so that they can optimize control of the BCI, optimize the interaction with the BCI, which itself is adjusting to produce this new kind of behavior very effectively. This is a very complex situation, and it's an illustration of why all the basic problems that people are now addressing, some of which you've heard about so far today, really need to be fully addressed and need to be solved before we can produce really effective BCIs for people without disabilities. So this is another illustration of that. These, I showed you this before, these are normal hexers. They're all very happily sharing this negotiated equilibrium. If we add a synthetic hexer here, we're going to affect in very, as yet unknown ways, many of these areas. We're going to interfere with this normal negotiated equilibrium. Solving the problem, how we do this, how we get this now complex system to work, is a major problem that will require a lot of work. So BCIs for people without disabilities, at present they're non-invasive systems that often have very major non-brain contamination from EMG and eye movements and other sorts of artifacts. They have very minimal, basically trivial capabilities. They're much inferior to muscles, and they certainly have the Grand Canyon problem. They're too inconsistent to be used for complex, critical sorts of tasks like this. So those two major areas are areas where a lot of science needs to be done, a lot of work needs to be done, and hopefully that will occur, and those BCIs will become much more capable and much more useful. In the meantime, the third category, as at this point, is promising right now. The BCIs to improve rehabilitation, the sort of work that Christoph Guger was talking about earlier. For one thing, there is a huge population that could benefit. The many millions of people around the world have had strokes, have other severe disabilities, cerebral palsy, multiple sclerosis, spinal cord injury. There's a very large population that could benefit from BCIs, which can enhance the results of current rehabilitation. There is no Grand Canyon problem. Perfection isn't essential. What's important is to add value. We want to be able to help a large proportion of these people to recover better. So this is the concept of BCI-based targeted neuroplasticity. This is BCI for rehabilitation. So BCI-based targeted neuroplasticity. So here you have a hexer, a nervous system, a hexer that's changed properties of specific sites so that it's appropriately performed. There's a stroke that's disabled this hexer. The hexer is now impaired. This might be locomotion. This could be reach and grasp. The idea is to develop a synthetic hexer that goes in and can change a critical property. A critical property can be improved. And this will enable improved practice of the behavior, that will improve the negotiation, and will lead to an improved situation where this hexer is now somewhat happier or much happier than it was here, where the performance is improved and the behavior is restored to a greater degree than it would be by normal rehab. So this you saw before. This is the normal range. These are two hexers that have negotiated. Suppose there's a stroke or a spinal cord injury, which takes this property and puts it here. This could be the strength of a stretch reflex. This could be some other property that the normal hexers cannot adjust this. They get stuck in a local minimum. They can't deal with the fact that this property is now very abnormal. And this property, if it's critical enough, may be entirely preventing practice of the behavior. It may entirely prevent normal rehab. If we can go in with a synthetic hexer, a hexer whose entire goal in life is to change this property. That's what it is. It's like a person that all it wants is to change this property, and it adjusts that property and brings it back down into this normal range where these hexers can now take over and maintain it again. This can then go away, and you now have a situation where more normal practice can occur and you enhance rehabilitation. So this is the concept of targeted therapy. This is another possibility for using it. EEG sensory motor rhythms, as we know, decrease preceding movement. This again, Christoph Google referred to this. It was originally described by Dr. Furchtscheller, now about 40 some years ago. You see the decrease in sensory motor rhythms, desynchronization occurring prior to a movement. This is a right hand movement. So this is the top of the head with the nose here. The desynchronization is focused over the left hemisphere, left sensory motor cortex. So what Dennis McFarlane et al. Demonstrated about 8 years ago was that if you trained a person to improve this desynchronization prior to movement, you could make the movement better. The movement time went down when they decreased the sensory motor rhythm. The movement error went down when they decreased the rhythm. And more recently, Picari et al. In Donatella Mattia's group has applied this for stroke rehabilitation. They've used EEG and have trained people to decrease sensory motor rhythms over the affected areas of cortex during movement to improve hand grasp. And they were able to show that with the training, they improved the desynchronization over the contralateral cortex. And this was associated with improved movement and with improved hand grasp and improved function, measured by a number of scales. The people who had used the BCI versus the control group recovered more effectively because of the use of the BCI. So this is an area of BCI application which can be effective now, and it could benefit quite a large number of people, and it's very fortunately gaining considerable interest and considerable attention. And there's a lot of work in this area, which is increasing, and it should, because this is something that can help a lot of people right now. So in summary, in regard to the substrates of BCI-based behaviors, BCIs enable people to acquire non-muscle-based behaviors. We've looked at the substrates of these non-muscle-based behaviors in terms of the substrates of normal behaviors, muscle-based behaviors. And as a result of the progress of the last 50 years in understanding the ubiquitous plasticity of the central nervous system, we know that normal behaviors are produced by distributed networks of plasticity that change to maintain the key features of behaviors. We're calling these distributed networks hexers. Hexers share neurons and synapses. They continually adjust to each other. Thus, they maintain the central nervous system as essentially a negotiated equilibrium. It's a negotiation among the hexers. They're really like a bunch of people, each of which has a particular purpose, maintaining the key features of its own behavior, and they need to negotiate this multi-user system. They're all using the same system, the same neurons and synapses. So they have to figure out how they can all use it. They can all be reasonably happy with how it's set. So a BCI creates a new kind of hexer, one that has two adaptive controllers. not just the CNS and all the various parts of the CNS, but this technology that we add on to the CNS, and we connect it by taking signals out of the CNS and giving them to the technology. This is a synthetic hexer. So this is similar. This produces the BCI-based behavior, and as I said, this raises a whole lot of problems. How these two controllers get along, what each one does, how they interact with each other, how they adjust to each other. For the point of view of the central nervous system, how the various parts of the central nervous system reorient their plasticity to do this new kind of task. And if this is a normal nervous system, or a nervous system that retains at least some aspects of its normal muscle function, even if it's had a stroke, which almost all the people with severe disabilities have, some remaining normal sorts of abilities, that becomes the problem of reconciling this new kind of plasticity with the old kind of plasticity, which it's also trying to improve at the same time or restore. So as a result of these problems, primarily, present BCIs are very simple, and they're slow, and they're unreliable. And we're now addressing, as you saw to a considerable extent today, the kinds of problems that must be solved for us to make them so they're not simple, and they're not slow, and they're not unreliable. At the same time, as a result, BCIs for communication and control have relatively limited value at present. They have some value, but it's relatively limited. On the other hand, BCIs for rehabilitation are potentially very valuable even now, that we can help a large number of people if we can enhance rehabilitation. And it appears that with using BCIs to produce targeted plasticity, we can in fact enhance rehabilitation and improve function. So it's a complicated situation that I've presented from the viewpoint of the substrates of BCI-based behaviors. It's to hopefully the sum total of my presentation is sobering and also encouraging. So there's a lot of science left to be done. There's a lot of things we have to understand, having to do with the interaction of the controllers, with how we provide feedback, what the nature of this problem is, how we control the plasticity to enable a BCI, a synthetic hexer, to operate as effectively as a normal hexer does in controlling muscles. So these problems have to be solved. If we do, communication control could become a great deal better. At the same time, we're able practically to make considerable contributions to improving rehabilitation. So it's a pretty complicated and exciting situation. So many people have contributed to this work over the past now 40-some years. I want particularly to bring out my friend Dennis McFarlane, who, as many of you know, most of you, probably all of you know, is a major figure in the development of BCIs over the past 30 years. What you may not know, unfortunately, that he tragically died unexpectedly a number of months ago. So I want to recognize him. I was privileged to work with him for decades. And he's really made major contributions to the development of BCIs. And the support that we've had from NIH, from the VA, from a number of foundations. Thank you very much, and be happy to take your questions.
Thank you very much. Very wonderful talk. I have a call from, I got a question from the Dr. Lee Miller. So Lee, could you tell your question to John directly, please?
Sure. First of all, John, I had no idea that Dennis died. I'm very sorry to hear that. I see my camera's off.
Yeah, thank you.
And as far as the question goes, I just wanted to comment. I agree with many of the things, of the comments you made. I think the application to rehabilitation clearly is a very important component of BCIs. I'm fascinated by the resemblance between your cooperating hexers thing and a deep network architecture called transformer. I don't want to ask a question about that here. It's a little bit technical, but we might talk about it over a virtual beer at the bar. But
Okay.
the one thing that I think I might take issue with, and I'd like your thoughts on, is your comments about BCIs being completely novel motor behaviors and requiring extensive learning. I wonder, would you accept the possibility that an EEG controlled cursor is fundamentally a different thing than a highly accurate decoder of muscle activity from single neurons, and that if it will take some learning, but I think a biomimetic approach may take significantly less learning, and I think is important to shoot for.
Yeah.
What's your thought about that?
Yeah, no, I agree. And I mean, I think the situation has become clearer, and I think everyone understands it better than the situation 20 years ago. Single neurons, obviously there's a lot of information, a lot of precision there that's possible that you're not going to get out of EEG. There are, at the same time, for example, now people are starting to say that, well, maybe if you back off a little bit on the resolution to local fields, if only from the viewpoint of the stability of recording over months and years, you may be in a better situation. So it's really finding the level of the language. And clearly the single neuron activity is one level of the language. And it's a pretty precise level. It's not by definition necessarily the best level for this particular practical application. I mean, it may be depending on, I guess, your technical capabilities, which are getting better in terms of recording, etc. But I mean, for example, what Andy Schwartz has done looking at multiple areas, when you put multiple areas together, you can be better than just taking neurons from a single area. You're really kind of reassembling the whole nervous system. The idea that behaviors are produced by distributed networks means that if you are going more widely, that you can presumably get better control. But I agree with you that, yeah, EEG is not, I've to some extent played devil's advocate in pressing EEG, but yes, I don't argue with you on that.
Okay.
Okay, one more question. The question comes from the floor. How do you use the hexer concept practically when working with the neural interface? How can hexer be distinguished?
Okay, well, the idea, I'm really fascinated, and basically it's at the level of fascination because I don't have a whole lot of, I'm not an engineer and I'm not an expert in control theory, but clearly there are a lot of issues when you think particularly about how these two controllers interact. First is the basic issue, how you set it up, what responsibilities you give to one and what to the other. But, the only sorts of principle that I can sort of come up with it sort of simplistically at this point is that you want to maximize we have this very sophisticated controller, the brain, and then we have this very relatively clunky and simple controller that we're adding onto it. That the function of that, at least a good part of the function, is to enable the central nervous system's very sophisticated and complex plasticity to be used to the best possible fashion. So basically to be able to offer opportunities to the brain to use its capabilities and really not get in the way of it, to enable it. The simplest way to think about this is that if you're using sensory motor rhythm amplitude to control something, the BCI needs to be able to adjust to the range of sensory motor rhythm amplitudes that the brain can produce. By making that simple adjustment, it enables the brain to then do what it normally does. Those are the kinds of things that are really interesting, and they really need to be resolved for us to get really good BCIs.
Thank you very much. We still have several questions in the window, but the time is coming. So could you, Dr. Walpole, please answer to the question on the by typing in the window later afterwards. So thank you very much, Dr. Walpole. Very impressive talk. Appreciate. So thank you very much, all the participants. The session is closed. And the organizer of this meeting will give us the announcement for the new bar.
Yes. No. Before the new bar, we have some announcement. Thank you, John. Thank you all speakers. Thank you both chairmen. And I make announcement in Russian because it's about Russian participants. Дорогие друзья, я от имени организаторов,
on behalf of the organizers, allow me to apologize. First of all, on behalf of all of us, I want to say that I'm sorry that some of you lost Zoom translation links, Zoom links broadcasting. It was our fault, and that's why eventually a decision was made that participation in the conference through Zoom will be free of charge. All the money that you paid will be paid back to you. Your Zoom link is on the website. Also, I need to apologize for failing to show you the exhibition. I think we will still show it to you. These are a couple of apologies that I've had to make, and the nice announcement is from my partner here. Tomorrow we'll have another informative day, 2 events going on at the same time. We'll have a symposium on brain-computer interfaces from signal processing to neurophysiology to clinical applications. That's in the morning. The symposium consists of several parts. Consists of 3 parts. In between, we will make an attempt to visit the virtual exhibition. I hope you know how to do that, and please move around and look at a variety of booths. At the same time, we'll have a separate conference on cognitive health and longevity, and during the breaks, we will be inviting speakers for brief interviews. Stay with us. Now we're moving on to the Neurobar. We can give the floor to Yannick, who will give us the details.
Hi everyone. Thank you very much for this amazing day today. I could not attend all of the talk, but definitely the last one with John Walpole was amazing. So to close the day, we invite all the attendees to join us at the Neurobar. So I'll be there myself, Yannick Roy, co-founder of Neurotech X, which is an international neurotech community. We do have chapters around the world. We do different kind of initiatives, from student club to our newsletter, webinars, events, and our famous Neurobars that we've been running at different events, where basically you come up with a drink. So that's the only requirement. You come up, you show that you have a drink. It could be water, it could be vodka, it can be, depending on the time of the day, it can be coffee. And then you join us, open your camera, your microphone. If you really can't have your camera on, it's okay. We will still let you in, but we'd like everybody to have the camera because it's a social event where we just talk. It's informal. There's no structure. We'll just talk about different event. So the way that you join the Neurobar, if you go on the exhibition website of the BCI Samara conference, you will find that you can enter the exhibition. And then you get in the island where you have all the booths. So you navigate on your left, you will see the Neurotech X and the Neurobar booth. And then by clicking on that booth, you'll see a big red button called Neurobar. You can really not miss that big red label. You click on it and it will open a Zoom link. You might have the pop-up on Zoom that will automatically start your Zoom application on your device. If it does not, then there's a button called Launch Meeting that you might want to press to make sure that it launched the meeting on your Zoom. So if there is any issue, please contact either the organizer of the conference or info@neurotechx, and we'll make sure that you get in the Neurobar so that you can enjoy the social. So once again, it's very informal. Usually it's kind of a Zoom call where we have people. We'll have breakout rooms. We'll split people on different teams, topics that they want to discuss. And usually it lasts from anywhere from 1 hour to 6 hours. Sometimes we have people that stay quite late on the Neurobar. So I will quickly share my screen just to make sure that everybody can follow if they're not familiar with the exhibition website. So just give me 1 second. Share screen. So you should be seeing the exhibition Samara website. And then you have, when you go on that website, you will see the enter the exhibition and poster session, which brings you on this amazing virtual island that I hope you've navigate and you've seen with the different exhibitors, different booths. And if you move forward with this hexagon in the middle, or you can navigate through the different windows here, I'll let you play with it. But the simplest way is that you navigate with the different hexagon. And here you'll see on your left, the NeurotechX Neurobar website on the left here. And if I click, I will get in the booth. And then, it's now blue, the big button. So you will see here that you could have the video on NeurotechX if you want to know more about ourselves and inviting to the Neurobar. And then you have the big button at the top that you click, and it should open a Zoom window that you will end up in a different Zoom as you did for this one today. So let me stop share my screen. And with that, I'll invite everybody else to join. Ilya just posted the link of the exhibition, so you can click there directly if that makes it easier for you. So thanks again for the organizer. I hope to see as many as you as possible in the Neurobar to close this amazing day. So go grab a drink. We'll start in 10 minutes on the other side at the Neurobar. Thank you very much. And back to the organizer, I assume.
Итак, друзья, мы...
All right. Well, we say goodbye for tonight. Looking forward to see you tomorrow. We'll have lots of interesting stuff going on. And now, have a nice evening. And as you communicate at our symposium, will start at 10 in the morning, Samara time. And goodbye.